Hello and welcome to module 3 of our exploitation basics series. In this module we learn about egg hunters, which is a very interesting technique to get out of limited buffer space that we might have available on certain occasions. So these are the few software that I am assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. They will help you in learning more about the software, or even if you want to learn them from scratch, they will help you with that also. So this is our module structure. Our module is divided into 6 parts: introduction, fuzzing, POC creation, controlling the execution, bad character analysis, and cracking the shell. We are on the first part, that is introduction, wherein I give you a bird's eye view of the technique that we'll be using in this module, and I also give you a brief about the tools that we will be using in this module. So these are the tools required for this module. We'll need a virtualization software. You can use either VirtualBox or VMware depending on your preference. And we need both a Linux machine and a Windows machine. I will be using both as a VM. For Linux, I'm using Kali Linux 2018.1, and on this machine I need Spike, Python 2.7, and Sublime Text or Notepad++. Again, you can choose whatever you are comfortable with. For Windows, I am using Windows XP SP3 again as a virtual machine, and on this machine I'll need Immunity Debugger, Mona library for Immunity Debugger, and our target software will be Vulnerable Server. The download link for this and all other software is mentioned in the description below, so please check it out. And again, we need a text editor. You can use either Sublime Text, Notepad++, or any other text editor of your choice. So what is egg hunting or egg hunters? So egg hunting or egg hunters is basically finding an Easter egg in a program's memory. The only difference is that instead of a chocolate egg, we get a shell back from a target machine, and that is beautiful. So as you can see here that this is an application's allotted memory, and on certain occasions when you start writing an exploit or when you come across a buffer overflow in an application, you might only have a limited accessible buffer available to us, which is typically 35 to 60 bytes. Now, if you know shellcoding really well, you might be able to fit in a shellcode that will give you either a bind TCP shell or a reverse TCP shell within these bytes. But usually this is not sufficient for the shellcodes that you generate from MSFNM or any other tool. At the same time, we do have a large buffer available to us over which we can write, but this is not accessible to us via shellcode. So this is a buffer which is typically greater than 300 bytes, and this is a perfect place for you to place your shellcode. But since we cannot directly reach it, we need a technique to find this code in the memory and then execute it. So that is where egg hunters come into picture. So in egg hunters, what we do is we write a shellcode in this inaccessible buffer, and we tag it with our egg. So egg is nothing but a tag or a word which you prepend to your shellcode, and we prepend it twice, and I'll explain that in a minute why we do it twice. So we prepend the egg twice to the shellcode, and then in a limited buffer space we write the shellcode to find this egg or the tag. Now what happens is when this code runs, it first matches the first occurrence of this egg, and then it continues to find the second occurrence of this egg. Now if it finds two occurrences, it then goes ahead and executes the shellcode. However, if it finds only one occurrence, it will move on from this memory to the next memory address. That was it about egg hunters. Things will get more clear as we move ahead with this module and do a practical example in later parts. So these are the learning resources that you can use to learn more about the software or the techniques that we are using in this module. Thank you guys for watching this video. I'll see you in the next part. Hello and welcome to part 2 of our egg hunters module. So these are the few software that I'm assuming that you as a learner have a basic knowledge of. If you don't, or if you want to learn these from scratch, please check out the resources mentioned at the end of this video. This is our module structure. We are in part 2, that is fuzzing, wherein we fuzz a target application to find out the vulnerability. So before I move on to fuzzing, I would like to discuss the exploit development process flow in brief. So this process starts by identifying a vulnerability, which is done by a process called fuzzing, which we'll cover in a minute. And once we have identified this vulnerability, we write a simple POC script in any of your preferred languages. I am using Python for this module, and replicate the crash in our application. Now this crash is then studied by attaching a debugger to the application, and by that process we try to identify whether we can exploit this vulnerability to obtain a shell. Once we have found an exploitable vulnerability, we enhance our POC to take control of the execution flow, and then we send the application all characters from hex 00 to hex FF to identify the bad characters. Now this bad character analysis is necessary because there are certain characters which might break our shell code. Before we generate our shell code, it is essential to do away with those characters. Now once we have identified the bad characters, we can then generate a shell code using any of the automated tools, or if you're comfortable with this process, you can even write your custom shell code. We then integrate this shell code into our POC and fire it against the target software and obtain the shell from the target machine. So what is fuzzing? So fuzzing is a method for discovering faults in a software by providing it unexpected input and monitoring for unexpected behavior or exceptions or any crashes. So as I said previously, that these crashes are then studied via debugger to identify whether the vulnerability that we have triggered can be exploited or not. Fuzzers are of two types. One is mutation based fuzzers, wherein you give a sample file to a fuzzer and then the fuzzer mutates the contents of that file and run it against the application. Second are generation based fuzzers, wherein you give a sample file to the fuzzer and then it generates further sample files using that first sample file. So while fuzzing, you can target various kind of things. You can target environment variables and arguments. You can target web application and server. You can target file formats, network protocols, web browsers, and in memory. In this module, we'll be targeting a vulnerable server. To learn more about fuzzing, you can check out this book, Fuzzing Brute Force Vulnerability Discovery. This is an excellent book to understand the fuzzing process better. Our target software for this module is Microsoft Windows XP SP3, and on this operating system, we'll be running vulnerableserver.exe. Now, vulnerableserver.exe is a application that is vulnerable on purpose, and there are multiple commands that are vulnerable to buffer overflow. And we'll be exploiting the vulnerability in kstat command, which can be done using egg hunters. So let's move this to the lab. So on the Windows machine, let's run vulnerable server. Let's move to a Kali machine. Now, before we fuzz an application, it is essential for us to understand the protocol the application understands. So to do that, we first connect with the application using netcat. So vulnerable server runs on port 9999 by default. And if I issue help, so these are the commands available to us to talk with the application, and the format of these commands is command space value. So as I said that we'll be exploiting kstat command, and this is the format in which this application understands this command. So I'll create a small spike script for this command, and I've already created it here. So this is a very simple spike script. When we read a line and we send it a string kstat space, and then we send it the value of kstat as a string variable. So we'll be fuzzing on this variable here. So now I'll go ahead, disconnect from vulnerable server here, and run the spike script. So let's see if we have triggered the crash. So looks like we have triggered the crash, but since we didn't attach our application to the debugger, we won't know at what point the crash was triggered. So what I'll do is I'll go back to my XP machine, and this time I'll run immediate debugger and open vulnerable server init, run the application, and I'll fire my spike script again. So looks like a crash has occurred. So let's just pause it and move to our XP machine. So you can see that an access violation has occurred when executing 414141, which is nothing but hex for capital A, and application has paused, and this was the string that was sent to the application. Our EIP has been overwritten with capital A's, so is EBP register. If I follow the ESP in dump, let's see what we get. So the ESP points to our buffer, but this is a very limited space that is available to us. If I just move back a little bit, so this is a larger space that is available to us. So what we'll have to do is we'll first have to get out of this limited space. Probably we have to jump back to the space and write our egg hunter shellcode here, and then in memory somewhere we'll find out a way to place our shellcode, because none of our registers currently point to the larger buffer available to us. So as you can see here, that a larger buffer than this is not available to us via this command. So we'll probably have to figure out a way to place our shellcode in the application via some other command, which we'll cover in the later part of the module. Now, how do we identify the string that was sent to the application? So one way is to find out at what point the application was crashed. So if I go ahead and check the output from the second run of my generics and TCP command, so it seems to have broken on the first variable itself, because I didn't get any line from that. And if I go ahead and check the output from the first run of the command, so here we are getting tried to send to a closed socket. Let's see from where this command starts. And so this command seems to have started from variable 74. So that means a variable 73, which has a length of 256 characters, seems to have triggered the buffer overflow vulnerability in the kstat command. In the next video, we'll create a POC and try to replicate the crash. These are the few learning resources that you can use to learn more about the software or the techniques that we're using in this module. Thank you guys for watching this video, and I'll see you in the next part. Hello and welcome to part 3 of Egg Hunters module. In the last part, we identified the vulnerability in the kstat command of a vulnerable server using fuzzing. In this part, we'll take the results we got from the fuzzing technique and we'll create a POC out of that. So these are the few things or software that I am assuming that you as a learner have a basic knowledge of. If you don't, or if you want to learn more about these software or you want to learn them from scratch, please check out the resources mentioned at the end of this video. So this is our module structure. We are on part 3, that is POC creation. Our target software is Microsoft Windows XP SP3, and on Windows we are running a software called vulnerableserver.exe. Now this software is vulnerable on purpose and it has many buffer overflow vulnerabilities which can be exploited in a variety of ways. We will be exploiting the vulnerability in kstat command, which we identified in the last part. So what is POC or proof of concept? So in this case, a proof of concept is nothing but a script to replicate the crash in the program. It can be written in any of the languages. I am using Python in this module, and it can be enhanced further, or rather it is enhanced further to create an exploit out of it. So now it is up to you if you want to enhance that POC to create a workable exploit out of it, or if you want to leave it as a demonstration rather than creating a full exploit out of it. So let's move this to the lab. So on my XP machine, I'll run immunity debugger, and in it I'll run vulnerableserver.exe, play the application, and I'll move back to my Kali machine. So on my Kali machine, I have created a very simple Python script that creates a TCP connection, creates an evil string of 256 A's, which we identified in the last part, and it then builds a command kstat space plus the evil string, and then it connects to our target machine at this IP address on port 9999 and then sends the command to the machine. So now I'll run this script and let's see what happens. Now I'm going to go back to my Windows machine, and so access violation has occurred, and as you can see that it has an access violation when executing 41 41 41 41, which is nothing but hex for capital A, and application has paused, right? And here you can see that EIP has been overwritten with 41, 41, 41, 41, and so has EBP. And on EAX we have the string that we sent to the application. Let's follow this in dump. So this is the command that we sent to this application, kstat and A's. So these don't appear to be 256 A's. Let me just run this again. I'll restart the application. And what I'll do is I'll increase the size of my buffer to, let's say, 700. Save this. So I'm doing this to check whether I can increase the size of the buffer available to me so that I can place my shellcode there. I'll run the script again. And let's see. So again, an access violation has occurred, application has paused, and I'll follow EX in dump. So looks like the buffer is of the same length as it was in the earlier case, and the increasing of a buffer in our POC has had no effect on the buffer that is available to us after the crash. So we'll probably have to employ some kind of technique to make use of this limited buffer, and at the same time find out a way to place the shell code in the application memory. So we'll do that in the later part. That was it for this video. So these are the few learning resources that you can use to learn more about the software or techniques that we're using in this module. Thank you guys for watching this video, and I'll see you in the next part. Hello and welcome to part 4 of our Egg Hunters module. In the last part, we created a POC to replicate the crash in a vulnerable server. In this part, we'll further enhance that POC and check if we can control the execution flow of the application. So these are the few things or software that I'm assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. So this is our module structure. We are on part 4, that is controlling the execution. So in this part, we'll first identify the location of the character which overrides the EIP register. We'll do this using MSF pattern create and MSF pattern offset utilities available in Kali Linux. We'll then verify this location, and once we have done the verification, we'll find a way to jump to our ESP register. Now in order to do that, we can either hard code the ESP register address, or we can find an accessible and a reliable memory address in memory that contains a pointer to the instructions such as jump ESP or call ESP. Now there are two prerequisites that we require for this pointer. One is that it should not be affected by data execution prevention and address space layout randomization, and it should not contain bad characters also. Now bad characters is something that we'll identify in the next part, so we'll just have to go by a trial and error basis for now. And lastly, we'll see that if we need a jump back to our shellcode, because we had a limited buffer available to us in this particular application, so a jump back might be required to jump to a bigger portion of the shellcode. So let's move this to the lab. On my Windows XP machine, I have vulnerable server already running and it is attached to immunity debugger. Now I'll first find out if we need a jump back to the bigger portion of the shellcode. To do this, I'll fire the POC again against vulnerable server. To do that, I'll go back to my Kali machine and I'll run this POC again. So our application has crashed and it has paused. Now if I follow the ESP register in dump, we see that we have only a limited portion of buffer available to us. And if I scroll back a bit, so here is a larger portion available to us. So what we'll have to do is we have to put a jump instruction here that can take a jump back into this portion of the shell code, and then we'll place our egg hunter code in this part. So for now, I'll go back to my Kali machine and open a new terminal window, and I'll run msf pattern underscore create, and I'll give it a length of say 256 characters. This is the pattern that has been generated. I'll copy this pattern and I'll paste it in our POC. Save it and then restart the vulnerable server. Run, and I'll fire the POC again. So here our application has crashed and our EIP has been overwritten by these characters. Let me just copy the selection to clipboard. I'll go back to my Kali machine and this time I'll run MSF pattern offset, and I'll give it a query for the characters that we have copied. So this is the offset at which the EIP gets overwritten. Let's just verify this. I'll remove this pattern and I'll put A into 70 plus I'll send it 4 B's, and in the remaining part I'll send C's, let's say 150, and I'll restart the application in immunity debugger, run it, and I'll fire the POC again. Let's see, yes. So our EIP has been overwritten with 42, 42, 42, 42. So looks like we have hit the correct location for EIP. Now our next task is to find the pointer to jump ESP instruction. To do that, I'll restart the application in immunity debugger again and run it. And in here I'm using Mona library to do that task for me. Jump RESP. Now this will give me a set of pointers to the, or rather a set of memory addresses which hold the pointer to jump ESP instruction. Now if I check the logs window, here it is, and it has returned these characters. Now I check this ASLR is false and safe ACH is false. Alright, so we can use any of these memory addresses for our purposes. I'm just going ahead and using this one. You can use any of the addresses available here, and I'll copy the message part of it. What I'll do is I'll paste this message part in our POC, that is for our records. So this will tell us from which DLL we are using this address. So this is the address that we'll be sending the application now. I'll write it in the little endian format because that is what Intel processors use. So here I have written the memory address that points to the jump ESP instruction. I'll copy this and move back to my Windows XP machine. I'll restart the application and run it, and now I'll put a breakpoint on this memory address. Now I've put a breakpoint on this instruction here. Now let me go back to my Kali machine and I'll run this POC again. Let's see if we have hit a breakpoint. So we have hit a breakpoint at this memory address, and if I step into it, we'll jump to our ESP register, and here we have the buffer of C's, which is so the hex for capital C is 43. And this is where we have written the address of jump ESP instruction. And now what we'll have to do is do a jump back to this portion of shell code. Now to find out the appropriate instruction to do that jump back, we'll use an utility called MSF NASM shell. So I'll use MSF NASM underscore shell, and now let's say I want to do a jump back of 90 bytes. So I'll do jump $-90, and the instruction for that is EBA4. Now I'll have to put this instruction in my POC. Copy this and I'll just put it here for our records, and I'll place this instruction after we have overwritten the EIP register, that is at this place. Save it, restart the application in immediate debugger, run it, place a breakpoint at this memory address, and I'll fire my POC again. Now let's see what happens. We have hit a breakpoint and I'll step into it. We have jumped to ESP, and here is our jump instructions that will take us around 90 bytes, and now I'll step into it, and it has taken us here, which looks like an area that is beyond our shell code, so we'll probably have to reduce our jump by around 20 bytes. So I'll do that. I'll make this 70 EBB8, and I'll put B8 here. Save it, run the application again, restart. I'll put a breakpoint at jump ESP instruction and fire my POC again. Let's see what happens now. So we have hit the breakpoint and we are at jump ESP instructions. Step into it. We come to our short jump, and let's see this time where it takes us. So this time it has placed us in our buffer, and then we can use this place to place our egg hunter code, and then we'll figure out a way to place a shellcode in the memory somewhere, which we'll do in the last part of the module. So these are the few learning resources that you can use to learn more about the software or techniques that we're using in this modules. Thank you for watching this video, and I'll see you in the next part. Hello and welcome to part 5 of our Egg Hunters module. In the last part, we enhanced our POC and took control of the execution flow of the application. In this part, we'll further enhance our POC by identifying the bad characters for our application. So these are the few things or software that I'm assuming that you as a learner have a basic knowledge of. If you don't, or if you want to learn them from scratch, please check out the resources mentioned at the end of this video. So this is our module structure. We are on part 5, that is bad character analysis. So in bad character analysis, we send all possible characters, that is all possible hex characters from hex 00 to hex FF as part of our buffer, and see if the application treats any of these characters differently and it breaks our buffer. Now if any of these characters breaks our buffer, that is bad for our shell code, because then it would change the entire meaning of the shell code, and our shell code won't execute and we won't get a shell back. Now by default, hex 00 is treated as a bad character because it is a null byte and it truncates our buffer. So let's move this to the lab. So on my Windows machine, I already have the vulnerable server running, and I have attached it to Immunity Debugger. Now to generate this byte array of hex characters 00 to hex character FF, there is a command in Mona library, that is Mona byte array. When I run this command, it will give me an array of 256 hex characters. As you can see here, that these are the characters that have been generated by this command, and these characters have also been stored in the file called bytearray.txt in the installation directory of Immunity Debugger. So I have it here, and this is the file that was generated by Mona library. So I open it and I copy this array of characters generated by Mona library, and now I'll move to my Kali machine and update a POC with these characters. So this is a short trick to generate these characters if you don't have them at hand. Now I have updated the POC with these characters, and I have divided them into 4 byte arrays. I have done this because we have a limited buffer available to us, and we will not be able to send all 256 characters in one go. And if you look here, we will be using this space of 70 characters to send these byte array one by one, and hence each byte array is a set of 70 characters, and the last one is a set of 45 characters. So when we'll send this last array, we'll have to pad it with other characters to make it a buffer of 70 characters. So now I'll change this, and instead of 70 A's, I'll put byte array 1 here, save this, and on my Windows machine, what I'll do is I'll put up first go to view CPU, and I'll put a breakpoint at the jump ESP instruction. We have already removed hex 00, so we are sending from hex 01 to hex 46. Let's save it and fire the POC again, and let's see what happened. So we have hit our breakpoint. Let's step into it, and if you just move up, you'll see that this is the buffer of characters that we had sent the application 01, and just glancing through, it looks like till 46 everything is intact. So these characters have made it successfully to the application. Now I'll restart this application, run it, put a breakpoint at jump ESP instruction, go back to my Kali machine, update a POC with byte array 2, and this time we are sending from hex 47 to hex 8C. I'll run the POC again and move back to my Windows XP machine. We have hit a breakpoint. I'll step into it. This is a short jump, and I'll move up to the buffer, and we have sent it from hex 47, and just glancing through, again it looks like our buffer has made it successfully till 8C, and we'll repeat this process again for the third array. Start, run application, set a breakpoint, and go back to my Kali machine, and I'll put byte array 3, and this time we are sending from 8D till D2, and I'll run the POC again and move back to my Windows machine. We have hit the breakpoint at jump ESP instruction. I'll step into it. We have come to the short jump. I'll move up the buffer, and here you can see that from 8D our buffer has made it till D2. So that is what we had sent, and none of these characters seem to be mangled up, and they have made it to the application intact. So let's repeat the process again for the final time with the last buffer. Yes, run, and go to expression. I put a breakpoint at jump ESP instruction. Move back to my Kali machine. Put a byte array 4 here, and this time we'll have to pad it with 25 A's to make it a buffer of 70 characters. Save it, run the POC again, and on my Windows XP machine I've hit the breakpoint. Step into it, I'll land on the short jump, and I move up the buffer, and this time we are sending it from D3 till FF. Yeah, so all characters seem to have made it to the application intact. So that means in this particular instance the only bad character was null byte, which we had already removed, and every other character has made it to the application intact. Now a thing you might be wondering is, was there any shortcut or a better way to identify the bad characters? Unfortunately, with this command, because of the limited buffer, this was our only way. Had been any other command, maybe trunk command or LTER command, our buffer size would have been much larger, and we would have been able to send it entire buffer of or entire array of 256 hex characters. So in that instance, we wouldn't be repeating this step multiple times. But with limited buffer, this is your only choice to do it this way. You can automate this process by writing a Python script but that is out of scope of this video. So as we identified that in this case only hex 00, which is the null byte, was the only bad character for this application or for our shell code. It is a global terminator and hence it truncates any characters that appear after it. So same thing happens with line feed and carriage return and end of file. They truncate the buffer and hence they are treated as bad characters in certain cases, which we have seen in previous modules. But in this only hex 00 was the bad character, so that is an advantage to us. These are the few learning resources that you can use to learn more about the software or techniques that we are using in this module. Thank you for watching this video and I'll see you in the next part. Hello and welcome to part 6 of our Egg Hunters module. In the last part, we identified the bad characters for our shell code. In this part, finally it's time to get a payback for all our efforts in terms of a shell. So these are the few things or software that I'm assuming that you as a learner have a basic knowledge of. If you don't, or if you want to learn them from scratch, please check out the resources mentioned at the end of this video. This is our module structure. We are on part 6, that is cracking the shell. So in this part, we'll have to do a couple of things first. We first have to find a place to store our shell code because we have a limited buffer space available to us. And then we'll generate our egg hunter code using Mona library of Immunity Debugger. This is the command that we'll be using to generate the egg hunter shell code. And finally, we'll be generating our payload shell code using MSF Venom, and we'll be using this command. And to get the shell back, we'll be running a multi-handler listener on our Kali machine on port 4444. So let's move this to the lab and start hunting for a place to place our shell code. One of the ways to store our shell code in the application memory is to check if we send the application any other command and if that command and its value gets stored in the application memory. So I have updated my POC to do just that. I have added an additional code section here which creates a socket, connects to our target machine on port 9999 and sends the gdoc command plus the shell code. For now, I'm using a junk value for the shell code. What I'll do is I'll create a MSF pattern of length 1000 bytes and replace these thousands A with that pattern. Then we'll send this command and this pattern to the application along with our original command, and then we'll use Immunity Debugger to find that pattern for us. So now I'll generate this pattern. I'll use MSF pattern underscore create, and I want a length of 1000 characters or 1000 bytes. Copy this pattern and replace these A here with the pattern. Alright, save it. On my Windows XP machine, I have the application running, and sorry, I don't have the application running. Now I have the application running, and I will put a breakpoint at our jump ESP instructions, which is at this address. Okay, and now I'll run my POC against the target machine. Let's see what happens. So we have hit our breakpoint and application has paused. Now let's use the Mona library to find the MSF pattern for us. So I'll use Mona and find MSP. So this takes some time to give you the full output. Now if you just see here that it has identified a cyclic pattern at this memory address and the length of that pattern is 1000 bytes. So it looks like our pattern has made, or our MSF pattern has made to the application and it has been stored successfully. So let's check what is at this memory address. I'll just note down this memory address here and copy it. We'll go to the CPU window and go to this address, and I'll follow this in dump. So this looks like the pattern that we had sent the application, and it has been stored successfully. So we can use this command to place our shell code in the application memory. Now our next task is to generate the egg hunter code, which we'll do using again the Mona library of WinDbg. Mona egg, and I'll specify the tag YCSC, and it will give me a 32-byte shell code, and the only bad character here for us is a null byte, and it does not contain that character, so it's good for us. I'll copy this, and now what we'll do is we'll give this egg hunter code a test run by first removing this pattern, and I'll put YCSC here twice. If you recall from the first video of this module that our shell code has to be appended by the egg 2 times, so that is why I am using YCSC 2 times, and then I'll put, let's say, 1000 A's here, and in here in the evil string I'll put this egg, and it's 38, and instead of 38 what I'll do is I'll borrow around 20 bytes from here, and I'll give some buffer or some padding to my egg hunter shell code of not instruction, which is hex 90, and I am giving it 20, right? So on my Windows XP machine I have the vulnerable server running, and it is attached to the imminent debugger. What I'll do is I'll go to my jump PSP instruction, place a breakpoint here, and I'll fire this POC again. So we have hit a breakpoint, and just step into it, and we have taken the jump, and this is the egg hunter shell code that we had sent the application. So this will basically identify, or rather check, the application memory for the double occurrence of the tag that we had specified. So let's come to this egg hunter shell code. I'll put a breakpoint here, and now we have hit a breakpoint. I'll step into it one by one. So it is now scanning the application memory, and it is checking for the first occurrence of the tag, and if it is not finding any occurrence, it is just looping back to these instructions. So I'll move here, put a breakpoint here, and I'll remove it from here, and I'll play. So we have hit a breakpoint, and it is now comparing the string at EX with whatever is there in EDI. So EX stores our tag, and obviously this is not what we are looking for, so it will just loop back again. Yeah, so now what I'll do is I'll remove the breakpoint from here, and I'll put it on the second comparison, which will only happen once it has identified the first occurrence of our egg. I'll run it again. So looks like this time it has found the first occurrence of our egg, and let's follow the EDI in dump, and if you just move up, you'll see that this is the tag that we had sent the application, but since it's only one occurrence and there is no second occurrence of this tag, so it will loop back from here. Let's see if that happens, and yes. So I'll run it again, and again we have hit the breakpoint, and this time if you check the EDI register, let's follow this in dump, and this time we have this occurrence, and if I move back, so this time we have two occurrences of the tag or the egg, and it is followed by A's that we had sent the application with the first command. And if I'll just step into the egg hunter shell code, it will compare it, and it will find a second occurrence, and this time it will not jump back, and it will move on to the next instruction, which is jump EDI, and from there onwards the control will be given to our shell code. So this much is clear to us. Now all that is remaining is to generate the shell code, place it here, and enjoy the shell. I'll go back to my Kali machine. I'll probably open a new terminal window. and I'll generate the shell code, the command I showed you earlier. So our shell code has been generated. I'll just copy this, and it is of 368 bytes, and I'll paste it here, and I'll remove these A's, and I'll just put the buff variable here. And for our records, let's just copy this command which we use to generate the payload or the shell code and put it here. Next, I'll set up the multi-handler listener for a reverse metapreter shell. So I'll run msf console, and I'll use multi-handler, and then I'll set the payload to Windows metapreter reverse underscore TCP and show options. So this requires these three options, out of which two are already set for us. So I'll only have to specify the L host option. L host 192.168.43.28, and then I'll run it. Great. Save this, and I'll move back to my XP machine, restart the vulnerable server in Immunity Debugger, run it, and I'll put a breakpoint at the jump ESP instruction. This is done, and now I'll fire my POC again. So now let's go back to our Windows machine, and we have hit the breakpoint. I'll just step into it. We have hit a short jump. We receive some NOPs, and I'll put a breakpoint here. Come here, remove the breakpoint, and then I'll put a breakpoint on this instruction, which happens once a tag has been found. So this means that this code has found the first occurrence of a tag, and if I follow the EDI in dump, you'll see that we have hit this code again, wherein we have the first occurrence of the tag, and this is the only occurrence for now. And I'll run it again. Let's again follow dump, and this time it has found the first occurrence, and there is a second occurrence of this tag also. So it will not take this jump, rather it will move to jump EDI instruction. Let's see if that happens. Yes, it has, and now it has jumped to our shell code, and I'll just run this program now from here, and we should receive a shell here. Yeah, so here it says metapreter session 1 has opened for us from this target machine. We have a metapreter shell here. So we'll try to take the admin access, or rather first let's verify our target. I'll get the UID of the machine. So this is the username that I have on that Windows XP SP3 target machine. And if I run the command get system, it has given me the administrative access on that machine, or rather the NT authority access. Let's verify this using get UID. So I have NT authority system access. Let me drop into the shell, and I do ipconfig. So this was the IP address that we were targeting. So this verifies that we have actually received the shell back from the target machine. So it has been a very exciting exercise to discover a vulnerability in an application and come across a limited buffer, and then find out a way, despite a limited buffer, to get a shell back from that machine. And we learned the technique of egg hunters, which I think that you should be pretty hands-on by now. And if you need further help with any of the software that we are using in this module, or the techniques that we have used in this module, please check out these resources. These are excellent resources, and they will help you in getting started with these techniques and the software. So that was it for this module, and I'll see you in the next module. Hello, and welcome to module 4 of our exploit development basics series. This module is about ASLR bypass and stack pivoting techniques. So these are the few things or software that I'm assuming that you as a learner have a basic knowledge of. If you don't, or if you want to learn them from scratch, please check out the resources mentioned at the end of this video. This is our module structure. Our module is divided into 6 parts, that is introduction, fuzzing, POC creation, controlling the execution, bad character analysis, and finally cracking the shell. We are on the first part, that is introduction, wherein I give you a brief overview of the technique that we will be using in this video and the tools required for this module. Following are the tools required for this module. We'll need a virtualization software. You can use either VirtualBox or VMware. We'll need two virtual machines, a Linux box and a Windows box. For Linux, we'll be using Kali 2018.1 as a VM, and on that we'll need Python 2.7 and a text editor. You can use either Sublime Text or Notepad++. On Windows machine, we'll be using Windows Vista 32-bit as a VM, and we'll be using following software, that is FileFuzz for fuzzing, Immunity Debugger for debugging the application, Mono library for Immunity Debugger, and our target software will be Cool Player Plus Portable. And again, we'll need an editor on the Windows machine as well. You can use either Sublime Text or Notepad++, and we need Python 2.7 installed on this Windows machine. So allow me to give you a brief overview of what is ASLR, or Address Space Layout Randomization. It is a memory protection technique to avoid memory corruption exploits. It was developed by Microsoft and it has been implemented in Microsoft Windows operating systems, Windows Vista onwards. Basically, it randomizes the base address of memory segments such as the stack or the heap. As you can see from the example here, I have two screenshots from Immunity Debugger in which I am running Internet Explorer. So in the first instance, as you can see on the left here, the memory address starts from 770B0F and 48. And if you come on the screenshot on the right, it's again the running instance of IE Explorer. This I created after restarting Windows Vista. And here if you see this address 77DD0F08. So in both these screenshots, the second byte here is different. So in here it is 0B and in here it is DD. Now every time the operating system is started, this base address gets randomized. But there is a way to exploit it, which we'll cover in a while. Now, in order for an application to be ASLR enabled, it needs to be compiled with dynamic base option. Now, most operating system DLLs are ASLR enabled by default. Now, what are the techniques to bypass ASLR? There are a couple of techniques that can be used to bypass ASLR. First is using non-ASLR enabled libraries. So usually it happens that when an application is developed, the exe and the associated DLLs might not be compiled with the dynamic base option. In this case, while OS DLLs are ASLR enabled, the application binary and its associated DLLs are non-ASLR enabled libraries. Our second technique is partial byte overwrite. So if I go back to the slide here, in here we can do a overwrite of these two bytes, and we'll design an exploit in such a way that the application supplies the randomized bytes. So this is a technique that we'll cover in the later module. The third technique is brute forcing the address space, wherein you design your exploit in such a way that it tries to guess the randomized address. So it's more of a trial and error method, and it has a huge overhead in terms of size, and it might also lead to unstable exploits. There are a few more techniques to bypass ASLR, which we'll cover in one of our later modules. Another technique that we'll be learning in this module is stack pivoting. Now, stack pivoting basically means that you point the stack to an attacker control buffer space. Now, at times, there might be situations wherein you need your exploit to do certain operations on the stack. For this, we'll need the control of ESP, that is a stack pointer. Now, let's assume that this is an application stack, and this is the current ESP position, and this is our attacker on buffer space. Now we want to do certain operations here, but since our ESP is pointing at this address, we won't be able to do that. So in order for the attacker to do operations here, we will need to shift the ESP pointer to this space. That is what we do in stack pivoting. We change the stack position from this space to our attacker owned buffer space. We do certain operations and then we restore the ESP to its previous place. This sounds more complex than it actually is, and you'll see that in later videos of this module. So these are the few resources that you can use to learn more about the software or techniques that we are using in this module. Thank you for watching this video, and I'll see you in the next part. Hello and welcome to part 2 of our module 4, which is ASLR bypass plus stack pivoting. So these are just few tools or software that I'm assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. A small change I've made here is in the first part I said that we'll be using file fuzz to fuzz the application. However, instead of that, in this part we'll be using PeachFuzzer. This is our module structure and we are on part 2, that is fuzzing. Before I move on to fuzzing, I would like to describe the exploit development process flow in brief. So this process starts by identifying the vulnerability, which we do by a technique called fuzzing. We'll cover that in a minute. Once we have identified the vulnerability, we move on to create a POC or proof of concept to replicate the crash in the application. Now once our POC is set and the application has crashed, we move on to enhance a POC and take control of the execution flow of the application. Once we have that in place, we move on to identify the bad characters for our shellcode. So now these are the hex characters which might be treated differently by the application and hence they have the potential to break our buffer or completely change the meaning of the shellcode that we sent it. Finally, once we have identified the bad characters, we generate the shellcode. You can do this either using an automated tool like MSF Venom, or you can write your own custom shellcode also, and we integrate it into a POC. Then finally, we fire our POC against our target application and obtain the shell from the target machine. Now, what is fuzzing? Fuzzing is a method for discovering faults in software by providing it unexpected inputs and monitoring for exceptions or any unwanted behavior. Now, there are different types of fuzzers. There are mutation-based fuzzers in which you give the fuzzer a sample file and then it mutates the contents of that file and supplies that to the target application. Then there are generation-based fuzzers wherein you give a sample file or sample test case to the application and it generates further test cases based on the original sample test case. Now using fuzzing you can target different kind of entities or different kind of things. These are environment variables and arguments. You can also fuzz web application and servers. You can fuzz file formats. You can also fuzz network protocols, web browsers, and in-memory. In this part, our target is file format. To know more about fuzzing, you can check out the book mentioned below. It's a great book to get started with fuzzing and understanding the basic concepts of fuzzing. Our target software here is Microsoft Windows Vista 32-bit, and on that we are running Cool Player Plus Portable. So in this application, we'll be exploiting a stack-based buffer overflow vulnerability. It was discovered in 2009 and it was given a rating of 9.3 out of 10 by Mitra's CVE initiative. So this vulnerability gets triggered when the application is supplied a malformed M3U file. Now, M3U file is nothing but a text file with a list of songs in it. Now when we use Peach to fuzz our applications, we use something called as PeachPit. So PeachPit is a XML based file and it is used to provide a configuration to the PeachFuzzer. Now all of this information is needed for Peach to perform a fuzzing run. Now a PeachPit file contains the following 5 sections. First is general configuration. In this section you specify every include or import that your PeachPit file might require. You can also specify the Python path here. The second section is data modeling, wherein you define the file format structure, and this section is also responsible for generating the fuzzed data. The third section is state modeling, which basically defines a simple logic state which opens up the file, writes the data supplied by data modeling into a file, closes the file, and launches the target application. Now, agents and monitors is the section wherein you specify the command to be executed in order to launch the target application and what debuggers or what kind of monitors we will be attaching to that application. In the last section, which is the test configuration, you finally tie up all these sections and define a test run for each fuzzer to use. Now this will get more clear once we see an actual pit file. Now an advantage of using Peach over other file fuzzers is that it gives us high flexibility to define a file format structure. Now let's say if we are targeting an application which uses a rather complex file format structure such as zip, this will help us in defining the exact file structure or the file format that is required by that application. So let's move this to the lab. Now I have a PeachPit file here. I don't need the first section, that is general configuration, because I don't need anything to include or import, and I don't need to specify the Python path as it is at the default path which the Peach fuzzer knows. So I'm starting with the second section, which is a data model, wherein I define my file format structure. Now M3U file format is a relatively simple file format. All it contains is a text file containing a list of file names. So that is what we have here. We have specified a block which occurs a minimum of 1 time and a maximum of 1024 times. And in this block, we'll have file names. Now, as I said, a state model writes the data supplied by data model to a file, closes the file, and finally calls the target application. Now in agent section, we specify the command to launch target application, and we also attach debuggers or certain monitors to this application. So I'm using Windows debugger and a page heap monitor also for it. Then finally in test section, we tie up all these things and specify a single test for Peach to run. If I explain it in very simple terms, the first data will be generated here. It will be written to a file. Then that file will be opened in the target application and a debugger will be attached here. And all this will be triggered by the test section. And it will also log the results into the path or the directory that we have specified here. So now let's see how this actually works. So I have the Peach fuzzer here with me and I'm using Peach 3.1.124. Now what I'll do first is validate my PeachPit file, and this Peach fuzzer provides a Peach validator to do that. I'll open my M3 fuzzer file, and since there are no errors, so that means a file is valid, and you can also see the structure that we have defined here. Now I'll just go ahead and launch the Peach Fuzz Bang, that is the Peach fuzzer. Go to general section, browse and launch or load my M3 fuzzer file. Then I'll specify a template file here, which I have in the C directory. Here, Peach fuzz minset and test.m3u, and I'll specify the name of the file to be first as fuzzed.m3u. I'll specify the strategy as sequential, and I'll give it a log path of codeplayer.log. We'll do 25 iterations, and then I'll move on to the debugger tab and I'll specify the command to launch the application here. Now what I'll do is I'll copy this from my peach bit file, which is this is the command I will be using. Paste. All right. Now most of these configurations have been specified in the peach bit file as well, but the Fuzzbang also requires them to be mentioned in the GUI. And now with everything in place, I'll just start fuzzing. So you can see the application being launched, and it says that fault has been detected and logged. So I'll let this continue till 25 iterations and we'll see how many faults were detected and logged. Alright, so our test default has finished and it has performed 25 iterations, and out of those 25 iterations it has found 1, 2, 3, 4, 5, 6 faults, and it has logged them also. So now let's go to our log path, or where the peach fuzz has stored the logs, which is in this directory, and this is the log directory that has been created by the peach fuzz bank. You can verify it from the timestamp also, and go to faults. These are the two folders which peach fuzzer has created, and it has mentioned exploitable. So whatever faults are there within these two folders seem to be exploitable. Let's open this one, and I'll go to this 14, and if I open the stack trace file, let's see what we have here. So these are the DLLs that are used by the application, and in here we have the state of the registers when the crash happened. Now as you can see that EIP has been overwritten by this string. If you come down in this file, you can see that multiple memory addresses have been overwritten with this particular string. So this seems to be the string that was sent to the application. And if I move further down to the application, the last line reads exploitable and read access violation at the instruction pointer, that is EIP, and it could not read the address mentioned here. You can also check the explanation here, which says access violations at the instruction pointer are exploitable if not near null. So obviously we are not near null, so this seems to be exploitable according to peach fuzzer. Now in order to see what data was sent to the application when this crash was triggered, we open the state action output name .bin file with notepad++, and this was the string that was sent to the application which caused this crash. So now let's move to, let me open some other fault just to check. So I'll come here and launch the stack trace, and this time EIP is 41, yes. So we'll use this as a reference because this seems to be the character we can understand. So 41 is nothing but hex for capital A. So EIP has been overwritten with 41, 41, 41, 41, 41, and so are these memory addresses. And as I have shown you previously also, if you come down, it says that this vulnerability is exploitable and access violation has occurred at EIP. Now if I open this bin file in notepad++, so this is the string of A's that was sent to the application that triggered the crash, and if I select it and just look here, it says the length of the string is 1870. So that means that a string of length 1870 triggered this crash. Now in the next part, we'll create a POC or proof of concept based on the results we have from the fuzzer and try to replicate the crash in the application. So these are the few learning resources that you can use to learn more about the tools or techniques that we are using in this module. Thank you for watching this video, and I'll see you in the next part. Hello and welcome to part 3 of our ASLR bypass plus stack pivoting module. These are the few software or tools that I'm assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. This is our module structure. We are on part 3, that is POC creation. Our target software is Microsoft Windows Vista 32-bit as our target operating system, and on it we are running Cool Player Plus Portable, which is vulnerable to a stack-based buffer overflow vulnerability. This vulnerability is triggered when this Cool Player is supplied by a malformed N3U file. Now, this vulnerability was discovered in 2009 and it has been given a rating of 9.3 out of 10 by Mitra's CVE initiative. You can check more about the CVE in the link given below. Proof of concept is a simple program or a script to replicate the crash in the application using the results that we identified in the fuzzing part. It can be written in any language: C, C++, Python, Java. I will be using Python for this module, and this POC is further enhanced to create a working exploit. Let's move to the lab now. This is a very simple Python script which creates a file name called martinsongs.m3u and writes an evil string of 1870A's in that file and closes it. So in the last part we found out that if we send the cool player a string of length 1870, we can crash that application. So let's verify if our POC works or not. I'll first run this script and generate an M3U file. I'll now open Immunity Debugger and open Cool Player Plus in it. Run the application. It's open and I'll load the file which is on my desktop, Martin Songs, and open. So as you can see that our application has crashed. An access violation has triggered when executing 41414141, which is hex for capital A, and our application has paused. Now if you see the state of registers here, EX is complete 0 and so is ECX. EDX holds a part of our buffer, but it also stores the path of the file in the beginning. Now EBX also seems to store our buffer. Let's follow this in dump. Okay. So it seems like our buffer or the string that we sent to the application has made it through and it has been stored in EBX. ESP also seems to be storing our string. Let's follow this in dump. As you can see here that our string has also been stored in ESP, or at least a part of our string. However, observe that there is a null byte here in the string. If I go back and check the POC, we did not send this null byte. Somewhere during execution, the cool player, while processing our string, it introduced this null byte into our buffer space. Though we can still work with this buffer, but our task will become a bit easier if we use the EBX register where our buffer is stored in its entirety. Now since 1870 is appropriate length for our buffer and our shell code, I'm not going to try and see if our application can store a longer buffer. If required, we can do it in a later part. Now this vulnerability seems rather straightforward to exploit. However, in our next part, that is controlling the execution, we will face a challenge that will force us to employ some kind of trick to reach to our shell code. But that is for the next part. These are the few learning resources that you can use to learn more about the tools, software or techniques that we are using in this module. Thank you for watching this video and I'll see you in the next part. Hello, and welcome to part 4 of our ASLR bypass plus stack pivoting module. These are the few tools or software that I am assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we are on part 4, that is bad character analysis. Now I've made a slight change here. I made a switch between part 4 and part 5. Usually bad character analysis is part 5 of our module, but in this case I'm doing it a bit earlier because we need to know the bad characters before we do stack pivoting. A bad character analysis entails sending all hex bytes from hex 00 to hex FF as part of a buffer and see how these characters are dealt by the application after the crash has happened. And if any of these characters are treated differently by the application or their meaning is changed by the application, they are treated as bad characters for our shell code because then they would change the meaning of our shell code. Usually hex 00 is a bad character by default because it represents a null byte. So let's move to the lab and do a bad character analysis on cool player plus portable. I already have cool player plus portable attached to immunity debugger, and this is the POC that we created in the last part. Now in order to send all these hex bytes, we need to generate these hex bytes, or we need to get these hex bytes from somewhere. A quick way to obtain them is to use Mona library. We have a command Mona byte array, and it will generate an array of 256 bytes and it stores this in byte array.txt in the installation directory of immunity debugger. So I have it here open with me, and this is the byte array file. I'll just copy this and I'll go back to our POC, make a variable called byte array and paste it here, and I'll include this here, and this will become 1614. All right, so now I'll generate a new M3U file, and I'll go back to Immunity, switch to CPU window and run the application. I'll load my new M3U file here now, and our application has crashed. You can see an access violation here, and I'll just follow EBP in dump. So you can see the characters that we had sent to this application. We have characters from hex 00 to hex FF, and it does not appear that any of these characters have been mistreated by the application or their meaning have been changed. So in this case we do not have a bad character, but still for our shellcode we'll consider this null byte as a bad character because our shellcode won't work with a null byte in it. So as we saw that for this particular application we didn't have any bad characters really, still we'll consider null byte or hex 00 as a bad character, primarily because our shellcode might not work with a null byte in it. That's all for this part. These are the few learning resources you can use to learn more about the tools, software or techniques that we're using in this module. Thank you for watching this video, and I'll see you in the next part. Hello and welcome to part 5 of our ASLR bypass plus stack pivoting module. I've divided this part into two subparts. In the first part, I will be covering ASLR bypass technique, and in the second part, I will be covering stack pivoting technique. These are the few tools or software that I'm assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we are on part 5, that is controlling the execution. Usually our part 5 is bad character analysis, but for the purpose of this module, I switched these two parts. In the first part of our video 5, we'll grab the control of the execution flow of the application. To do that, we'll first identify the location of the character which overrides EIP register. We'll verify this location. We'll do this using MSF pattern create and MSF pattern offset tools. We'll then redirect the execution to EBP register because that holds the entire of our buffer. Now we have two options. We can either hardcode the EBP address, or we can find an accessible and reliable memory address which holds the pointer to jump EBP or call EBP instruction. Now there are two prerequisites for such a memory address. It should not be affected by DEP, that is data execution prevention, or ASLR, that is address space layout randomization, and it should not contain bad characters. Now, as we saw in the last part, for this application, there are essentially no bad characters. So this second prerequisite is already met, and if required, we'll do a jump forward. If you remember from our first video, in this module, we'll be using the technique of using non-ASLR enabled executable or DLLs to bypass ASLR. So let's move to the lab now. On my Kali machine, I'll first generate a pattern of 1870 bytes using MSF pattern underscore create, and I'll specify a length of 1870. I'll copy this string pattern and I'll go to my Vista machine and I'll remove this byte array. We don't need it anymore. And I'll replace the evil string with the pattern that we have just created. Save it, and I'll go back to my command line, generate the M3 file again. I'll move to my WinDbg where I have already attached it to Cool Player Plus Portable. I'll run the application and I'll load the M3 file now. This is my desktop, not in songs, and our EIP has been overwritten by this string. I'll just copy it to clipboard. Now I'll move back to my Kali machine and this time I'll use MSF pattern offset and I'm querying for the string that I have copied. I paste it here. So the exact match has been found at offset 230. So this means that the characters beyond 230, that is 231 to 234, are overwriting EIP. Let's verify this. To do that, I'll first restart Cool Player Plus in WinDbg and I'll move back to my POC. I'll remove this MSF pattern and once again I'll send it a string of A, this time first of 230 characters, and then I'll send it 4 B's. Now hex for capital B is 42 and in the remaining I'll send it 1636 C's. Right, I'll save it, go back to my terminal, generate the M3 file again. Now I'll run the Cool Player Plus again and reload the M3 file. So as you can see here that our EIP has been overwritten by 4 B's, that is 42, 42, 42, 42. So 42 is hex for capital B, as I said previously. And if I follow EBX in dump, so we have 230 A's here followed by 4 B's and remaining are C's. Now this creates a problem for us which I'll come to in a bit. Meanwhile, if you can identify it on your own, that would be great. So let's move to the next part, which is finding a reliable memory address that holds a pointer to jump EBP or call EBP instruction. To do that, I'll first restart my cool player plus portable, and I'll run the application. And now I'll use Mona library to find a jump to the register EBX. Alright, let's go to log window, and it has generated a total of 183 pointers. Now if you have a look at the results, you'll see that most of these instructions are found in cool player plus exe. So this is the file that we are running. So, and if you see here, you'll see that this exe is not enabled for ASLR. So we can use any of these memory addresses. It has also found a total of 183 pointers which it has written in jump.txt file. So let's check this file, and I'll just maximize it. So these are the DLLs that are being used by this application, and as you can see here that most of them are ASLR enabled except for this one, which is our cool player plus.exe executable. And most of these addresses or all of these addresses belong to this particular exe file. So that means we can use any of these addresses, and also note that these address start with hex 00, which is a null byte, which might have created a problem if our application might have treated null byte differently. But as we saw previously, that for this application null byte is not a bad character. So what I'll do is I'll go back to WinDbg and copy this address, and I'll put it in my POC. First I'll put it in comments for my reference, and next I'll put it here. Now I'll write it in the reverse format because the Intel processor uses little endian format. Alright, I'll save this POC, generate the M3 file again, and I'll switch to my CPU window. I already have the cool player plus running here. I'll load this file, go to desktop, and M3U. So something has happened, but I have forgot to put a breakpoint at that address. So what we'll do is we'll restart it again, run it, and from a POC let's copy this address, and I'll go back to my WinDbg. I'll go to this address, and I'll put a breakpoint here. Now I'll open the M3 file again. This time it should hit the breakpoint and it should stop at this instruction. Alright, so we have hit a breakpoint here, and as you can see that our registers hold the buffer that we have sent to this application. And if I follow the EBX in dump, I'll step into it. Yes, so we have landed to our buffer. Now if you closely examine this window here, we have 230 A's, and then there is this string. What is this string? Can you guess what is the string? So this is the memory address that we have written here. So that means if we are transferring the control here, somewhere EIP or somewhere the execution will come across this string and it will break our shell code. So we will have to jump from this part of our buffer to this part where we'll put rest of our shell code, because this space is sufficient enough to hold our shell code or the payload shell code. Now in order to do that jump, we have a couple of techniques, or we might not even need a jump if you have been through our egg hunter module. we can simply put a egg hunter code here and put the shell code here with that egg tag or with the egg twice, but we are not covering that technique here. We have done that in the previous module. Another technique we can use is to simply do a short jump. So if I go back to my Kali machine and I launch msf nasm underscore shell, msf nasm shell, and if I want to see the opcodes for jump dollar plus 120, so it's EB76. So let's try this jump. I'll come back to my Vista machine and I'll assemble the code here, which is, or rather I'll binary edit it. Binary edit, I'll put EB76. I don't want to keep the size right now, so EB76, and it will take a short jump to 120 bytes ahead. Let's see where that places us. So that again places us in the same part of the buffer which we wanted to skip. And if I just come here and follow this in dump, so yes, we have come a bit far, but that jump was not sufficient enough to skip the entire of this part. Probably what we'll have to do is take another leap of 120 bytes. Now if I do that, I'll have to again binary edit this to EB76. Alright, and now let's see where we land. So this time, if I follow this in dump, so this time we have landed in the second part of our buffer, skipping the memory address that we had placed here, and now we can successfully execute our shell code here. This was a very simple technique, but for the purpose of this module, we will not be using this technique. What we'll be doing is we'll rather take a more complicated way and do a long jump into the second portion of our buffer, and we'll do that using stack pivoting. Now you might be wondering that this is a very simple application to exploit, and why are we going to such a complicated way to exploit this? A simple answer to that is that the concept of stack pivoting is a bit complicated, and if I do it with a complicated application that might have certain bad character limitations, it would increase the complexity of entire thing to explain. So just to keep things simple, I've chosen this relatively very simple application to exploit, through which you can very easily learn how stack pivoting is done and why it is required. We'll learn that in the next part of this video. These are the few learning resources you can use to learn more about the tools, techniques, or software we are using in this module. Thank you for watching this video, and I'll see you in the next part. Hello and welcome to second part of the fifth video of ASLR bypass plus stack pivoting module. These are the few tools and software that I'm assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. This is our module structure, and we are on part 5, that is controlling the execution, and in this part we'll cover the technique of stack pivoting. In the last part, we redirected the execution flow to EBX register, and we also saw that if we do 2 short jumps, we can jump into the second part of our shell code or our buffer. But we will not be doing that, rather we'll be taking a long jump directly into the second part of our buffer, and for that we'll have to do a long jump of more than 200 bytes. So here is what we are going to do. We have our stack here, and our current ESP is at this position, and this is the buffer that we control. So we'll reposition the stack pointer to our buffer, carve out the long jump in the buffer space that we control, and then restore the stack pointer to its previous position. In order to do that, we make use of the following code. So we'll first save our stack pointer into the EAX register by using the move instruction, and then we'll go on and carving out the long jump But before we move on to this part, we first have to know what is the instruction that we are going to carve out. So let's move to my Kali machine and see what is the instruction that we'll have to carve out. I'll launch MSF Nazm shell, and here I'll specify jump dollar plus 299. So this basically means that I want to jump ahead 299 bytes from the current position. And the opcode for this is E926010000. I'll copy this for a reference. And let's move back to the slide to understand the code. So this is the code that will carve out that instruction in our buffer space. So first we are pushing EBX, that is the address of our buffer space, onto the stack. We are popping it into ESP. So essentially we are pointing the ESP register to our buffer space, and then we are adding 40 to the ESP register. Now remember that the stack grows downwards. So any of the carving that we'll do will lead to stack growing in this direction. And if we don't have a sufficient space, this might override the instructions that we have here. Hence, I'm adding 40 to the current ESP pointer so that the carving out will start at a place much below this code. And then I'm pushing ECX onto the stack. So at the time of a crash, the value stored in ECX is 0. So that will take care of the null bytes at the end of our opcode. And then I'm adding 126 to CX register and pushing it onto the stack. So that will push this part of opcode onto the stack. And then finally I'm adding E86A into CX, which will make the value of CX to 90EN, and then it will push 90EN to the stack, hence completing our opcode. And then we'll finally take this jump and then restore the stack to its previous value. So we'll do that by pushing EAX onto the stack and then popping that value into ESP. Let's move to our lab and see how all this works out. This is the POC that we created in the last part. So I'll first put the opcode for the jump instruction here, and I'll put jump dollar plus 299 for my reference. So this is the instruction that we need to carve out. Now in order to do stack pivoting, we'll need the opcode of these instructions. A quick way to get these opcodes is to go to the immediate debugger and run our application. I'll put a breakpoint on the call EBX instruction, and now I'll generate the M3 file again and I'll open it here. So we have hit the breakpoint at call EBX instruction. I'll step into it and we have landed into our buffer. So you can just go here and start assembling these instructions. So now if I want to move ESP into EAX, all I have to do is move, and this will give me the opcode here. In a similar fashion, I can go on and assemble all these instructions here, and I'll get these opcodes here. Then I can just simply copy it and go back to my POC and build a variable out of it. I've already done that here. So let's copy this variable and paste it here. And I'll replace A's with hex 90, which is the NOP instruction. And what I'll do is I'll just keep 10 NOPs here, and then I'll put my stack pivot variable, and I'll also put rest of the knobs here, hex 90. Now this is of 22 bytes and this is 10 bytes, so that makes it 32 bytes, a total of 32 bytes. So we'll have to specify 198 because if you remember, this space was of 230 bytes. Oh, sorry, 198. And we'll save it and go back to my debugger, restart the application. Okay, run it and place a breakpoint at our call ebx instruction, and I'll generate the POC again and go to my application and load the M3 file. So we have hit the breakpoint at call ebx instruction. I'll step into it, and this is a stack pivoting code. Now let's see if this works or not. So I'll just step into it and come here. Now we are at move ex esp instruction. So notice the value of ex, it's 0, and so is ecx, and esp is 001226f0. I'll step into it. Now the value of ex has become 001226f0, and now I'll push ebx, that is this value, onto the stack. So if you follow esp here now, follow in dump, you'll see that this is the same value that is contained in the ebx. Now we'll push this value, or rather we'll pop this value into esp. So now ebx and esp point to the same memory address, and now I'll add 40 to this address to give me sufficient space to carve out my long jump. And now I'll push the ECX register on the stack, and if you notice here that the ECX register has been pushed here, or the contents of ECX register have been pushed here, which were 00000000. Now I'll add 126 to ECX, so this becomes 0126. Now I'll push CX again to the stack, and now I have 26010000. Now I further add E86A to CX, and this will give me E990. And now if I further push CX onto the stack, it will give me this instruction finally, E926010000. So this is the same instruction that we saw on my Kali machine here. And if I just put a breakpoint here and come to this instruction, and now I'll step into it, and now we are into the second part of our buffer. I'll follow this in dump selection. So this is the second part of our buffer, and this was the memory address here that we placed, and this is the first part. Now in this part we first have to realign our stack to its previous value, or rather restore the ESP to its previous value. As we saw here, it can be done using these instructions, push EX and pop ESP. The opcode for it is 50 and 5C. So I'll go back to my POC. I'll put knob here, X90. Let's say we get a buffer of 200 bytes, and then I'll put X50, X5C here, and in the rest I'll put knobs to complete a buffer into 1436. I'll save it. Now I'll go back to the debugger, restart the application, run it, place a breakpoint at the call ebx instruction, and I'll go to my command line, generate the M3 file, and now I'll open this M3 file in the Cool Player Plus. So we have hit the breakpoint at call ebx instruction. Let's step into it, and this is our stack pivoting code. So let's just come here. Sorry, I'll put a breakpoint here, and now I'll step into my stack pivoting code, and a long jump has been carved out. So I'll put a breakpoint at this instruction. So now we have hit a breakpoint at a long jump, And now I'll step into this, and we have taken a long jump here. Let's follow this and down selection, and here is our 50 and 50C, that is the push and pop instructions. So I'll just come down here, and now I'll put a breakpoint here and run the application. We have hit our breakpoint, and now I'll step into these instructions. So they will essentially restore my ESP value. Now notice the current EX value and the ESP value. So we push EX on the stack and it increases the value of ESP, and then finally pop this value into ESP, and you can verify it from here. Now all that is left for us to do is to generate the shell code and place it in this part and obtain the shell back. That is something we'll do in the next part. Now I hope that the concept of stack pivoting is clear to you. I would highly recommend that you do this exercise on your own, build these instructions in immediate debugger, get these opcodes, and then create a POC of your own, and then with the help of the debugger, see how these instructions are working. These are the few learning resources that you can use to learn more about the tools or techniques or software that we are using in this module. Thank you for watching this video, and I'll see you in the next part. Welcome to part 6 of our ASLR bypass plus stack pivoting module. So these are the few tools or software that I'm assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. This is our module structure, and we are in the final part, that is part 6, cracking the shell. Now all that remains to be done with our POC is to integrate the payload shellcode in it and fire it against cool player plus portable. Now to generate our payload shellcode, we'll be using MSF Venom tool. Our payload is Windows Metapreter reverse TCP, and it takes two arguments, lhost with this IP address and lport with this port address, and we'll specify the bad character of null byte, and we need it in the form of Python. Once we get the shell code, we'll paste it in our POC, and then we'll go back to our Kali machine and set up a multi-handle listener on port 4444 to catch our reverse shell. Now let's move to the lab. So I'll now run this command to generate the payload shell code. As you can see that this is 368 bytes in size. I'll copy this and I'll move back to my Vista machine, and I'll paste it here. Save this, and I'll have to update my evil string. So first let me put another 100 knobs here, and then I'll put buf, and I'll save it now. Now I'll go to my terminal window and I'll generate a new M3U file. I'll open immediate debugger and I'll open cool player plus init, run the application. I'll set the breakpoint on the memory address of call ebx instruction, which is this. Come here and go to expression, this. I'll set a breakpoint, yes. And now I'll open the N3U file in the cool player plus. We have hit our breakpoint and we are at call ebx instruction. I'll step into it. And this is our stack pivoting code. I'll put a breakpoint here, run my application. Now we have carved out the long jump. I'll place another breakpoint here, run. Now we have again hit the breakpoint and I'll step into it. We have taken a long jump into the second part of our buffer. I'll just come down, and this is our stack restore or stack realigning code. Run to it, and we have again hit a breakpoint. I'll step into these two instructions. and our stack has been restored. Now I'll come further down and I'll put a breakpoint here, run it, and now we are at the beginning of our shell code. So now let's run it and see if we get a shell back or not. Oops, seems like we have got a access violation, and it does not know how to bypass the command at address this, which is this 8f command, and our application is paused. So somewhere something has caused a trouble for us, and to identify that, let's restart cool player plus. Okay, and I'll set the breakpoint again, and I'll load the M3 file. I've hit the breakpoint at call EBX instruction. I'll step into it, and this time what I'll do is I'll just move a bit further down and set a breakpoint at the beginning of a shellcode. So this is our shellcode, and I'll place a breakpoint here, run the application, and we are at this breakpoint. So before running the shellcode, let's just analyze our shellcode to see if everything is in place or not. Now if you just come here where we have these question marks, and if you see this instruction A1 B7 0D 0A E2, now this looks like something suspicious is going on here. So what I'll do is I'll just find this pattern in our POC of FE A1 and B7. I'll do a quick search. So here it is, and after that we have a 0A character and E2 character. But if I come back to my debugger, I'll see that after it we have a 0D. Now from where does this 0D character came in? Now this looks like something we have missed in our part 4, and it's very easy to miss this kind of thing. So I have a screenshot here from the part 4 of our module, wherein we did the bad character analysis, and if you see closely here, we have 00, 01 until 09 everything is fine, and if you look after 09 we have 0D and 0A. So looks like whenever the application encounters 0A characters, it prepends it with 0D. So this is obviously a bad character for our shellcode, as it has changed the meaning of our entire shellcode. So now we'll have to fix this. In order to do that, we'll have to generate a new payload shellcode using a bad character of hex 00 and hex 0A. So this is our new command. Let's go back to the lab again and restart it. And I'll put a breakpoint at call EBX instruction. So everything is set in here. Now I'll go back to my Kali machine and I'll generate a new payload. So I'll do hex 0A here. I'll copy this. This is again 368 bytes, and update it into our POC. So basically I just have to replace this part of code here. Right. Everything else remains as it is. I'll generate the new M3 file. But before running that file, I'll have to set up a multi-handler listener. So I'll go to Kali and open a new terminal, and I'll do msf console. Now I'll issue use multi-handler command and set the payload to Windows interpreter underscore TCP. Oops, looks like I have missed the payload option. And if I see options for this payload, sorry for that, electricity problems. Now as you can see the options here, it needs 3 options and 2 of them are already filled for us. So we'll only have to specify the lhost option. So I'll set lhost 192.168.43.28, which is the IP address of this machine, and now I'll run it. Now I'll go back to my Vista machine. I have everything in place here, and I'll load the M3 file. We have hit the breakpoint at call EBX instruction. I'll step into it, and I'll again go further down a bit to our shellcode and place a breakpoint there. So this is our shellcode, and I'll put a breakpoint here. So we have arrived at this breakpoint, and now more or less everything seems to be in order. I'll run this and let's see if we get a shell here. So it says Meterpreter session 1 has opened, and we do have our Meterpreter command line. So let's verify this by get UID. So this is the username I have on my Vista machine, and you can also drop into the shell or the command line shell of Windows Vista here by using the shell command in Meterpreter. And if I do a ipconfig, so this is the IP address that I have here, 126.159. Let's verify it here. Into my terminal. So 126.159. Now let's try to take system access here. I'll exit this Windows command line and go back to Meterpreter, and I'll issue the command get system. This time it has failed, and all 3 techniques that were available were unsuccessful. So not a problem. We'll probably have to do a certain kind of privilege escalation, or we'll have to find a privilege escalation exploit for our Vista machine here, but that is for some other day and some other module. If you want to play around more with Meterpreter, you can just issue a help command here, and it has some interesting commands which can let you do very cool stuff. So the screenshot commands seems interesting, and so is hash dump. So we can reboot the machine also, and we can shut it down. So let's try and shut down our Vista machine. I'll issue shut down. Says shutting down. Meterpreter session 1 has closed, and if we go to our Vista machine, it is shutting down. All right. So that was a lot of fun. So these are the few learning resources you can use to learn more about the tools, techniques, and the software that we were using in this module. Thank you for watching this video and this module. I hope that now you're pretty hands-on with exploit development process and with the techniques that we have shown in this or the previous modules. So keep checking this course regularly. I'm creating new modules on regular basis, and I'll update them in this course whenever they are ready. Hello and welcome to module 5 of our exploit development basics series. In this module, we'll cover how to write Unicode compatible exploits. So these are the few tools and software that I'm assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. So this is our module structure, and we're on the first part, that is introduction, wherein I give you a brief overview of the technique that we will be learning in this module. These are the tools required for this module. We'll be needing a virtualization software. You can use either VirtualBox or VMware. We will be needing 2 machines, one running Linux and one running Windows. I will be using these as a virtual machine, and for Linux I will be using Kali Linux 2018.1. On Kali Linux I have installed Python 2.7, Sublime Text or Notepad++, and I will also be needing Alpha 2 or Alpha 3 encoder. For Windows, I will be using Microsoft Windows 7 SP1 as a VM, and on this machine I will be running FileFuzz to fuzz our target application, Immunity Debugger, Mono library for Immunity Debugger, Trilogic Media Player 8, which is our target software, Sublime Text or Notepad++, and Python 2.7. The download link for these tools and software is mentioned in the description, so please check it out. So what is Unicode? Unicode is a standard for encoding computer text in most of the internationally used writing systems. In simple terms, it means that it is a standard to represent the character set of most of the written languages of the world. Now, a benefit of Unicode is that it is 4 bytes, that is 32 bits, and it can represent a large number of characters, whereas ASCII is 7 bits and it is somewhat limited in the number of characters it can represent. Many applications which have an international reach are now using Unicode 16 as their preferred character encoding standard. Now, why is it a limitation for us? Primarily because it converts a buffer into Unicode format before it is stored into a stack. What this means is that the application will transform each byte that we send as part of a shell code and convert it into a Unicode compatible format as shown here. So in the example here, a buffer of 41, 41, 41, 41 has been converted into 0041, 0041 and so on. So in this case, x00 has been prepended to each of these bytes and this changes the meaning of the original byte. Now, how do we work around or bypass this limitation? Now, in order to write a Unicode compliant exploit, we will first have to find a memory address that looks something like this. We'll only need to send it these 2 bytes and these will be converted into this memory address wherein 00 is prepended in front of both bytes. Then we'll need to find a Unicode compatible knob which essentially will help us in continuing our execution flow without affecting the state of the registers. And then we'll need to align the CPU register to the beginning of our shell code and we'll generate a shell code using MSFNM, but we'll encode it using Alpha 2 encoder to generate the Unicode compatible shell code. To read further about Unicode compliant exploits, please refer to the FAQ article mentioned in the link. If this all sounds a bit confusing, don't worry, we'll cover this technique step by step and things will get clear in further videos. So these are the few learning resources you can use to learn more about the tools and techniques that we are using in this module. Thank you for watching this video and I'll see you in the next part. Hello and welcome to part 2 of Unicode module. So these are the few tools or software that I'm assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. They will help you learn more about these tools or software, and if you want to learn from scratch, they will help you with that as well. So this is our module structure and we are on part 2, that is fuzzing. Now before I dive into fuzzing, I would like to explain the exploit development process flow in brief. Now this process has 6 steps and it starts with identifying the vulnerability. Now in order to identify a vulnerability in an application, we use a process called fuzzing wherein we send random data to the application and monitor how the application treats that data. If some of the data that we send to the application crashes the application, we then analyze the crash and see if it is exploitable or not. Now once we have successfully crashed the application and we have found an exploitable crash, we try to replicate the crash using a POC or a proof of concept script or a program. You can write this POC in any of the languages that you prefer. I'm using Python for this module. Now after that, we enhance a POC to take control of the execution flow of the application so that we can redirect the execution or the EIP register to the shellcode payload that we send to the application. Then we move on to identify the bad characters. So these are the bad characters or bad bytes that might be translated differently by the application. and if they are translated differently by the application, they might change the meaning of the shell code, hence completely breaking our shell code. Now, once we have identified the bad characters, we move on to generating the shell code. We do this using either a automated tool like MSF Venom, or if you have that kind of expertise, you can write a custom shell code also. Then finally, we integrate the shell code into a POC, fire this POC or exploit against the target application and obtain a shell from the target machine. Moving on to fuzzing. So fuzzing, as I said, is a method for discovering faults in a software by providing it unexpected input and monitoring for the exceptions. In simple terms, we use fuzzing to identify faults in the application that we can exploit. Now, there are different types of fuzzers, such as mutation-based fuzzers and generation-based fuzzers. Now, in mutation-based fuzzers, you provide a sample input to the fuzzer, and the fuzzer then mutates the content of that input and fires it against the target application, and then observes how the application treats that input. Now, in generation-based fuzzers, you provide a sample input to the fuzzer, and based on the input, the fuzzer generates further samples, which are then provided to the application, and the application behavior is monitored. So fuzzing can be used against a variety of targets. You can target environment variables and arguments. You can target web application and servers. You can target a file format. You can target network protocols, web browsers, and in-memory. An example of mutation-based fuzzer is speech fuzzer, and an example of generation-based fuzzer is spike, and another example is file fuzz. To learn more about fuzzing, you can refer to the book mentioned below. It's a great book and it will help you learn the basic concepts of fuzzing, and it will also help you in learning the basic concepts of tools that are used during fuzzing process. Now, this is the target software that we are using in this module. We are using Microsoft Windows 7 SP1 as a target machine, and on that we are running Triologic Media Player 8, which is vulnerable to a stack-based buffer overflow vulnerability, which can be triggered by providing it a M3U playlist file containing long strings. Now, this vulnerability was discovered in 2009 and it has been given a rating of 9.3, as it leads to complete compromise of the system and it can provide the admin access to the attacker. You can refer the link below to know more about this vulnerability. So let's move this to the lab. Now I'll first create a sample M3U file. So what I'll do is I'll open Sublime Text here. Now I'll just put 4 A's and save this as test.m3u on my desktop. Great. Now I'll open FileFuzz and I'll first generate the sample files. So what I'll do is I'll choose my test.m3u file from the desktop as a sample file or a reference file, and I'll specify the target directory. So I'll create a new directory on the desktop and I'll name it m3u fuzz, enter, and I'll have to create another directory inside it. This is due to an error in FileFuzz. If I mention only the first level directory, what it will do is it will create the sample files on the desktop itself. So that is why I have to specify this directory twice. And in here I'll match my 4 A's and I'll replace it with A into 100, A into 100, and I need 100 files. Create. So as you can see, 100 files have been written to the disk, and if I open this directory, you can see there are 101 items including this folder. Now let's move on to the execution part. I'll move on to the execute tab and I'll specify the path to Triologic Media Player 8, which is in my program files, and here it is, and try MP8, and I'll leave the argument as it is, and I'll specify first 10 files. Now I will have to make a small change here because at the time of creation it requires this, but at the time of execution it needs the first level directory to pick up the files. And I'll change this milliseconds to 15,000 seconds. So what it will do is it will give us an interval of 15 seconds between launching an application and terminating it. In this case we need 15 seconds because we will be manually opening the M3U file in Triologic Media Player 8 and then we'll be observing the crash. Unfortunately, the automated way of opening an M3U file is not supported with Triologic Media Player 8. So now I'll clear the log and I'll execute it. Okay, so I know why this error is because there are spaces in this path. So I will have to mention this in quotes and I'll clear the log again and I'll execute it again. So this time this has opened and we are on the desktop. I'll go through N3 first folder and I'll select the first file. There is no crash. Alright, and wait for the application to close and it has launched again. I'll go to my target directory. Now this time there is a crash here. Now let's try with another file and again we have received a crash. Now we have two crashes here. Let's analyze these crashes. So it says that the crash.exe, which is the debugger that comes with FileFuzz, and it has found a crash in m3ufuzz.1 or m3ufuzz1.m3u, and it has got an access violation and exception has been caught at 00410041, which has been translated into this instruction, and this is the state of our registers. So as you can see that EBP has been overwritten by our buffer and EAX is 0 and EBX has been set to FFFF and so on. Alright, this was the file that caused the application to crash. Now first what I'll do is I'll stop the execution of this application. I'll use kill all and this does not work, so I'll have to go to the task manager and I'll kill the file first process from here in process and I'll close this. I hope it will not run anymore. No. And so this is the file that triggered the first crash and it is of 404 bytes. Let's open it in Sublime Text and you can see that there are A's here, and if you see at the bottom there are 404 characters, so that means these are 404 A's that we sent to Triologic Media Player 8 and it triggered the buffer overflow vulnerability in the application. Now another file that triggered the crash was this file. I'll open this in Sublime Text, and this file also contains a string of A's, and if I select all you can see that there are 604 characters that have been selected. So that means any string which is of length greater than 400 seems to trigger the buffer overflow vulnerability in Trilogic Media Player 8. So that was all for this part. In the next part, we'll create a POC using the results that we have got in this part and try to replicate the crash in the application. These are the few learning resources you can use to learn more about the tools and techniques that we are using in this module. Thank you for watching this video and I'll see you in the next part. Hello and welcome to part 3 of the Unicode module. These are the few tools and software that I'm assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we are on part 3, that is POC creation. Now in the last part we saw that if we send the Triologic Media Player 8 a string of over 400 characters, it triggers the buffer overflow vulnerability in the application and the application crashes. In this part we'll use those results and create a proof of concept script or a program to replicate the crash. So this is our target software. We are using Microsoft Windows SP1, Windows 7 SP1 as our target machine. and on it we are running TryLogic Media Player 8, which is vulnerable to a stack-based buffer overflow vulnerability, and this is triggered by sending the application a M3U file containing long file names. This vulnerability was discovered in 2009 and it was given a rating of 9.3 by Mitra's CVE initiative. To read more about the vulnerability, please check out the link mentioned below. So a proof of concept is a simple script or a program that replicates the crash in the application. It can be written in any language. I will be using Python in this module, but you can use any language that you are comfortable with, be it Perl, Java, or C or C++. This POC is then further enhanced to create a working exploit out of it. So now let's move this to the lab. Here I have a very simple proof of concept script. So this declares a evil string of 404 characters and I'm sending 404 A's to it. Then it declares a file name called top40.m3u. Then it opens that file and writes this string to the file and closes the file. Now I'll generate this top40.m3u file using this script. So I'll go to my command terminal and I'll run python trylogic poc.py, and it is saved on the desktop in this video. So let's go to the desktop and see if the file has been created or not. So here is the file that was created. Let's open it and see what is there in it. So as expected, there is a string of capital A's, and if I select all and look at the bottom here, it says 404 characters selected. I'll close this and I'll run immunity debugger, and I'll open the TryLogic Media Player 8 in it. Let me maximize the CPU window and I'll run the application. Now I'll open the M3U file in it. Now an interesting thing with TryLogic Media Player is that when you open this file window and if you want to select a path from here, it will trigger another crash. Now to get past this, all you need to do is press Shift F9 and the application will continue to execute. And on my desktop, I'll select top 40 M3U. And we have an access violation when writing to this memory address, which is nothing but null bytes, and the application has paused. If you see here, the EIP has been overwritten with 4141, so our A's have been converted into Unicode compatible format, and X00 has been prepended to the byte 41. And if I jump to the ESP, so we can see that here is a buffer of A's that we send to the application, and this part of buffer has not been converted into Unicode format. And if I scroll up a bit, we'll see that this part has been converted into Unicode compatible format. Now why is that? I leave it to you as an exercise to figure it out. But for this module, we will not be exploiting a jump ESP based path. We'll be using the SEH override technique to exploit this application. So let's go to view and SEH chain and let's see if we have overwritten the SEH chain or not. So looks like we have not overwritten the SEH chain, and so I'll restart TryLogic Media Player 8 and I'll update my POC, which is here. I need to open it in Sublime Text, and this time let's increase the number of characters by 1000. So I'm sending it 1404 characters, and I'll generate the M3 file again and I'll run the application in immunity debugger. Now I'll open the M3 file again. Here is it, and again the same access violation has been triggered. Now just out of curiosity, let's follow ESP in dump and let's see what is the state of this register right now. So this time, as you can see, that these A's also have been converted into Unicode compatible format. And if I scroll up a bit, yeah, so even these A's are now in Unicode compatible format. And if I scroll down, so now all my A's have been converted into a Unicode compatible format. So now let's open the SEH chain and see if we have overwritten it or not. And looks like we have overwritten the SEH chain. So I'll go to my CPO window again and I'll pass the exception to the application using Shift F9. So this time also I have overwritten EIP with 4141, which is in the Unicode format, and our ECX register has also been overwritten with 4141. EAX is 0, EBX is 0, and if I follow ESP in dump, let's see what happens. So now it's a bit far away from our buffer. So anyways, this is not the route that we are taking for this exploit. Now what I'll do is I'll increase the length of the string that I'm sending to the application and again see what happens. So I'll restart the application and this time I'll increase it by 2000 characters. So this will become 3404 and I'll generate the M3 file again and I'll run the application in TriLogic Media Player 8. Sorry, I'll run the application in Unity Debugger. I'll open my M3 file and we have triggered our stack based buffer overflow, and let's see the SEH chain, and again this time we have overwritten the SEH with 0041 0041 and also 0041 0041. So looks like that we have found the correct length of the buffer that we need to send to the application to trigger an SEH override. In the next part, we further enhance our POC and take advantage of this SEH override. These are the few learning resources that you can use to learn more about the tools, software or techniques that we are using in this module. Thank you for watching this video and I'll see you in the next part. Hello and welcome to part 4 of the Unicode module. These are the few tools and software that I'm assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. This is a module structure and we are on part 4, that is controlling the execution. Now in the last part, we created a basic POC wherein we sent the application a string of 3404 characters and we triggered the buffer overflow vulnerability and we successfully overwrote the SEH pointers. So now I have divided this into two parts. In the first part, we'll be identifying the location of characters which override the SEH pointer and hence the EIP. We will verify the position of those characters and then we will redirect the execution flow of the application to that memory location. Now, in order to do that, we need to find an accessible, reliable, and a Unicode compatible address in memory that contains the instructions pop pop return. And then finally, we'll overwrite the SCH with this memory address so that when we pass the exception to the program and it goes to SCH, it will jump to the memory address that we have given it and hence it will execute the pop pop return instructions. In the second part, we will have to find a Unicode compatible knob and we will have to align a register to the beginning of a shell code. Covering both these processes in one video would make it a larger video. Hence, I have divided it into two parts so that it is easier for you as a learner to grab the concepts. So let's move this to the lab now. Now here I have the POC from the last part. Now what I'll do is I'll replace this string of 3404 A's with a pattern of string that I will generate using MSF pattern create. So I'll move to my Kali machine and I'll generate a pattern of 3404 characters. So I'll use MSF pattern underscore create and I'll specify a length of 3404. I'll now copy this pattern update our POC with it. For that, I'll have to remove this, paste it here. Yeah, I'll save it and I'll generate the new M3U file. Now I'll open the immediate debugger. Now this time you will have to run immediate debugger as an administrator because that would allow Mona library to write files in the program directory. And I'll open TryLogic Media Player 8 here. Say yes and run it. And now I'll open the M3U file. Great, we have an access violation and our application has paused. Now let me just pass this exception to the program using Shift F9. And as you can see that EIP has been overwritten with 0039 and 0072. Now we cannot use this string with MSF pattern offset. Let's see what happens if I do that. Specify a query of and I'll use offset. So it has not found any exact matches for this candidate. So an alternative to this is you can use the find MSP command of Mona library to find the Metasploit pattern. So I'll use Mona and find MSP. Now for some reason when you issue this command on TryLogic Media Player 8, it freezes the immediate debugger. But before it freezes, it has given the offset to us and it has found this Unicode pattern at offset 536 and it is followed by 2864 bytes of cyclic data after the handler. So we will need to verify this. What I'll do next is I'll have to close immediate debugger first and restart it, and I'll use end task. I'll close the program and I'll go to my POC and here I'll write the SEH offset for my record. This is 536 and here I'll change this to a into 536. Sorry, and I'll specify 2 bytes. Now usually we specify 4 bytes, but since this is a Unicode exploit, these will be appended by hex 00 and essentially these 2 bytes will be converted to 4 bytes. And here I'll write CC and here I'll just specify D into, let's say, 3000. Save it and I'll generate the new M3 file. I'll run the immediate debugger as administrator. Open TryLogic Media Player 8 in it. Yes. And I'll run the application. Open the M3 file. So we have triggered an access violation and our application is paused. So let's pass this exception to the program using Shift F9. And as you can see that it has overwritten EIP with 0043 and 004F. It seems that for some reason it has translated the last 43 to 4F. Let's try this with any other character. So I'll restart it. Run it and I'll update my POC. And this time I'll send it hex 90 and hex 90. I'll generate the M3 file again. Go back to immediate debugger application is already running. I'll open the M3 file and I'll pass the exception to the program, but before that let's see the SEH chain here. So we have 4242 here and we have 0090 here. So this should correctly reflect an EIP now. I'll pass this to the program, shift F9, and this time EIP has been overwritten with hex 0090 and hex 0090. Correct, great. Our next step is to find a reliable and Unicode compliant memory address which points to pop return instructions. To do that, I'll restart the application in immediate debugger. And I'll issue a command mona sh, and we need it to be compliant with Unicode. Let's see the log window. Now it has found a total of 0 pointers. I think that is because I have not run the application yet. Now let's again run this command. And I'll go back to the log window. And this time it has found 11 pointers. And if you closely observe here that few of them meet a requirement of having a null byte in the beginning of 2 bytes. So this seems to be compatible, and so is this, and so is this and this. So let's just use this address. I'll copy it to clipboard and I'll put it in my POC for the record, and I'll update my POC with it. I'll do F2 and 41. Save it. I'll generate the new N3 file, and now I'll have to put a breakpoint at this address. For that, I'll go to CPU window first and I'll go to expression this, and I'll put a breakpoint here. Now, since my application is already running, I'll just open this file. So we have triggered an access violation and our application has paused. I'll pass this exception to the program using shift F9, and we have hit our breakpoint, and as you can see that EIP has been overwritten with 0041 and 00F2, and this points to this instruction which is pop ASI followed by pop EBX and return. So I'll just step through it, and we have arrived at the buffer that we sent to the application. Now let's see what happens if I further step into the code. Okay, now it has got stuck here. So what I'll have to do is I'll have to find a Unicode compatible knob to be placed at this part so that it can skip this instructions and can finally come to this part of the shell code. And since it is a Unicode exploit, we cannot put short jump instructions here because they usually need 2 bytes and without any trailing or leading zeros in them. So now we have covered the first part, and in the next video we'll have a look at the second part, which is, as I said, finding the Unicode compatible knob and aligning a register to the beginning of a shell code. These are the few learning resources you can use to learn more about the tools, software and techniques that we're using in this module. Thank you for watching this video, and I'll see you in the next part. Hello and welcome to part 4 of the Unicode module. These are the few tools and software that I'm assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we are on controlling the execution. And as I said in the last part that I have divided this part into 2 subparts. So in the last part, we identified the location of the characters which overwrite SEH, and we verified the location, and we finally redirected the execution to the memory address which contained the instructions pop return. In the second part, we will have to find a Unicode compatible knob, and we need to align a register for a shell code. Now let's look into this in a bit more detailed way to understand why these are required. Speaking of a Unicode compatible knob, we'll need this so that it can absorb the trailing and leading zeros without affecting the execution flow. Now if I go back to my lab, now as you can see here that if we send 2 bytes to it, let's say 41 41, 1 byte is intact and the next byte absorbs the leading zero as well as trailing zero. Now if you can find such an instruction that can absorb both these bytes and does not affect our execution flow, that would be considered as a Unicode compatible knob. Now these are the few instructions that can be used as Unicode compatible knob. To learn more about these, you can refer to the link below, and we will be using 71 as a knob here. The second part in this process is to align a register to our shellcode. Now since we are using alpha2 encoder to encode a shellcode, and alpha2 encoder needs a CPU register to be specified while encoding the shellcode. So that is the reason why we need to align one of the CPU registers to our shellcode. Now there are two ways we can do this. First is we can identify a CPU register that is closest to our buffer and align it to the location of our buffer by adding or subtracting a certain value. The second way to do is that if the address that points to our buffer is on the stack, we can simply keep popping the instructions from the stack until we reach the memory address that points to our buffer, and then pop that memory address into one of the registers. In this module, we'll be using the first technique. These are the instructions that we will be using to align our register. Now, without going into specific, the general flow of these instructions is we will first push the instruction that is closest to our buffer onto the stack. We will pop that address into EAX, and then we'll collectively add 600 to the value stored in EAX, and then we'll push that value or push EAX on the stack, and we'll finally use return instruction to direct the execution flow to EAX. Now let's move to the lab now. Here I have the Triologic Media Player 8 running from the previous video. I'll restart it. Okay. And I'll run it. Now I'll go to the instruction or the memory address that contains pop-up return, and I'll put a breakpoint on it. And this is our POC. Now I'll update these B's to our knob instructions. So that would be hex 41 and hex 71, and I'll save it and generate the POC file again. I'll open this file. Now we have hit an access violation and our application has paused. I'll press Shift F9 to pass the exception to the program, and we have hit a breakpoint. I'll step into it, and we have come to a knob. Now let's see what happens if I step into this instructions. Cool. So now we have successfully landed into this part of our buffer, and our knob works as it should, and these instructions, that is the memory address that we specified that points to pop-up return instructions, also does not affect the execution flow. So that is a plus point for us. Now our next task is to align the register using the code that we saw previously. Now I have this code here. I'll copy it and I'll paste it in my POC, and I'll change this to 600. So this is just for comments, and in the code it's correct. So this will make it easier for us to understand what this code is doing, and I'll put this aligning part here and I'll save it. Now let me restart the try logic media player 8. Okay, and I'll run it. I'll go to this address and put a breakpoint here. Yes, generate the file again, and I'll open this file in Trialogic Media Player 8, and I'll pass the exception to the program using Shift F9. Now we have hit our breakpoint, and let's step into pop-up return instructions. We have arrived at our knob, and this is the aligning code that we have specified. So take a note of the value of EAX and EBX. The value stored in EBX is closest to our buffer, so we will be using EBX for this exploit. Now I'll just step into this code, and we have arrived at our aligning code. So we are pushing EBX onto stack. So you can see here that EBX has been pushed on stack, and we will be popping it into EAX. So this value is now into EAX. Now in it we'll add this. So the value of EAX has increased, and now we'll subtract from EAX. So now this value has been subtracted from EAX, and now it points into our buffer. So as you can see that this is the buffer that we had sent to the application, which stores these. And if I further step into it, I'll push the value of EAX onto stack, which is here, and I'll return the execution flow to this address. So now the EIP points to this address, so that means our execution flow has been transferred to this particular address. So our next task is to identify the difference from this address to this address and then provide that padding. So let's do that calculation. I'll open calculator, and I will subtract E12 E2C0 minus 1 2 E2 4D, and this comes out to be 73 in hex, and in decimal it is 115. So we'll have to provide it a padding of around 58 bytes. So let's update our POC, and I'll put 58F here, and I'll put 4 or 5 E's just to make sure or to identify that the EAX is pointing correctly. Now I'll restart this application in immediate debugger. Run it and put up breakpoint at our pop-up return instructions. Yes, and our file is saved. We'll now generate a new M3 file from this, and I'll open this file in Trialogic Media Player 8. Now we have hit an access violation, and I'll pass this exception to the program using Shift F9, and we have hit a breakpoint, and we are at the pop return instructions. So let's step into it, and we have come to our register aligning code. So let's step into it and see what happens. And if we see the location of EAX, it's pointing to the same memory address, but here it has one extra byte in it. So we'll have to reduce the value of the padding by 1 byte. So earlier we were providing it 58 bytes. Now we'll have to provide it 57 bytes. Save it. Restart Trialogic Media Player 8. Yes. Okay, and I'll run the application and I'll go to the memory address that points to pop-up return instruction and place a breakpoint here. Right, I'll generate the new file. Now I'll open this in the media player. 40, passing the exception to the program using Shift F9. We have hit a breakpoint and let's just step into it. This is a register line code and let's see what happens now. So this time our EAX register points to the correct location that we want it to point to. Now all we have to do is replace these E's with a shell code and obtain a shell from the target machine. A thing that you need to observe here is that even these calculations are converted into a Unicode compliant format. Now if we go back to the POC, we'll see that we had sent it 3 bytes 05, which is add EAX instruction, and the value 07 and 11, and this has been translated into 05, 00, 07, 00 and 11. So that means even 07 and 11 bytes and even byte 5 has been prepended by a null byte in this case. So we have done this calculation taking into the consideration this conversion into Unicode compatible format. So if you feel confused on from where these values came, just bear in mind that these values are also converted into Unicode compatible format, and hence we have taken that into account and manipulated our values in such a way that effectively we add 600 bytes to the value of EAX. These are the few learning resources you can use to learn more about the tools, software and techniques that we are using in this module. Thank you for watching this video and I'll see you in the next part. Hello and welcome to part 5 of Unicode module. These are the few tools and software that I'm assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we are on part 5, that is BAT character analysis. So in BAT character analysis, we send the application all hex characters from 00 to FF as part of our buffer and see how these characters are dealt by the application after the crash has happened. The purpose behind identifying the bad characters is that if these bytes or if certain bytes are translated differently by the application, they might break our shell code. So once we have identified these bad characters, we will eliminate these bytes or bad characters from our shellcode using an encoder. Now by default, hex 00 is considered as a bad character because it represents a null byte, and in this particular case only the bad characters in the range of hex 41, that is capital A, to hex 5A, that is capital Z, are of interest to us because we will be using alpha 2 encoder and generating a shellcode in uppercase characters. So let's move to the lab now. So here I have the POC created from the last part. I'll copy this array of bad characters and I'll paste it in my POC. And I already have the bad characters variable here. So I'll save it and generate a new file or a new M3 file, run immunity debugger, and I'll open TriLogic Media Player 8 in it. Okay, I'll run this. Let's put a breakpoint on the address of pop return instruction. Yes, and now we'll open the M3 file in the media player. So we have triggered the vulnerability I'll pass the exception to the application, and we have hit our breakpoint. I'll step into it, and now if I just scroll down, so our bad characters array or variable starts from here, and we can see that we have 01 to 09, and after that there are null bytes, and basically the rest of the buffer has been changed. So that means whatever byte was there after 09 is a bad character for us in this case. Now I'll restart the application first before going to my POC. Run it, and I'll put a breakpoint. Okay, now let's go back to our POC and see what character is there after hex 09. So there is hex 0a. We'll remove it, and I'll put it for my records here that hex 0a is a bad character. I'll save this, generate the new M3 file, and open it in Trilogic WinDbg 8. And we have hit a breakpoint. I'll step into it, and now if I scroll down, so you can see that this is the beginning of our bad characters array 01, and this time we have 0b 0c. Now as you can see here, after removing hex 0a, our buffer has been sent correctly to the application so far. Now if I step down further in the application, so till here everything is correct. Now let's go down further, and after 7f you have AC. So that means whatever byte was there after 7f has been translated differently by the application, and we need to remove that from our bad characters array. So let's restart the application, and I'll run it, and I'll put a breakpoint at pop return instruction. So basically the same process that we have been following. And now I'll go back to my POC, and after 7f we have hex 80. So hex 80 also seems to be the bad character for this application, hex 80. And I'll generate the M3 file again. I'll open it in the Trilogic player. Shift F9, and I'll step into it, and let's just scroll down. So here now we have received 81 correctly, but after that again our buffer has been mangled up by the application. So let's quickly restart it and follow the process again. Okay, run, and I'll set a breakpoint. Yes, go back to our POC and remove hex 82. Save it, and I'll put hex 82 here. Again save it, generate the new M3 file, go back to Trilogic player, open the M3 file, and let's see what happens now. Shift F9, and I'll step into this, and we have arrived at a buffer. Let's just scroll down, and looks like we've scrolled down a bit further. So this is 7f and this is 81. So even after removing the byte 82, rest of the buffer seems to be mangled. And now if I look a bit further down, you'll notice that bytes from A0 and further on are more or less correct, and they have not been mangled up. So that means that bytes in the range of 80 to 9f are somewhat troublesome. Now I leave this as an exercise to you to identify all the bad characters in this range. Now for our purposes, these bad characters, that is except null byte, are not relevant as we will be using only uppercase alphabet characters as our shell code. I would still recommend that you do this exercise and try to identify all the bad characters for this application so that you get well versed with this process. These are the few learning resources you can use to learn more about the tools, software and techniques that we're using in this module. Thank you for watching this video and I'll see you in the next part. Hello and welcome to part 6 of the Unicode module. These are the few tools and software that I'm assuming that you as a learner have a basic knowledge of. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we are on the last part, that is cracking the shell. So in this part, all that is remaining is to generate the shell code, encode it with alpha2 encoder and integrate it into our POC and fire that POC against the target application. And we'll also need to set up a multi-handler to catch the reverse shell that we'll get from the target machine. Now to generate the shell code, we'll be using MSF Venom and we'll be using Metapreter reverse TCP as our payload. And these are the parameters that I'll give it. And instead of Python, this time we'll need it in the raw format and we'll store it in a .raw file. We'll then encode this shell code using alpha2 encoder. We'll specify a CPU register that is aligned to our shell code. In this case, it is EAX, and we'll need a Unicode compatible shell code, and we'll need it in all uppercase characters. And then finally, we'll specify the shell code to it. Now, if you're having trouble to find alpha2 encoder, make sure to check the description of this video or the first video of this module. The download link for alpha2 encoder is mentioned there. Let's move this to the lab now. So on my Kali machine, I'll first generate the shell code in raw format and then I'll encode it using the alpha2 encoder. So this is the shell code that we'll finally send to the application. I'll copy it and I'll go back to my Windows 7 machine. I don't need this bad characters array anymore. Instead, I'll write a buffer variable to store our shellcode. And instead of bad characters, I'll specify this buf variable. And here I'll need to change the length to whatever the length of this buffer variable is. I'll need to subtract that from 3000. Now I need to do this to keep the value in EBX same as we have been working with. If I don't reduce this length, then the value in EBX will change and then we'll have to rewrite the aligning code to align EAX to the new memory address. I'm not showing that as part of this video. If you are interested or curious, you can just leave this 3000 as it is and give it a test run. I'll save this and before I move ahead, I'll start Metasploit and set up a multi-handler and use multi-handler and set payload to Windows underscore TCP and show options. Now it needs 3 options, 2 of which are already specified for us. I'll not change them. I'll only need to specify the lhost option, which is the IP address of this machine. So I'll set lhost to 192.168.43.28, which is the IP address of this machine, and I'll run it. Now let's go back to a target machine and generate this POC file. Now let's run emulator debugger. open Triology player in it. Okay, run it, and now I'll put a breakpoint on the memory address that contains pop return instructions. Now I'll open the M3U file in Triology player, and I'll go here, select this file. I've hit an access violation, and I'll pass this exception to the application. We have hit a breakpoint and we are at our pop return instructions. I'll step into it, and now we have come to our knob. I'll go ahead, and now we are at our register aligning shellcode. Note the value of EBX, which is same as we have seen in earlier parts, and I'll just step into this and align EX to the beginning of our shellcode, as you can see here, and finally redirect the execution flow to EX here. And now I'll run the application, and we should receive a shell on our tagging machine. So here you can see that Metapreter session 1 has opened, and we have our Metapreter command line. Now I'll use get UID, and this is the username on my Windows machine. I'll drop into the shell, and I'll also check the IP address. Sorry, config. So this is the IP address of the target machine that I'm using, and if I just scroll up a bit, you'll see that the Metapreter shell has been opened from this IP address. Now I'll exit the shell, and let's try to take system access of this machine. So all the techniques have failed. We'll have to probably use a privilege escalation exploit for that. That is something beyond the scope of this course. Now just go through the help menu of Metapreter and just play around. You'll find a lot of interesting commands in Metapreter. For example, now if I run the command screenshot, and it has saved a screenshot of my target machine to this file. So let's open this, and I go to home, and this was the screenshot that was mentioned in the terminal window, and you can see that this is the target machine that we are working with. I would recommend you to play around with Metasploit and get a hang of it. You can also try different sorts of payloads such as bind TCP shell or reverse TCP shell and see if they work with this application or not. So that was it for this module. These are the few learning resources you can use to learn more about the tools, software, and techniques that we were using in this module. Thank you for watching this video, and I hope this has been a good learning experience for you. If you have any questions, please ask them in the Q&A section, and I will be more than happy to answer them. Also, please leave a rating and a review for this course, as this would enable other students to find this course and get most out of it. Thank you once again, and I'll see you soon. Hello, and welcome to a new module of our Exploitation Basics course. In this module, we'll deal with writing exploits for scenarios where we have a limited buffer space. Now, I am working on few assumptions here that you have a prerequisite knowledge of following tools or software, and if you need to learn more about these things or tools, you can check out the resources mentioned at the end of this video. This is our module structure, and we are on the first part, that is introduction, wherein I give you a brief insight into the technique that we will be learning in this module and the tools that are required for this module. So beginning with tools required for this particular module, we'll need a virtualization software. You can use either VirtualBox or VMware, and we'll need two virtual machines, one Linux box and another Windows box. For Linux, I will be using Kali Linux 2018.1 as a VM, and on that I'll need Python 2.7.9 plus, and I'll need a text editor. You can use either Sublime Text or Notepad++ or any other text editor of your choice. And for fuzzing, we'll need BooFuzz on the Linux box. On the Windows box, I'll need a Windows 7 SP1 machine, and on this machine I'm going to install BooFuzz, which is a fuzzing application, and I'll need Emily Debugger, Mona library for Emily Debugger, and a target application for this software is vulnerableserver.exe, and we'll be needing a text editor. Again, you can use either Sublime Text or Notepad++ or any other text editor of your choice. And finally, we'll be needing Python 2.7.9+. Please note that for this module, any version of Python prior to this will not work with BooFuzz. So I recommend that if you have old versions of Python, please upgrade them to a version which is newer than Python 2.7.9. So let's say you find yourself in a situation wherein you manage to trigger a crash in an application, and you manage to get control of the execution, but you find that you have a very limited buffer space to work with. So how do you get out of that? How do you create more buffer space, or leverage that buffer space to achieve a working shell out of that exploit or out of that crash? Now here, by limited buffer space, I mean that the available buffer space for us is not more than 150 bytes. So 150 bytes, as you would have known by now, is not sufficient for either a TCP bind shell or a reverse shell payload. So we'll have to employ some kind of creativity to get to a shell using this buffer space, using the limited size of a buffer space. Now, possible techniques that we can use are: one is egg hunters, wherein you send the egg hunter code, which is usually 32 bytes, as part of your first payload that will be stored in this limited buffer space, and then using some other technique you manage to store a larger payload, let's say a reverse TCP shell, in some other memory region which is not directly accessible to you. But we have already seen this technique, so I'm not going to go into details of it. You can see our previous modules if you want to learn more about this technique. The technique that we will be using in this module is to reuse existing functions. So a lot of times, let's say for example in FTP functions, it happens that most of the functions that we need to run a bind shell or a reverse shell are already loaded as part of the binary. Now what we are going to do is we are going to reuse those functions. Instead of locating them in system, we will be reusing those functions and try to execute our payload. Now there are two types of exploits you can write, again depending on the buffer space that you have. First is a single stage exploit, wherein you require a buffer space of at least 122 bytes for it to run, and using the single stage you can send a reverse shell back to your attacking machine. The second technique, and the technique that we are going to learn in this module, is the multi-stage technique. In this technique, we first send a small payload to the application which executes a function call, and through this function we can then send a larger buffer or a larger payload to the application, which will then get executed and send a shell back to us. A major con of using these techniques is that they are highly OS dependent, as they use hard-coded function addresses. So you cannot develop a generic exploit using this technique. If you want to develop a generic exploit, you will have to find a larger buffer space, or you can use the previously mentioned egg hunter technique. Now, if it all sounds a bit complicated, do not worry. I will go into the detail of this technique in later videos, which will help you in developing a better understanding of this technique. So these are the few learning resources you can use to learn more about the tools or techniques that we are using in this particular module. Thank you, and I'll see you in the next video. Hello. and welcome to part 2 of our limited buffer space module. So I'm working on few assumptions here that you have a prerequisite knowledge of following software or tools. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we are on part 2, that is fuzzing. Now before I move ahead with fuzzing, I would like to give a brief overview of the exploit development process flow. Now, I know that I have covered this in all other previous modules and I am explaining it again and again so that you are more familiar with this process and this process gets etched in your memory. The exploit development process flow starts by identifying the vulnerability, and in order to identify a vulnerability, we use a process called fuzzing, wherein we send random data to the application and observe the application behavior for any anomalies. We then analyze these anomalies to identify if we can convert that particular anomaly or crash into a working exploit. Now, once we have identified such a crash or anomaly, we move on to the next step, that is replicating the crash, wherein we create a POC in a programming language. You can use any programming language of your choice for this. I will be using Python for this module. So we create a script in a programming language and replicate the crash in the application. Once we have replicated the crash successfully, we enhance our POC or proof of concept to take control of the execution flow of the application. Once we get code execution capabilities, it becomes very easy to send a payload to the application and get it executed. But before that, we need to identify certain bad characters. Now, these are the characters which the application might treat differently, and if they are in our final payload, they will completely change the meaning of our payload and hence our payload will not work. So it is very important to identify these bad characters. Then once we have identified the bad characters, we generate a shellcode using an automated tool like MSF Venom, or if you are comfortable in writing your own custom shellcode, you can do that as well. And then we finally integrate this shellcode in our POC, fire the POC against the target application and obtain a shell from this application. Now, as I said, that fuzzing is a process of discovering faults in an application or a software by providing unexpected input and then monitoring the application behavior for any exceptions or anomalies or crashes. These crashes are then analyzed to check if they can be converted into a workable exploit. Now there are two types of fuzzers. One are mutation based fuzzers and others are generation based fuzzers. Now using fuzzing, you can target various kind of things. You can target environment variables and arguments. You can fuzz web application and servers. You can also fuzz file formats, network protocols, web browsers, and in memory. Now for this module, I will be using BooFuzz fuzzing framework. This is a Python-based fuzzing framework and a successor to Sully fuzzing framework. Now some of its feature includes that it is easy and quick to generate data using BooFuzz, and the recording of test data is also much easier than other fuzzing frameworks, and it has an extensive online documentation. This is something that was missing with Sully framework, and it supports serial fuzzing, Ethernet and IP layer fuzzing, and UDP broadcasts. And as I said, that it has good capability to record test data which is consistent, thorough, and clear. To know more about BooFuzz, please visit the link below. Here you will find the documentation, the installation notes, and some examples on how to use BooFuzz fuzzing framework. Now, if you need help in installing BooFuzz framework, there is a bonus video included with this module. Please check it out. Now, BooFuzz fuzzing framework has two components. One is the framework itself, which runs on a attacking machine and it is used to fuzz the target application. And then there is process monitor, which runs on the target machine and it detects the crashes in the application and restart an application. Now the process monitor component is available on Windows only. If you check the GitHub page of BooFuzz, you'll see that there is a Unix version of process monitor also, but we will talk about that in some other module. So now let's move to the lab. So here I have a very simple BooFuzz fuzzing script. This is written in Python. So first we import buffers library or buffers framework, and then I defined a main method, and in that I first defined a file handler wherein buffers will be storing the results of fuzzing, and then I've specified a start command. So this command will be sent to the process monitor that will be running on our target machine to launch the application. This is the IP address of our target machine. Then we define a session wherein we define a target, and in target we define a target IP address, port, and the protocol type. In this case it is TCP, and if we are using process monitor, then we specify certain arguments for it. First is the process monitor client information that will be running on a target machine. So we need to specify the target machine IP address and the port on which the process monitor will be running. And in process monitor options, we specify the start command. And as I said that this command will be used to start and again restart the application on the target machine. Then we define a sleep time of 1 second, and we define a logger to record our test case data or fuzzing data. So I have specified two types of logger. One is the text-based logger and other is the CSV logger. So this will create a CSV file recording all the fuzzing test data that Bufuzz uses. Next, we define the protocol which Bufuzz will use to talk to our application, and in this case we will be using kstat command of vulnerable server. Now here static means that this string will not be fuzzed. Then we specify a delimiter, which is space in this case. And Bufuzz provides you an option to fuzz this also, but in our particular case we will not be fuzzing it, so hence I have specified fuzzable equal to false. Then we have specified a string, that is the string that we want to fuzz, and in this case I have just put test as a random value. Then again we have used the static function to define the carriage return and new line characters. We will not be fuzzing these. Then we finally connect this protocol to our session and call the fuzz method to start fuzzing. So now let's move to the target machine and start the process monitor. So I'll open the command window, and I have the Bufuzz framework stored in the documents directory, the tools. In here I'll specify the command python process underscore monitor.py, and I need to specify certain arguments to it. So first is the crash bin file wherein it will store all the crash data. Let's name it kstat underscore crash, and then I'll specify the logging level as 2, and I need to give it the name of the process that we are fuzzing. In our case it's vulnerable server, that is vulnerver.exe, and finally the port on which we want the process monitor to be bind to. So in our case it will be 26002, and then we run it. So process monitor is now running, and let's go back to the attacking machine and run the buffer script. I'll open a terminal window and I'll go to desktop, and here I have Python, and script name is kstat.py. Sorry, .py. If you see this message, it says that web interface can be found at localhost 26000. So let's check that out also. And before that, if I move on to my target machine, you'll see that it has launched vulnerable server and it is accepting the connections, and the debugger is also attached to it, and the application is being restarted again and again once it has been crashed. Let's check the web interface, and if you see here that it specifies the test case number and a crash synopsis, wherein it says that procmon or process monitor detected a crash on test case 2, wherein it found this to be invalid and it was unable to disassemble this particular value, and it caused access violation when attempting to read from this memory value. Now obviously it's 41, 41, 41, 41, which is X for capital A. Now if you want to see this crash in more detail, you just click on this particular crash or test case, and it will list down the entire synopsis of the crash that Buffers has recorded for us. So if you come down and see the context dump, you'll see the value of various registers, and you can see there that EIP has been overwritten with 41, 41, 41, 41. As I said, this is nothing but hex for capital A, and you can also see the string that was sent to the application, and this is what has caused the crash in this application. And if you see further down that it has closed the connection to the target application and it is sleeping for 1 second. And again, here is a context dump from the previous crash, and it is now restarting the process, and it is giving some time for the process to start and start accepting connection. So in total, the Buffers framework has identified 3 crashes, that on test case 2, 3 and 10. And if you want to check the strings that was sent as part of these test cases, you can just check here. And in this case, this is the string. And in this case, this is the string. So if you want to check out detail of any of these test cases, all you have to do is just click on it and the test case log will be shown. So in this case, we have identified that this command or this set of string when sent to vulnerable server using kstat command causes a crash. In the next video or in the next part, we will use the results from this fuzzing process to create a working proof of concept and replicate this crash in the application. So these are the few learning resources you can use to learn more about the tools, techniques or software that we are using in this module. Thank you for watching this video and I'll see you in the next part. Hello and welcome to part 3 of our limited buffer space module. I'm working here with an assumption that you have a prerequisite knowledge or basic knowledge of following tools and software. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we're on third part, that is POC creation. So our target software for this module is Microsoft Windows SP1 32-bit version, and on that we are running a vulnerable server, which is a software or a server designed to be vulnerable on purpose, and there are multiple commands that are vulnerable to buffer overflow, and there are different techniques to exploit this vulnerability in different commands. We will be exploiting kstat command for this module. So a proof of concept is a simple program to replicate the crash in the application that we found in the last part using fuzzing technique, and it can be written in any language of your choice, either Python, Perl, C, C++ or Java. I am using Python for this module, and this POC will be enhanced further to create an exploit. In the last part, we used boofuzz to fuzz vulnerable server and kstat command of vulnerable server to be specific, and we identified 3 crashes. In this part, we'll be using the results from that fuzzing process and creating a POC in Python. So let's move to the lab. So in the last part, if you remember, we stored the results of our fuzzing in a CSV file. Now if you see the script, you can see that we had defined a wellnessfuzz.csv file, and we have used a CSV logger to store our results in this file. So let's go to this file and see what is there. So it's here on my desktop, and I'll open it in LibreOffice. So as you can see that here this file stores the results of fuzzing, and if you see here, this is the first crash that the Buffers identified, and it has stored the results of that crash as well. So this was the command that was sent to the vulnerable server. So this is a pretty lengthy command, and if you see the result or the crash dump here, you can see that this was the string that triggered the crash in the application. Now obviously this is a pretty small string in comparison to what was sent to the server. This means that somewhere our buffer gets truncated and we cannot use characters more than these as part of our buffer. So this is one of the key insights that we could gain from our fuzzing results. So now I'll use this command, or rather I'll copy this string and I'll go to my POC. Now here I have a bare bones structure of the POC created. So first I'm importing socket module, then I'm creating a TCP socket and I'm connecting to my vulnerable server on this IP address and port. I'm receiving 1024 bytes of the server banner, that is the first text that the server sends on connection. Then I'm creating my evil string here and I'm sending this evil string as part of kstat command with the send function, and finally I'm closing the socket or the connection. Now I'll just paste the string that I copied from the CSV file and I'll save this file. On my Windows 7 machine I have vulnerable server already running. I'll start Immunity Debugger and I'll run it as an administrator. I'll attach it to vulnerable server. If I increase the size of this a bit, much better. And let's see where the vulnerable server is. Here it is. So I'm attaching Immunity Debugger to vulnerable server. And let's resume the application. Now I'll go back to my Kali machine and I'll run my POC. And let's see what happens. Did we crash the application? Yes, we did. So as you can see that we have triggered an access violation when executing 41 41 41 41, which is nothing but X for capital A, and EIP has been overwritten and EBP has also been overwritten. And if I follow EAX and dump, you can see that here is the buffer or the command that we had sent to vulnerable server, and it has been stored in the memory address that is pointed to by EAX register. So ESP also seems to be pointing to a part of a buffer. Let's follow this in dump. As you can see here that the number of bytes stored in this memory address are much less than the number of bytes that was stored in the memory address pointed to by EAX. So EAX seems to be pointing to our entire buffer, but because it's starting with kstat and with these symbols, we will not be able to jump to EAX directly and execute our code. You will have to jump to ESP and then take a short jump backwards. But that is something we'll cover in the next part. For now, let's see if we can increase our buffer size. So I'll restart Immunity Debugger, or rather vulnerable server in Immunity Debugger, and I'll go back to my Kali machine. Let's go back to the POC and let's see how many number of A's we have here. So we have 90 characters selected. So what I'll do is I'll just put A, and if I do it to 200, let's see if we are able to increase our buffer size. And I'll run the POC again. Let's go back to the Windows 7 machine, and this time again we have triggered the crash. And let's follow ESP dump. So again it is pointing to a part of our buffer, not the entire buffer. And if I follow EAX and dump, so again it is pointing to our entire buffer, but the size of the buffer doesn't seem to have changed much. Now let's try this exercise again and note this memory address. So I'll just copy it somewhere. Oops. So what I'll do is I'll go here and copy selection to clipboard and open notepad. and I'll restart a vulnerable server in Immunity Debugger again. Let's go back to the Kali machine and increase the number of A's, let's say by another 200, and fire the POC again. Go back to the Windows 7 machine, and that crash has been triggered. As you can see, EIP has been overwritten. And let's follow EX and num, and this time again the length of the buffer seems to be same. Let's verify this with the memory address that we had copied earlier. So it was 178F990. In this case it is 170F9F0. So this randomization might be because of address space layout randomization, and if required we'll deal with that in a later video. So now we have a working POC with us, and in the next video we'll enhance this POC to take the control of the execution flow of the application. Now if you want to learn more about the tools and techniques that we are using in this module, you can check out the resources mentioned here. These are excellent resources and they will help you in understanding the basics of exploit development and associated tools and techniques. Thank you for watching this video, and I'll see you in the next part. Hello and welcome to part 4 of our limited buffer space module. So these are the few assumptions that I'm working with. I am assuming that you have a prerequisite knowledge or at least a basic knowledge of following tools and software. If you do not, please check out the resources mentioned at the end of this video. This is our module structure and we are on part 4, that is controlling the execution. So in this part, we'll enhance our POC further and try to grab the control of the execution flow of the application. Now, in order to do this, we need to identify the offset at which the EIP register gets overwritten. Once we have identified that, we'll verify that location, and then we'll find out a way to jump to the ESP register, because as we saw earlier that the memory address that is stored in the ESP register points to part of our buffer. Now, in order to jump to our ESP register, we have a certain prerequisites. First is that the address that we choose for this instruction, it should not be affected by data execution prevention policy or address space layout randomization. Second is that it should not contain any bad characters. Now, we have not yet done bad character analysis, so we'll identify this address on a trial and error basis. Now there are two approaches we can do this. We can either hard code the ESP address, or we can find a reliable and accessible address in memory that contains an instruction or that points to the instruction such as jump ESP or call ESP. Now once we have figured this out, we'll integrate this memory address into our POC. Now since the ESP register points to a limited portion of our buffer, we need to jump back to the larger portion of the buffer. We'll do that using short jump instruction. Now in previous modules, we have used the MSF pattern create and MSF pattern offset utilities in Kali Linux. This time we'll make use of Mona library in Immunity Debugger to do all these tasks. So this is something new that you'll get to learn in this module. So let's move to the lab. So this is the POC from the last part, but as we saw in the last part that no matter how many characters we send to the vulnerable server, our buffer size does not increase. It stays at 90 bytes. So I'm going to go ahead and change this to 90 bytes. Now in order to find the offset at which EIP gets overwritten, we'll need a cyclic pattern or MSF pattern. In the previous modules, we have used MSF pattern utility for that, but this time we'll use Mona library. So I'll go back to my Windows 7 machine and I'll launch Immunity Debugger. And I'll start a vulnerable server in it. Let's run it. sorry, and now use the command exclamation mark Mona and PC, which is short for pattern create, and I'll specify the length as 90 bytes. As you can see that a cyclic pattern has been created for us and the length of this pattern is 90 bytes. I'll copy this to clipboard. And by the way, you can also find this pattern in pattern.txt file, which is in the root directory of WinDbg. And I'll go back to my Kali machine and update our POC with this pattern. I'll save it and come back to my terminal. And now I'll launch this POC. And let's see what we have got on a Windows 7 machine. So the application has crashed and you can verify it from here. EIP has been overwritten with certain characters, and as before EAX points to our buffer. So let's follow the EAX in dump. Alright, so this is the pattern that we had sent it. And now in order to find the offset at which EIP is overwritten, we'll use hash Mona and find MSP. So it will take some time to search, and once the search is finished, you can see that it has examined registers, SCH chain, stack, and it has written all this information into a file called find MSP. Now we are interested in the registers, so I'll check this section only, and it says that EIP contains normal pattern, which is the value with which the EIP was overwritten, and the offset for it is 66 bytes. So this means that the characters or the bytes after the 66 byte overwrite EIP. So let's verify it. I'll go back to my POC, and for the record I'll just put a comment here, and I'll say EIP offset is at 66, and now I'll remove this pattern. I'll put 66 A's and I'll put 4 B's, and to complete to 90 characters I'll put 20 C's, 20, and I'll save it. No, I don't want to purchase. And in my Windows 7 machine I'll restart the vulnerable server, run it, and go back to Kali machine, and let's fire the POC again. So now this time again our application has crashed. You can verify it from here, and one second, and EIP has been overwritten with 42 42 42 42, which is hex for capital A, and as usual EAX is overwritten with our entire buffer, as you can see, and ESP is also overwritten with a part of a buffer starting at C. So if you see, or if you drag this a bit upwards, you'll see that the ESP starts at C, and 4 bytes before that are the ones with which the EIP gets overwritten. So our next task is to find a reliable address in memory to jump to the ESP register. So to do that, we'll again use Mona library, and I'll use Mona jump -r ESP, and let's see the log window. So it has found a total of 9 pointers, and all of which are listed here. So you can copy any of these. So I'll choose this one and I'll copy it to clipboard, and I'll just need the message part. Back to my POC, put another comment with this line, and now I'll replace these 4 B's with this address, and I'll write it in the little endian format, which is the reverse format, hex df, hex 11, and hex 50, and hex 62. Alright, so So I'll copy this address because we need to set a breakpoint at this address now. Now, in order to verify that our control indeed gets a redirect to ESP, we need to fire that POC again. To do that, I'll restart vulnerable server, run it, and I'll go to this address and put a breakpoint here. On my Kali machine, I'll go to my terminal and run the POC again. Let's move back to the Windows 7 machine, and you can see that we have hit the breakpoint at this address and application has paused. So I'll just step into it, and we are at the beginning of our buffer, which was pointed to by ESP. So this is starting with C, and if you drag this a bit up, you'll see that this was the address that we had written, or rather overwritten EIP with. Now, in order to go back into this portion of the buffer, into these A's, we need to do a jump back of 70 bytes. Now I leave this as an exercise to you to figure out how did I arrive at this figure of 70 bytes. It's very simple and basic maths, so you should be able to do it. So let's just restart the vulnerable server. Let's again put a breakpoint at the memory address where we have stored jump ESP, and go back to a Kali machine. And now we need to find out the hex characters for a jump back, for a short jump back of 70 bytes. To do that, I'm using a utility called msf nasm shell. To launch that, you use msf nasm underscore shell, and here I specify jump $-70. Now this is the opcode for it, EBB8. So I'll copy it and I'll put another comment here, and now I'll add this short jump to our evil string. So this will be like hex EB and hex B8, and I'll have to reduce the number of C's by 2, which makes it to 18 bytes. I'll save it and I'll run the POC again. To do that, I'll first exit from here and now launch my POC again. Great. Let's move back to our Windows machine, and we have hit our breakpoint. Let's step into it, and we have arrived at a short jump. Let's take the short jump of 70 bytes backwards, and we have landed into a buffer of A's. And if you just drag this up, you'll see that we have landed at the beginning of A's. Perfect. So now our next task is to identify the bad characters before we proceed with our shell code. We'll cover this in the next part. So these are the few learning resources you can use to learn more about the tools and techniques that we are using in this module. Thank you for watching this video, and I'll see you in the next part. Hello and welcome to part 5 of the limited buffer space module. I'm working with few assumptions here. I'm assuming that you have a prerequisite or basic knowledge of following tools and software. If you do not, please check out the resources mentioned at the end of this video. So this is our module structure, and we are on part 5, that is bad character analysis. In bad character analysis, we identify certain hex characters which might be treated by the application differently. Now, these characters, if they are part of our payload shell code, might change the meaning of our shell code and hence render it completely useless. Now, in order to do this, we send all possible hex characters from hex 00 to hex FF as part of a buffer and see how these characters are treated by the application once the crash has occurred. Now, usually hex 00, which is a null byte, is considered bad characters in most of the cases because, as I said, that represents a null byte and it acts as a global terminator and it truncates our buffer. So any other characters that come after it usually get truncated. So let's start with the process of bad character analysis for kstat command of vulnerable server. Before we move ahead, I would like to mention that in this module we will be doing things little bit differently. So up until now we have been doing bad character analysis manually. This time we'll leverage Mola library to automate certain tasks for us. So this is another new thing or technique that you will be learning in this module. This is a Windows 7 machine we have been working with. I'll run Immunity Debugger as an administrator. Now I need to do this because when we use Mona library, it writes some file in the installation directory of Immunity Debugger. If Immunity Debugger does not has administrator rights, it won't be able to write files into the installation directory. And we need those files for bad character analysis, as you'll see in a bit. So now I'll start vulnerable server init and I'll run it. Now since our buffer can only contain 90 bytes, we will have to divide the byte array in 3 bytes of 90 bytes each. If you have been through the previous modules, you already know how to generate a 256 characters byte array using Mona library. You can also generate a 90 byte array using Mona library. To do that, I'll use this command !Mona byte array and cpb, and then I need to specify the characters that I need to exclude from my buffer. So this would be hex 5a to xff. So this has generated a 90 bytes byte array for me. You can see it here. It has also written this byte array into a file called bytearray.txt, and it has written the binary output of this byte array in bytearray.bin. We will be using this bytearray.bin for automating the comparison, which I'll show you in a bit. So let's just go to this file bytearray.txt. Files, immediate debugger, and I'll open byte array. Now I'll just copy this entire array and go back to my POC. I'll comment out the previous evil string. Let's create a new evil string with a byte array in it. Update the POC and I'll go to terminal and launch the POC. Let's see what happens with a vulnerable server. And go to the CPU window. So you can see that our application is still running and it has not crashed. Now this is probably because our buffer contains hex 00, which is a global terminator, and it is highly possible that it might have truncated the buffer that came after it. So essentially what application received from us is a buffer of 1 byte, and obviously it will not crash with that buffer. So let's try it again, and this time we'll remove hex 00 from our byte array and we'll increase it by 1 byte. So let's go to our Immunity Debugger installation folder, open this byte array.txt and copy this new byte array. And let's go to our POC and update this old byte array with the byte array that we have just generated. Let's save it and I'll launch, or rather fire, the POC again. Let's go to our Windows 7 machine and see what happened. So this time our application seems to have crashed. You can verify it from here, and it has paused. And if you follow EAX and dump, you can see the buffer that we had sent. Now in order to compare this buffer with the contents of bytearray.bin, we'll use Mona library, and there is a compare command in Mona library that we can use for this. So we'll use Mona compare, and we'll need to specify it a file which is byte array dot bin. Now, if you're using the default working directory for Mona library, you don't need to specify the complete path of this file. However, if you have changed the working directory of Mona library to a custom directory, you will need to specify the complete path to this file. And we need to specify an address to it. This is the address from where the buffer starts. So in our case, it is 0191F 99A. I'm not using 998 because 998 contains 3A and 999 contains 2F. So a buffer starts from 99A. So I'll specify this address here. This is 0191F99A. And I'll press enter to execute this command. Let's see the results of this comparison. So Mona has compared the contents of bytearray.bin, the content that was stored on this memory location, and it has found that the shellcode was normal and it was unmodified. So it confirms that this segment of the byte array does not contain any bad characters. Let's repeat this process again with the next segment. To generate that, we'll again use Mona byte array command. So by the way, if you're just wondering how we are able to generate a limited array, all we are doing is telling Mona that these are the bad characters for a byte array and we do not want to include them in the byte array. So this time I'll generate hex 00 till hex 5a. I will exclude these characters and I will also exclude characters from hex b5 to hex ff. So this will give us another byte array buffer of 90 bytes starting from hex 5b to hex b4. So let's go to the installation directory of WinDbg, open bytearray.txt and copy the new byte array. I'll go to my Kali machine and I'll update my POC with the new byte array that we had just generated. Save this, and I'll also need to restart vulnerable server. Run it, and I'll fire the POC again. Let's see what has happened. Application has crashed and it has paused. Let's follow EAX and dump. This is a buffer. Now in order to compare it, we'll again use Mona compare command, and this time we need to specify the address 0176FF99A. Now this address is changing because of address space layout randomization. So every time that we are running the application, this address or the base address is being changed. So 017 and 6F99A, and I'll press enter to run the command. Let's see what happened. So this time again Mona has compared the contents of bytearray.bin with the contents of stack at this memory location, and it has not found any bad characters. So even this segment of byte array did not contain any bad characters. Let's repeat this process for the last part or the last segment of byte array. To do that, this time I'll need to exclude characters from hex 00 to hex b4, and I need every other character apart from that. So this has generated a byte array of 75 bytes starting from v5 to hex ff. So now since we need a buffer of 90 bytes, we'll have to pad this with 15 NOP bytes. So let's go to the installation directory of WinDbg. Again open the byte array file, copy the new byte array and update our POC with it. And let's pad our evil string with 15 NOPs. Sorry. 215, save it, and I need to restart vulnerable server. And I'll fire the POC again. Let's see, our application has crashed. Let's follow EAX and dump, and this is the memory address, or rather 017df99a is the memory address that we need to use this time. So we again use Mona compare command to do this comparison for us, and we'll change the address. So this is 017df99a this time. We'll press enter to run the command, and let's see what happened. So again, Mona has not found any bad characters in the last segment of our byte array either. So that means that the only bad character in this case is x00, which is a null byte. So as we saw that the only bad character identified in this case is x00, and it is a null byte which also acts as a global terminator, and it truncates any characters that appear after it. This was the reason why our application didn't crash when the first time we sent it a byte array of 90 bytes. Now in the next part, we'll write the first stage of our multi-stage shellcode. These are the few learning resources you can use to learn more about the tools and techniques or software that we are using in this module. Thank you for watching this video, and I'll see you in the next part. Hello, and welcome to part 6 of our limited buffer space module. So I'm working on few assumptions here. I'm assuming that you have a basic or prerequisite knowledge of following tools and software. If you don't, please check out the resources mentioned at the end of this video. This is our module structure, and we are on part 6, that is cracking the shell. I've divided this video into 2 subparts, else it would have been a longer video. So now we have the control of the execution flow of the application, and we have also identified the bad characters. Now we need to figure out what first stage payload we should send to the application so that we can send a larger buffer to the application, which will result in a remote shell. Now in order to create the first stage payload, we need to first analyze the binary to identify if there is any reusable code or function, and if we find something, then we need to figure out a way to use this code or function. Let's move to the lab and analyze the binary. So this is a Windows 7 machine, and let me just quickly run emulate debugger, and I'll launch vulnerable server in it. I'll run it. Now let's just scroll through the assembly code here and see what kind of function calls are being made in this binary. An alternative way to do this is to go to view executable modules, and then you can select any of the executable modules to see the function calls. So I'll use vulnerable server, which is what was loaded earlier, and I'll search for all intermodule calls, and I'll just sort this out. So you can see that these are the functions that are being called by the application. So let's just walk through this list and identify if any of the function interests us. So we have the accept function, we have the bind function, and we have the listen function. If you want to see the definition of these functions, please check out the MSDN. Then we have send, and here tucked in between is the receive function. And this function seems interesting. Let's find out more about it. So here I have a snapshot of the definition of receive function from the MSDN, and as you can see that it states here the receive function receives data from a connected socket or a bound connectionless socket. So this means that a vulnerable server is using receive function to accept the input that we are sending to it. Let's have a look at the parameters. it needs a socket descriptor, it needs a pointer to the buffer where the input will be stored, the length of this buffer, and flags. So in our case, the flags will be null bytes, so we don't have to bother about it. If you want to read more about this function, please check out the link mentioned below. This seems to be an interesting function for a requirement through which we can send the second stage payload to the application. In order to call receive function from our shell code, we need to fulfill these requirements. First, we need to know the location at which the vulnerable server loads this receive function. Then we need to figure out the parameters that we want to send to this function. We'll need a socket descriptor. We can hardcode this or we can pick this up from memory. Now, since vulnerable server already has a socket established, there will be a socket descriptor that is available to us. We'll see that once we analyze the execution of vulnerable server. Then we'll need the location of the buffer, and we need the second stage of our shellcode to be placed right after the first stage shellcode so that we don't have to make any jumps to any other memory location. Third argument is the buffer length. So we need to specify a buffer length that is greater than 512 bytes, and flags will be set to 0, that is null. Then we need to align the stack to be positioned above our buffer, else any stack operations will interfere with the shellcode that we put in our buffer, and hence it will render our shellcode useless. And since, as you saw, that ASLR is enabled on Windows 7 SP1, we'll need to figure out a clever way to bypass it. So let's move back to our lab and figure out a way to meet all these requirements. To meet the first requirement of knowing the function location, I'll put a breakpoint on the receive function call, and I'll go back to my Kali machine and fire the POC again. So on my Kali machine, I'll run kstat poc.py, and here I've hit a breakpoint at this address, which is a call to the receive function. Now if I just right click and assemble it, I can see the location which is getting called. I can just copy this location and move to my POC, and let's just put another comment, and location of receive function is this. So this meets our first requirement of function location. Now we need to figure out what parameters are being sent to the receive function when it is being called. So I'll move back to the Windows 7 machine again, and if you see here down in the stack window, you'll see the parameters that are set up for this function call. So the socket descriptor is 5C and the buffer location is this. So we won't be using this buffer location. We will use a buffer location that is right after our first stage shellcode, and the buffer size is 1000. So this is 1000 in hex, which means 4096 bytes, and the value of flags is 0. Now we can either hard code this socket descriptor, or if you have a look here before above the function call, so this is where this function call is being set up and the arguments are being pushed to the stack. So let's just put a breakpoint here, and I'll restart vulnerable server, run it, and I'll run the POC again so that the breakpoint is hit. And now let's see how these arguments are set up on the stack before this receive function call. So I'll just step into these instructions. Now just take a note of this value which is stored at EAX, and then we'll again take a note of the value of EAX once we have moved past this instruction. So you can see that EAX has now become 5C, which is our socket descriptor. And if you see this instruction here, it is moving this value from a memory location on stack, which is EBP minus 420. So just let's make a note of this value and I'll launch calculator. I have hex here and the value of EBP is 0184 FF88 and minus 420 gives us 184 FB68. So now let's just scroll down to that location, 184 FB68. Alright, so you can see that 5C is stored here. So now let's just take a note of this address and I'll copy to clipboard. I'll move back to my POC and put another comment here. Location of socket descriptor is this. Alright. Now we will not hard code this address because as we saw that ASLR is enabled on Windows 7, but we'll figure out a way to reach to this memory address using the value of ESP. We'll come to that in a bit. Let's move to other arguments. So let's just step through it till we reach this call to receive function. And our next argument is the location of the buffer. To identify that, I'll first put a breakpoint at the jump ESP instruction, which will transfer our control to the memory address which is pointed to by ESP register, and I'll let the application run. Now we have hit this breakpoint. I'll step into it and we'll take a short jump back. So this is the location where our first stage shellcode would be, and let's just assume that it is 50 bytes in size. If it's less than that, we'll pad with knobs to make it 50 bytes. So let's see what is 99A plus 50 in hex. 99A plus 50 in hex is 9EA. So this lies somewhere here. Now if we use this location, the problem is that we'll have to bypass these instructions, else any of these instructions might interfere with our shellcode. In order to avoid that situation, let's just randomly select a location from any of these, and let's say I select 0184 F9D2. So 9D2 minus 99A is equal to 38 in hex or 56 in decimal. So we need a location which is 56 bytes further down from the beginning of our first stage payload shellcode, and that location is this. So let me just copy this to clipboard and I'll go back to my POC and I'll put another comment here. Location of buffer is this, and if we go back to our Windows 7 machine, let me just restart it so that we land back to the receive function call, and I'll run it. I'll run the POC again. So we'll hit our first breakpoint and just move on from it, and this is the breakpoint at call receive function. And if you see, the third argument is the buffer size, which is 1000 or 4096. So even if we do it to 512, we should be fine. So as I said that we will be using 512 bytes, which is 200 in hex. So 512 is in decimal is 200 in hex. So again, let me take a note of it in our POC and I'll put a comment here. Buffer length is 200 or 512 bytes, and our last argument is flags, which is 00. So let's see if we have met all the requirements. So we have figured out the function location, and we have figured out the parameters that are required for us, and we also need to align the stack to be positioned above our buffer. We'll do that once we write our assembly code, and a clever way to bypass ASLR. In order to meet this requirement, and if I move back to the lab, so instead of hard coding any of these addresses except for the function call, which is this address, because irrespective of OS, the receive function will be loaded by a vulnerable server.exe on the same address. So except for this address, we will not hard code any other address. We will make relative calculations based on ESP register. If it sounds a bit complicated, just bear with me for some time and things will get more clear once we come to the assembly code. So now with all the requirements figured out, let's see what the flow of events will look like. So we'll first align ECX with the location of our socket descriptor. We'll then align the stack to be positioned above our buffer, and then we'll push these 4 arguments on stack, and then load the function address in EAX, and finally call EAX to execute the function call. In order to save some time, I have already gone ahead and converted this flow of events in assembly code. As you can see here that we are first aligning ECX to the location of our socket descriptor. To do that, we are first pushing the value of ESP on stack and then popping that value into ECX. And then we add the required offset to ECX so that it holds the memory address at which the socket descriptor is stored. And then we come to aligning the stack, and to do that we subtract 50 from ESP. This will locate the ESP or the current stack pointer to a place which is above our shell code. Then we finally push the function arguments. We first XOR EBX register to make it 0, and we push EBX to stack. This is the first argument of flags. Then we XOR EDX and add 2 to it, and then we push EDX on stack. This is the buffer length, which is 200 in hex or 512 bytes in decimal. And then we add 42 to AL so that EAX points to the location of the buffer where we want our second stage payload to be stored. And then we push this value onto stack, and finally we push the value stored at the memory address pointed to by ECX, which is our socket descriptor, onto stack. Finally, we move the location of receive function into EAX. Now, since the function location has null byte in the beginning, and null byte is bad character for this particular application, so we cannot send null byte directly. So in order to make the last or the first 2 bytes of the address null, we shift this value to right by 8 bits, which will essentially make these 2 bytes as 00 and convert them into a null byte. Now finally we call EAX, which will result in the call to the receive function. On the right, I have this assembly code translated into shell code, and this comes out to be 34 bytes. So now let's integrate this shell code into a POC and see it in action. Now as you can see here that I've updated the POC with the first stage assembly and shell code, and I've put the assembly code in comments for a reference, and I've created a new variable called first stage in which I've placed the first stage shell code, and in the evil string I have replaced the first part of a buffer with first stage, which is 34 bytes in size, and for the remaining 32 bytes I have placed knobs. Rest is same as earlier. Now to see that our first stage actually works or not, we need to send a second stage shellcode to the application. To do that, I have created a second stage variable wherein for now I have stored 512 hex cc, which gets translated into breakpoint. And after sending our first stage shellcode as part of evil string, we sleep for 2 seconds and then send the second stage and finally close the connection. So now let's see this code in action. And on my Windows machine, I have already restarted vulnerable server. So I'll go to the location of jump ESP and place a breakpoint here and go back to my Kali machine, and I'll run this POC again. You can see that it waits here for 2 seconds, then closes the connection. So now it hits our first 2 breakpoints. Let's just remove them for now because we don't need these breakpoints anymore, and run the application. It has hit the breakpoint at jump ESP instruction. Let's step into it. It takes the short jump back to the first part of a buffer and lands at the first stage shellcode that we had sent. Now if you refer back to the slide, you'll see that this is where we align ECX. So let's step through these instructions and keep a watch at ECX. Now we push ESP on the stack, you can see here, and pop it into ECX. So value of ECX has changed and it is equal to ESP. And now we add 188 to CX to align it to the memory location at which our socket descriptor is stored. To verify it, right click and let's follow this address in dump, and you can see that 5C is stored here. Now the next part pushes these arguments onto stack. So we first XOR out EBX register, but before that we need to align the stack, and we have just did that by subtracting 50 from ESP. So now the stack points to F990 and our current location is F9A4. So this means that stack points to a location which is above our shell code. So any stack operations will now not interfere with our shell code. So now moving on to the next part, we first XOR out EBX register and push it on the stack. So this is the value of flags, and we then XOR out EDX register. So EDX is now 0, and add 2 to DH, which is the higher byte. So the value of EDX now becomes 200, and we push EDX to stack. This is a buffer length which is 200 in hex or 512 bytes in decimal. Then take a note of the EAX register. We add 42 to it. Now it is equal to the memory location which we had chosen to place our second stage shellcode. You can verify it from the POC comment. So I am on my POC right now, and as you can see here, we wanted to store the second stage payload starting from F9D2. Don't bother about this part because this keeps changing on application rerun. So EX is pointing to this memory location. Now we push this value onto stack, which is the location of a buffer, and finally we push the socket descriptor onto stack. So as you can see here that our stack is now completely aligned, or now stack is now completely ready with the arguments that we need to make a receive function call. In the next part, we move the memory location of receive function into EAX, and we shift EAX right by 8 bytes so that these values become 0. And as you can see here that immunity has translated this memory address to the location of receive function. Now let's just step over this call to EAX, that is called to receive function, and once we are out of this call, the remaining part of a buffer should be loaded in this region. So let's just step over it, and to do that I'll do this. And as you can see here that this entire region has been written, or rather overwritten, by the value of our second stage payload, which was CC in this case. Perfect. So I hope that this first stage payload and its working are clear to you. If not, I highly recommend that you do this on your own. You can refer to this video whenever you are confused. That way, you will be able to understand the execution and the working of this entire code in a much better way. Now, all that remains for us is to replace this second stage payload with a reverse TCP or bind TCP shellcode, which we'll do in the next part. These are the few learning resources you can use to learn more about the tools, techniques, or software that we are using in this module. Thank you for watching this video, and I'll see you in the next part. Hello, and welcome to part 6 of the limited buffer space module. So I'm working with few assumptions here. I'm assuming that you have a prerequisite or basic knowledge of following tools and software. If you don't, please check out the resources mentioned at the end of this video. Now, this is our module structure, and we are on part 6, that is cracking the shell. In the last part, we built our first stage payload and tested it. Now, all that remains for us to do is to generate our payload shellcode, integrate it into our POC, and run our POC against the target machine and receive a shell. To do that, we'll be using the following MSF venom command. We'll be using Metapredator reverse TCP as our payload, and we'll be specifying following options to it. The L host will be this IP address, which is the IP address of my Kali Linux machine, and we'll be listening on port 4444. Now, as we saw, that bad character in this case was hex 00, so we have specified a bad character here, and we need the output in form of Python, and we want to use the variable name which can be specified with -v as second stage. And we'll also launch MSF console and set up multi-handler to run on port 4444 or to listen on port 4444. So let's move to the lab now. So this is our POC from the last part, and this is the second stage variable that we need to update. So let's generate the payload shellcode using MSF Venom, and I have a terminal here, and I'll just issue it the command. It will take some time to generate the shellcode, and if you just scroll up, you'll see that the payload size is 368 bytes, which falls within the space that we have created for the second stage buffer. We have created a space of 512 bytes, so this is more than sufficient for our 368 bytes payload. So I'll just copy this and replace this second stage variable with this shellcode. Now that was the only change required in this POC. Now let's go ahead and set up a multi-handler listener on port 4444. To do that, I'll run MSF console, and now I'll use multi-handler, set the payload as Windows Metapredator reverse underscore TCP, and set the L host option to 192.168.1.10, and I'll set the L port to 4444, and I'll finally run it to start the listener. So now our reverse TCP handler is running on this port at this IP address. Great. So let's go to our Windows machine and prepare vulnerable server. So I have already loaded vulnerable server in WinDbg. All that I need to do is place a breakpoint at the jump ESP instruction. So I'll place a breakpoint here, And again I'm going back to my Kali machine, and let's fire the POC. So it will wait for 2 seconds and it's done, and we have hit our breakpoint. We are taking the short jump. We have landed on a first stage shellcode, and let's just step through it, and we'll step over the call EX, and as you can see that a second stage shellcode is here now. So now let's just run the application and let the shellcode do its job, and we'll move to the Kali machine, and here it says that Metapreter session 1 has opened from IP address 192.168.1.12, which is our target machine, and we have a Metapreter shell here. Now to confirm the target, I'll use sysinfo. So this is the name of a Windows 7 machine, and OS is Windows 7 Service Pack 1 32-bit version. Let's get the UID of the user logged in, and it says PT Lab machine, which is the username of the profile I am logged into in my Windows 7 machine. Let's drop down into the shell of the system, and IP config. So as you can see that this is the IP address of this machine, which was the same IP address we were using earlier. Now I'll exit this machine, and let's try get system to check if we can get admin access. We got system via technique 1. Now this was because we were running vulnerable server in WinDbg, which I had run as an administrator. Now had I run it as a normal user, we would not be able to leverage get system to get admin access to this machine. And if I now check get UID, we'll say NT authority system. Great. So we have the highest level of access on this machine using this exploit. Now you can go ahead and have fun with Metapreter. You can check out the help menu of Metapreter to get interesting commands. Just off my head, you can upload, download files, you can take screenshot, you can set up a keylogger, and you can do n number of things. So I leave that to you to have some fun with that. So with this, we have arrived at the end of this module. So I hope that you are now comfortable with the techniques that I have shown you in this module. I highly recommend that you do them on your own to get a complete understanding of how these exploits and how these techniques work. These are the few learning resources you can use to learn more about the tools, techniques, and software that we were using in this module. Thank you for going through this module, and I'll see you soon. Hello. In this video, we'll see how to install Boofers on Kali Linux 2018.1 and Windows 7 SP1. So let's just get right to it. So these are the installation requirements for installing Boofers. You need Python version 2.7.9 or higher on both Kali Linux 2018.1 and Windows 7 SP1. And you need PIP. PIP comes pre-installed with Python. You need PyDebug library for Python if you want to use the process monitor component of Boofers. We'll need this on Microsoft Windows, and we'll also need PyDasm for process monitor, and we'll need it on Microsoft Windows as well. Next, we'll need Visual C++ compiler for Python 2.7, and again this is on Windows. And as I said that we will be using Microsoft Windows 7 SP1 and Kali Linux 2018.1 as our base operating systems for this module. You can download these software or tools from the following links. If you don't want to search these links on Google, simply download this presentation as PDF, copy and paste the links in browser. So Python you can download from this link, and PIP, as I said, it comes pre-installed with Python, and you can download PyDebug and PyDasm from GitHub, and you can download Microsoft Visual C++ compiler for Python 2.7 from Microsoft website. You can also refer Boofers documentation, and it has all the steps required to install buffers. So if I just show it to you, so this is the buffers documentation, and the release version at the time of making this video is 0.1.4. And if you click on the installation here, you'll reach the chapter wherein it tells you how to install buffers. For detailed installation steps, you can refer to chapter 4, and it also tells you prerequisite installation steps, and if you want to install it from source, what you need to do. And again, if you need extras such as process monitor.py, what you need to do and install. All right, so now let's move to Kali Linux first and install buffers. I'm launching a terminal, and let's check Python version. So I already have Python 2.7.15 RC1, so I don't need to install Python in it. And to install buffers, all I need to do is pip install buffers. Now it will take some time depending on the connection speed. So as you can see that it is saying that requirement is already satisfied. That is because I have already installed buffers in Kali Linux. So that was all we need to do to install buffers in Kali Linux. Now let's move to Windows machine. So I have these tools already downloaded here. So I have Python 2.7.16 and VC for Python 2.7, and I have buffers master, LibDasm, which includes PyDasm, and PyDebug master. So our first step is to install Python 2.7.16. It's a simple installation procedure. So I already have it installed, so hence you are seeing the screen. And I'll now cancel it, finish. And similarly, you can just double click and install VC for Python 2.7. Now to install buffers master. So we will be installing buffers from source. To do that, I'll just right click this folder, shift right click and open command window here, and just let me check if I'm in the right directory. I am, and all I need to do is pip install. I need to give it pip install and dot for the installation from current directory. So buffers has been installed on the system, and as you can see that many requirements have already been satisfied. That is again because I have already installed buffers on Windows 7 SP1. Now next we'll move on to installing PyDbg or PyDebug. So if you go to the documentation and refer to the installation steps for installing PyDebug, it says that you need to use this command to install PyDebug from the source. So let's move to our Windows 7 machine and do it. So let's get out of this directory and let's move to PyDebug, and again we'll issue the command pip install dot. Okay, it's giving me an error. First let me clear the screen and let's see dir. So we need to go in a step further into this directory. So I'll do cd PyDebug, and now I'll give pip install. So now it has successfully installed PyDebug on my system. Great. Now let's install PyDasm. To do that, I'll change the directory to LibDasm, and okay, I need to get out of the PyDebug directory first. So now I am here, and if I do dir, seems like I'm in the correct directory now. And again, we are going to refer the buffers documentation on how to install PyDasm. So it says that you need to give these two commands to install PyDasm from the PyDasm directory. So let's just copy this. So you don't need these double asterisks. If you use these, the command won't run. So I'll go into PyDasm directory and I'll paste this command and run it. So it has run build extensions, and all now we need to do is set up and store. So it has successfully installed PyDasm as well. Now in order to check if everything went well, we can run process monitor. So I'll need to go to buffers directory for that, and I'll just run python process underscore monitor.py. So if you see this kind of output, that means process monitor has installed correctly. Alternatively, you can also check by giving this command python process underscore monitor.py, .py and hyphen help. And if you see the output like this, that means that everything has been set up successfully and your buffers installation was successful. Now, if you have installed Python for the first time, PIP might not run out of the box. You will have to update your path variable to include this folder in Python which has PIP in it. So you can see that PIP is located here, and we need to update this path in the environment variable. So to do that, you go to properties in my computer, advanced system settings, environment variables, double click on path and add the path to the scripts folder here. Okay, okay, okay. And next, when you start the command window or the terminal, you will be able to use PIP. So that was it for installing buffers. Thank you for watching this video. Hello and welcome to a new module of our hands-on exploit development advanced course. This module is named Acrobatics or Limited Character Set. These are the few assumptions that I'm working with. I'm assuming that you have a prerequisite or basic knowledge of following tools and software. If you don't, please check out the resources mentioned at the end of this video. This is our module structure, and we are on first part, that is introduction, wherein I give you a brief overview of what we will be covering in this module and what tools are required for this module. The tools required for this module are: we'll be needing a virtualization software. You can use either VirtualBox or VMware, and we will be needing two virtual machines, one Linux and one Windows. For Linux, I will be using Kali Linux 2018.1, and on Kali I will be using Python 2.7.9 plus and a text editor. I will be using Sublime Text, but you can use any text editor of your choice, whichever you're comfortable with. And we'll also need Alpha 2 encoder. For Windows, we will be using Microsoft Windows XP as a virtual machine, and on Windows XP we will be using Immunity Debugger and Mono library for Immunity Debugger. Our target software will be QuickZip 4.6, and again on Windows also we will be needing a text editor. You can use any text editor of your choice. I will be using Notepad++ in this case, and we will also be needing Python 2.7.9 or above. Let me give you a brief overview of what all we'll be covering in this acrobatics module. And we will be covering a lot of things, some previously learned techniques and some new techniques. And we will be doing a sort of acrobatics in most of the phases of our exploit development. So the first thing that we will be doing is fuzzing acrobatics, in which we will reverse zip file format and create a fuzzing script out of it, and then we'll use a combination of manual and automated fuzzing to fuzz quickzip.exe. Then we'll move on to creating our exploit or exploit acrobatics in this case. And we will be combining two techniques that we had previously learned. These techniques are SCH override and egg hunters. After that, and as you will see later, that we will be doing some crazy shellcode acrobatics. We will be taking a short jump, then a long jump. We will be carving out some code on the stack itself, and we'll also be doing stack pivoting and realignment. Then finally, we'll move on to encoding acrobatics, wherein we'll manually encode our egg hunter because of the limited character set of this application. And for our final shellcode, we'll be using automated alphanumeric encoding via alpha2 encoder. My advice to you would be to not get overwhelmed by all of this. We will be covering each of these things step by step and gradually, and I will be taking you through this module in a way that you can easily follow and understand what I am doing. So sit back, relax, and continue onwards to this module. And if you want to learn more about the tools and techniques that we are using, please check out the resources mentioned here. Thank you for watching this video, and I'll see you in the next part. Hello, and welcome to part 2 of our acrobatics module. These are the few assumptions that I'm working with. I'm assuming that you have a prerequisite or basic knowledge of following tools and software. If you don't, please check out the resources mentioned at the end of this video. This is our module structure, and we are on part 2, that is fuzzing. Now, before I move on to fuzzing, I would like to reiterate the exploit development process flow. As you know that this process is a 6-staged process, and the first stage is identifying the vulnerability, and we do that by fuzzing the target application. In fuzzing, we send random inputs to an application and see how the application behaves, and if it produces any crashes, then we see if we can exploit that crash to get a successful buffer overflow. The next step in this process is to replicate the crash that was identified by a fuzzing process. In this phase, we also create a proof of concept script. It can be written in any language of your choice. We will be using Python for this module. In the next stage, we further investigate this crash to see if we can gain the control of the execution flow of the application, and if we can, then we update our proof of concept script accordingly. In the fourth stage, we identify the bad characters for a particular application. The bad characters are those characters which, if they are present in our shell code, might change the meaning of our shell code or break our shell code altogether, and hence our payload will not get executed. So it is necessary to find these bad characters and eliminate them from our shell code. In the fifth stage, we finally generate the shell code. You can do this either manually or you can use a tool such as MSF Venom. And in the last step, we finally update a POC with the generated shell code, fire that POC against the target application, and obtain a shell from the machine. Now let me give you a brief bird's eye view of what fuzzing is all about. In fuzzing process, we send random inputs to the application in order to discover any faults and monitor for any exceptions or crashes that we can further exploit. There are two types of fuzzers, mutation-based fuzzers and generation-based fuzzers. In mutation-based fuzzers, you provide a sample to the fuzzing application. The fuzzing application then mutates the contents of that file and generates further test cases. In generation-based fuzzers, you again provide a sample to the fuzzing application. However, instead of mutating the contents of that particular file, it reads that file and generate new test files based on the original sample. Using fuzzing, you can target a variety of things. You can target environment variables and arguments. You can also target a web application and a server. You can target file formats, network protocols, web browsers, and in-memory. Now, if you want to learn more about fuzzing, do check out the book mentioned below, Fuzzing Brute Force Vulnerability Discovery. It's a great book to learn about the concept of fuzzing and whatever tools there are available and how to use them. In this module, we'll be fuzzing file format, and the file format that we have chosen for this module is zip file format. Our target software for this module is Microsoft Windows XP. That will be a target VM. and on Windows XP we will be running our target application, which is QuickZip 4.60. This version of QuickZip is vulnerable to a zip file containing long file names. This vulnerability was discovered in 2010 by Code and Coder. If you want to learn more about this vulnerability or want to read a detailed write-up, please check out the link mentioned below. Now I have divided this second part into three subparts. In the first part, we'll be discussing zip file format in detail. In the next part, we'll be correlating the zip file format with the zip file format structure used by a target application by reverse engineering a zip file that is created by the target application. In the last part, we'll create a fuzzing script by correlating zip file format and the zip file structure used by the target application. We will then use the script to generate further test zip files, and then finally we'll use FileFuzz to fuzz quickzip.exe for us. The same thing can be done via PeachFuzzer also, and I have created a Peach bit for fuzzing zip file formats, but I have not been able to get it working for this particular application, so that's still work in progress. And if I'm able to get it working, I will definitely share it with you. Now let's move our discussion to zip file format specification. Now as you can see in this diagram that a zip file is made up of following structure. A zip file is made up of four major sections. First is the file entry, which is also called local file header. A local file header is added for each of the files that is included in the zip file. It contains a specific format that we will discuss in a bit, followed by the data. Now, depending on the contents of the local file header for a file entry, there might be another section included after a file entry or the local file header for a particular file. This section is called data descriptor, and we'll talk about it in a minute. Once all local file headers have been included, a central directory record for each of these files is included. A central directory record is made up of certain bytes and has specific format, and we'll discuss it in a bit. For now, just note that the number of central directory records is equal to the number of files that is included in the zip. And then finally, at the end of the zip file, there is end of central directory record, which marks the end of a zip file. Now, when a zip tool reads a zip file, it starts with the end of central directory record, and then it goes on to read the central directory records for each of the files included in the zip file to get information about these files. Now, when you open a zip file and you see a list of files, that is usually generated from the central directory record. Zip tools usually don't prefer to walk through the entire zip file structure to get the file details. They usually check the central directory record and list the files. However, if you are using any tool that is working on recovering a corrupted zip file, it will go through the entire zip file and check for valid files in that particular zip file. Now let's dive a bit more into the depth of each of these file headers. We'll start with the local file header. As you can see here that the local file header is made up of 13 fields, and depending on the content of file name and extra field, the size of local file header is 30 plus n plus m bytes. Now each local file header starts with a local file header signature, which is 0403-4B50, and it is written in the little endian format. Now 50 is hex for capital P and 4B is hex for capital K, which stands for Phil Katz, who was the creator of zip file format. These 4 bytes are then followed by the version that is needed to extract the zip file, then 2 bytes of general purpose bit flag. Now note that whenever there are multi-byte fields in a zip file, these fields are written in the little endian format, which means that the most significant byte will be written last and the least significant byte will be written first. So keep that in mind, and that will come in handy in the next part when we reverse engineer the zip file created by our target application. After the version needed to extract, the local file header contains general purpose bit flags. Now there are 11 bit flags, and based on how these flags are set, this data descriptor header might be added to a zip file. Now here it says that if a bit at offset 3, which is this, of general purpose flags is set, then crc32, which is this field, and file sizes are not known when the header is written. So this means that if this bit is set, that means that the crc32 and the file size are not known at the time of creation of this header. These fields in the local header are then filled with 0, so the value of these fields here will be 0 and they will be included as part of the data descriptor field instead. Now again note that the data descriptor field has its own signature which starts with PK and then followed by 2 bytes, that is 07 and 08. Again keep that in mind and it will come handy in the next part. Then finally we have compression method, which is of 2 bytes, file last modification time again 2 bytes, file last modification date 2 bytes, crc32 4 bytes, then compressed size and uncompressed size of 4 bytes each. Then we have the file name length, which specifies the length of this field, and again it's 2 bytes. And if the zip file uses any extra fields, which are mostly used to specify encryption information, their length is included here in the extra field length field. And then we finally have the file name and the extra field that we specified here. The next file header in the zip file format specification is the central directory file header, and as we saw 2 slides back that it is written after all local file headers have been written, and it is basically an extended form of the local file header, and it is written for every file entry that is included in the zip file. As you can see here that it is made up of 20 fields, and depending on the file name, extra field and file comment, the size of this header is 46 plus n plus m plus k bytes. Again, note that any central directory file header starts with a unique signature of its own, which is pk and then followed by 2 bytes 01 and 02. And then again, most of this information is what was included in the local file header itself. However, it does contain some extra fields. As you can see below, there are fields such as file comment length, disk number where file starts, internal file attributes, external file attributes, and relative offset of a local file header, and then the respective fields. So these are the few extra fields that are added in central file header. Now the main purpose of including a central file header record in a zip file is to save time when a zip tool is reading a zip file. Now for example, let's say when a zip tool reads a zip file, and if it has to go through all the files one by one in that particular zip file, it will take a lot of time to open up that zip file. So instead it uses the central directory file header record for each of the file to know what files are included in the zip file and then display them to the user. The last section in a zip file format is end of central directory record, which as the name suggests, it marks the end of the central directory records, and it also marks the end of a zip file. Now this section is made up of 9 fields, and depending on the size of the comment length, the size of this section is 22 plus n bytes. Again, note that this section is marked by a special signature, which is pk, and then it is followed by 2 bytes, which are 05 and 06. And then there are fields such as number of disk, number of this disk, disk where central directory starts, number of central directory records on the disk, total number of central directory records, size of central directory in bytes. So this is a cumulative size of all the central directory records in this file, and then offset where the central directory records start related to the start of the archive, the comment length, and finally the comment. Now I know that I have not gone into the details of each of these fields and what purpose do they serve, and I've purposely left that out from these videos to keep us on track of what we are doing. However, if you want to learn more about each of these fields and what purpose do they serve in a zip file, do check out the Wikipedia page of zip file format structure. All this information that I've shown you here and explained to you is taken from this page only. So that was all for this part. In the next part, we'll correlate the zip file structure used by the target application with the zip file format specification that we have just seen. These are the few learning resources that you can use to learn more about the tools and techniques that we're using in this module. Thank you for watching this video, and I'll see you in the next part. Hello and welcome to part 2 of the acrobatics module. I'm working with few assumptions here. I'm assuming that you have a prerequisite or basic knowledge of foreign tools and software. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we are on part 2, that is fuzzing. In the last video, we went through the zip file format specification in detail. In this video, we'll reverse the zip file format structure used by our target application and then correlate it with the zip file format specification that we saw in the last video. So let's move to the lab now. This is my Windows XP machine and on it I already have QuickZip 4.6 installed, and for this video we will also need a hex editor. I am using HXD. You can find the download link for this tool in the download links document, which is part of the first video of this module. So the first thing that we are going to do is create a zip file using QuickZip. To do that, I'll open QuickZip, press new, and I'll go to my desktop, and here I'll create a file called test.zip and open, and then I'll navigate to my desktop again, and here I'll add this file text.txt in this zip file. Before I confirm this action, I will modify a few options. To do that, I'll go to add options tab and I'll uncheck save folder info and add subdirectory. If I keep these two checked, it will add directory information as part of the file name field, which we don't want at this stage. And then finally I'll press add. And as you can see here that this zip file has been created. So I'll close this window now. The next thing I'm going to do is open this zip file in this hex editor HXD. So to do that, I'll first open this tool and I'll go to file, open, and on the desktop I'll select the test.zip file and I'll press open. So now I can see the hex representation or the byte representation in hex format for this file. Next, I'll open the zip file format specification that we saw in the last part. Now I have copied that specification into an Excel file, which is here. I'll open this. Let me just maximize it. And as you can see that this is the same zip file format specification that we saw in the last part in the presentation. So let me just tile these two windows horizontally. First, I'll need to restore it. And then I'll go to the taskbar, press Ctrl and right click, and I'll select tile windows horizontally. Great. So now we have the zip file format structure of our target application in this window, which is the HXD tool, and the zip file format specification in form of an Excel file in this window. Now let's start correlating this zip file format structure with this zip file format specification. The way we are going to do this is based on the fields here. We'll copy the value from here and paste it here, and at the same time we'll also mark whether this field is static or dynamic. Now by static I mean that this field will not change during our fuzzing process, and dynamic means that this field might change during our fuzzing process based on the values of other fields. So things will get a bit more clear in a bit. Be patient and follow along with me. So the first field that we have here in the local file header says that it needs a signature, and the signature should be 504B0304. So now if we move to the zip file structure and we see the first 4 bytes, we see that it indeed has 504B03 and 04 as the first 4 bytes of its structure. So we'll copy this and paste it here. Now we'll want to paste it in the little endian format. However, as you see that this is not written in the little endian format as shown here. A quick trick to do that is to check this box which says show integers in hexadecimal base, and here it will show the value of integers in hexadecimal form. So now if I select these 4 bytes, you can see that they are now represented in the little endian format, or as this tool says, the integer is now represented in the hexadecimal base. So I'll copy it from here and I'll double click on this field and paste the value here. Just add 0, and so that it becomes easy while creating a fuzzing script, I'll just put /x to make it into a Python format hex byte. And so this is done. Now we'll need to know that if this field is static or dynamic. Since this is a signature and it is required by every zip file and it stays same across all zip files, so this will be a static field. So let's mark this with green. To do that, I'll go to this icon and I'll just select this. Next we have is the minimum version needed to extract this zip file, and it is of 2 bytes. So the next 2 bytes after this are 0A and 00. Now unfortunately the little endian format values are not available for this value, so we'll just have to write this manually. So let's write /x00 and /x0a. And again this is going to be a static field because this value will remain same across all zip files. To mark it as static field, I'll just go to this icon and select the green color. Moving on to the next field, which is journal purpose bit flag, and it is of 2 bytes and is at offset 6. So these are the 2 bytes which represent journal purpose bit flag, and as you can see that QuickZip has not set these bytes, so we will also not set these bytes, and let's consider this field as static for fuzzing purposes. So I'll put hex 00 and hex 00 here, and I'll mark this field as static. Let me just copy and paste it here. Next is compression method, and it is of 2 bytes and offset is at 8th byte. So these are the 2 bytes that represent compression method, and again these are written as 00 by quickzip.exe. So we'll keep it this way and not touch it. So let's just copy this value and paste it here as well. So next 2 fields are file last modification time and date, and each of these is represented by 2 bytes, and file last modification time starts at 10th byte and file last modification date starts at 12th byte. So let's see what do we have at 10th byte. We have the value of 6E and 3F. So we'll just copy this value from here and paste it here, and let's just convert it into a Python hex byte value format. Now we can choose to keep this field as dynamic or static because the time of your file creation might change, but for the purpose of this module I'm going to consider this field as static, and any zip file that we generate from a fuzzing script will have the same date and timestamp. So let me just go here and copy this. So we have marked this field as static also, and now let's look at file last modification date, which is at 12th byte, that is 0C, and in here we have C3 4E. So let's copy 4EC3 from here in the little endian format and paste it here. Let's convert it into Python hex format by adding backward slash and X in the beginning of each byte, and let's mark this field as static also. Now next we have a set of fields which are 4 bytes each in length, and these are CRC32, compressed size and uncompressed size. As you can see that CRC32 starts at byte 14th, which is 0E. So let's see what are the 4 bytes starting at 0E. So this is 00, 00, 00 and 00. So that means that the value of crc32 is 0 for this particular zip file, and we'll keep it that way. And let's put this value here. I have added 2 zeros, and let me put 2 more null bytes, and I'll mark this field as static also. Now do note that since the general purpose bit flag is not set, this file will not have the data descriptor section. Do keep this in mind. So the next field is compress size, and it starts at 18th byte, which is this. And let's see what is 4 bytes from here. We have 0 0 0 0 0 0 and 0 0. So again the value of this field is 0, which seems to be true because the size of our text file is 0 bytes, as you can see here. So I'll just copy this from here and paste here. Next we have uncompressed size starting at the 22nd byte, which is this. So the next 4 bytes from here are again 0. So let's put this value here. So let's copy this value from there, since this is essentially the same value, and paste it here. Now again I have kept this field as static because we are going to have a 0 byte size text file inside all of our zip files that are generated by the fuzzing script that we'll create in the next part. Next, starting at 26th byte, we have file name length, so which is this, and here it says 8 and 0 0. So let's just put it here in the little endian format. So hex 0 0 will come first, and then hex 08. Now as you may have guessed, that value of 8 here means that the length of this field, which is the file name, is 8 bytes, which is true if we see the name of the text file, which is text.txt, and it has 8 characters, which is text.txt. Now since we are going to fuzz this field, this cannot be a static field, this will be a dynamic field, and it will change for each of the zip files that we generate via our fuzzing script. So we'll mark it as dynamic, and to do that I'll put a red in the dynamic column, so it becomes easy to differentiate between static and dynamic fields. Next we have extra field length at 28th byte, which is after this, and it is again marked as 0 0, so that means we don't have any extra fields. So let's just put it here, which is hex 0 0, hex 0 0, and we'll keep this as static. So let me just copy this from here and paste here. And next we have the value of file name starting at the 30th byte, which is this, and it is of 8 bytes. So let me just select 8 bytes from here, and it ends here. So as you can see that we have selected the file name. Now since we'll need it in the little endian format, let's copy this value from here and paste it here, and let's just quickly convert it into a Python hex byte format. Now again, this field is not going to be a static field, this is going to be dynamic, because each of the zip files that will be generated by our fuzzing script will have a different file name in it. So we'll copy this red color from here and paste it here. So far we have 2 dynamic fields and remaining static fields, and since we don't have an extra field, we don't need this field here. So let's leave it blank and move on to the next section in zip file format. So we don't have data descriptor section in this zip file because the general purpose bit flags were not set. So that means that our next section is central directory file header. Now let me give you a quick exercise here. Since local file header and central directory file header are essentially more or less same, go ahead and fill these columns on your own. I'll do that also, and when I come back we'll compare our results. Let's see if you can identify any more dynamic fields. So I hope you have done this exercise and you have come up with a result of your own. Now let's compare our results. So the central directory file header starts from here, which is 26th byte in the structure. So if you want to see the offset now, remember to add 26 to each of these values. And now it says that the 4 byte from here are the signature of central file header, which is 504B0102, and this is the value that we have pasted here. I hope you have the same value, and this field will be a static field. Similarly, next 2 bytes are version made by, which is 14 and 00 in this case, so our value will be 0014 in the Euclidean format, and again this will be a static field. Next we have version needed to extract minimum, which is 0A and 00 as we saw here, and that is what I have written here in Euclidean format, and this will be a static field. And these next set of fields till extra field here are same fields that we saw in the local file header, and their values will be same as they were in the local file header. That is what I have mentioned here, and I hope you have done the same. You can verify these values from the file structure here. Next we have file comment length, which is at 32nd byte. Now remember that we identified that in this structure central file directory record or header starts at the 26th byte, but this 26 is in hex and this 32 is in decimal. So we need to do a certain calculation. So we'll open calculator, and here I'll write 26 in hex, and let's convert it into decimal and add 32 to it, which gives us 70 in decimal, and 70 in decimal is 46 in hex. So that means that here we'll need to start from this byte, and since this field is of 2 bytes, so we'll see these 2 bytes which are marked as 00, and that is what I have written here. And I've also marked this field as static because QuickZip does not use any file comments. And I hope you have the same value. If not, please correct it. The next 2 bytes are the disk number where file starts. These are the 2 bytes pertaining to this field, and these are 00, which is what I have mentioned here, and again I have marked this field as static. Next we have 2 bytes of internal file attributes, which is these 2 bytes, and again they are 00, which is what I have written here, and we will consider this field as static. Next we have 4 bytes of external file attributes. So next 4 bytes here are 20, 00, 00 and 00, and this is what I have written here, and I have considered this field as static for the purpose of fuzzing this application. Moving down, we have relative offset of the local file header, which is again of 4 bytes, and in this case it is all zeros, so this is what I have mentioned here. Then finally we have the file name, which is starts from here, and this is what I have written here in the little endian format, and it is a dynamic field as we saw in the local file header section. Now since we don't have any extra field or file comments, I'm leaving these entries as blank. Let's move to the last section, which is end of central directory record. So in end of central directory record section, the first field that we need is end of central directory signature. It is of 4 bytes, and it needs to be these 4 bytes, which is 504B, 05 and 06, and this is what we have here, 504B, 05 and 06. So let's just copy it from here and paste here, and this is going to be a static field, so let me mark it in green. Then the next 2 bytes are number of this disk, which is 00 in this case, and again this will be a static field since this is what the value is written by QuickZip, and we are not going to fuzz this field for now. So let me just go up, select this value, copy it and paste it here. Next 2 bytes are disk where central directory starts. So these are the 2 bytes that are required now, and again these are 00. So we'll just copy this and paste it here as well. Next 2 byte or the next field in end of central directory record is number of central directory records on this disk. So in this case we have only one central directory record, and That is what is represented by these 2 bytes. So we'll write it in the literary format, which is hex 00 and hex 01, and this is going to be a static field because in all of our zip files that we'll generate via our fuzzing script, there is going to be only one file. So that essentially means that there is going to be only one local file header and only one central directory record. The next field is total number of central directory records, which is again 1, as can be seen here by these 2 bytes. So I'm just going to copy this value and paste it here. Now the difference between these two fields is, let's say if your zip file is divided into multiple parts and they reside on different disks. Imagine a floppy disk containing multiple parts of a zip file. So in that particular case, the value of number of central directory records on this disk will be different than the total number of central directory records. Then we have the size of central directory record in bytes, which is marked by these 2 bytes, and in this case it is 36 and 00. So that is what we will write, hex 00 and hex 36. Now do note here that the size of central directory record depends on the size of the file name or the file name length. So if we increase the file name length, the size of central directory record goes up. So that means that this is going to be a dynamic field. So let's just come up, copy this red color and paste here to mark it as dynamic. So this is of 4 bytes. So we'll write it as hex 00 and hex 00. Next field we have is offset of start of central directory related to start of archive, and again this is of 4 bytes, and in this case these 4 bytes are 26, 00, 00 and 00. So that is what we'll write here. Now again, this offset of start of central directory is dependent on the size of the local file header, and the size of the local file header, as we saw, is dependent on the length of the file name. So this is again going to be a dynamic field. Let me just copy this red color and paste here. Next field we have is comment length, which is of 2 bytes, and these are the next 2 bytes, which is 00. So that means we don't have any comments, so we can just copy this value and paste it here, and this is going to be a static field. And since we don't have any comment, we'll just leave this field as blank. Now to quickly demonstrate why these two fields are dynamic, so let's calculate the size of central directory in bytes. So our central directory record starts from here and it ends here. Now if you see here, the length, it says 36, and that is what we have here. So that means the length of central directory records is 36 bytes, and out of those 36 bytes we have 8 bytes of file name. Now if this file name were to increase to say 10 bytes, the size of central directory record will become 38 bytes. Similarly, the offset of start of central directory record is 26, as you can see here, 20 and 06, and this is dependent on the size of the local file header, which is again dependent on the size of the file name. Now in this case, the size of the file name or the file name length is 8 bytes. Let's say if it were to be 10 bytes, then the offset value will be 28 bytes. So that finishes our correlation of the zip file format structure used by a target application and the zip file format specification. And now we have some values that we can work with to create a fuzzing script. This is something we'll see in the next part. Now if you have some confusion regarding this, do go through the first video of this part again and then come back and go through this video again and try to do this exercise on your own. That way you'll get more comfortable with this process. Now we have completed these 3 steps. So our next step is to create a fuzzing script out of this correlation so that we can generate zip files to fuzz our target application. This is something we'll see in the next video of this part. So these are the few learning resources you can use to learn more about the tools and techniques that we are using in this module. Thank you for watching this video, and I'll see you in the next part. Hello and welcome to part 2 of our acrobatics module. These are the few assumptions that I'm working with. I'm assuming that you as a learner have a prerequisite or basic knowledge of following tools and software. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we are on part 2, that is fuzzing. In the last part, we did the correlation between the zip file format specification and the zip file format structure used by a target application. Now in this part, we will take our learnings further and create a fuzzing script to generate sample zip files out of our findings. Before moving ahead with the script, I would like you to go back to the Excel sheet and I would like to make some corrections in that Excel sheet. So let's open the Excel sheet. So this is the Excel file that we created in the last part. The first change that I would like to make here is these three fields: CRC32, compressed size and uncompressed size. In the last part, though I said that there are 4 bytes, but I put only 2 bytes here. I would like you to change that and make all these 3 fields of 4 bytes each as it is shown on the screen. Now once you have made this change, I would like to suggest the second correction. Now in the last part I had said that we are writing these values in Little Eden format. However, the values that were shown in the hex editor were already in Little Eden format. So we need not convert it again into Little Eden format. So that means that all these values that you're seeing here, these and these, every value that we wrote yesterday will get reversed. And after you have reversed these values, the final result should look something like this. So I hope you have made those changes. If not, this Excel file is available with course files. So please use that Excel file. So let's move on to create the fuzzing script now. In order to create a fuzzing script to generate our sample zip files, we will need to do the following steps in that script. We will first need to create a payload and then calculate the payload length in hex, because if you remember, we'll need to specify that length of file name here. In this case, it is of 8 bytes. However, when we'll generate sample zip files, a new file name will be generated by a script and hence this length will change. And since this length is in hex byte, we will need to convert that length into hex and that too in 2 bytes, as you can see here. Next, we need to calculate the size of central directory record header, again in hex. So in our case, that would be 46 plus length of the file name. As you can see here, that the total length of central directory file header is 46 plus n plus m plus k, where k is the length of file comment field, m is the length of extra field, and n is the length of file name. Now in our case, since the values of m and k are 0, the total size of central directory file header becomes 46 plus n, where n is the length of the file name. And since we need to specify in the zip file format, we'll need to convert it into hex form. Similarly, next we'll need to calculate the offset of start of central directory record, that is related to start of the archive, and this is again dependent on the length of the file name. That is because the central directory file record header will start at the end of the local file header, and as you can see here, the length of the local file header is 30 plus n plus m, where m is the length of the extra field, and in our case the value of m is 0, so the total length of local file header becomes 30 plus n, where n is the length of file name. And again, since we need to specify this in the zip file structure, we need to convert this length into hex format. Next, we'll create the zip file structure based on the Excel file that we created, which is this. So make sure that you use the Excel file after making the changes that I had suggested earlier. So we'll take these values and put them into a script. And finally, we'll write this zip file structure to a file. So let's move to the lab now and create the script step by step as I have shown here. What you see here is the final version of the script that we are going to create. I'm not going to explain this here because it will be too cumbersome for you to understand. So we'll create it step by step as I had just shown you earlier. So to do that, I'll just create a new file. And what I'll do is, instead of typing, I'll pick up the blocks from this file and then build a script from them. So the first step that we need to do is create the payload. So let's go to the script, and this is a line where we are creating the payload. So I'll just copy this and paste it here. And instead of this count variable, let me just specify a length of 10 bytes to start with, or a length of 10 to start with. And let me save this file also. Let's save it on my desktop and let me call it zip2.py. So there is nothing complicated in this line. All we are doing is creating a file name which is 10 times a.txt, and this file name will be included in our zip file structure. Our next step was to calculate the length of the payload in hex. So again, I'll go back to my final script and let me just pick up this block here wherein I'm calculating the length of the payload using len function of Python. Next, remember that we need to convert it into hex. To do that, we will use the format function of Python, and it is done in this line here. So let me paste this line. So all we are doing is calling the format function with payload length, and this is the format in which I need this value. By this string, I'm specifying that format function should return a value of total of 6 characters and in 0x notation of hex. Our next step is to extract each byte from this payload length and convert into /x format. To do that, I will use the unhexlify function from the bin.ascii library. To import that, I'll use from bin.ascii import unhexlify, and then we'll go to the final script and copy these two lines here and paste them into a script. So in the first line, I'm extracting the first byte from this payload length in hex and passing it to unhexlify function to convert it into /x format of hex. And similarly, in the second line, I'm extracting byte 2 and then passing it to unhexlify function to convert it into the same format. To understand it better, let me demonstrate how this works. To do that, I'll go to command prompt and I'll type Python to enter into Python terminal. And here let me create a variable called byte, and I'll give it a size of 12 or a value of 12. Next, I'll need to convert it into hex format, and I'll do that using the format function as we can see here. So I'll write byte hex is equal to format, and the first argument is the byte variable, and next is the format in which we want this value to be. So that will be #06x. And now if we see the value of byte hex, you can see that it has given me a value containing a total of 6 characters and in 0x format. And next step is to extract these two individual bytes and convert them into /x format. To do that, as I told you here, that we'll be using unhexlify function of bin.ascii library. So let me import that first from bin.ascii import unhexlify, And now let me create another variable byte1, and I'll call unhexlify function. And now I'll use slicing feature of Python to extract these two characters and pass them to unhexlify function. So to do that, I'll use byte hex, and I'll need characters from the offset 2 till 4. And let me close this function. And now if we see the value of byte 1, you can see that this has given me this individual byte in /x format. Similarly, if we want to convert the second byte into this format, we need to pass that to an exlify function. And to extract that, we'll again use the slicing feature byte hex, and this time we'll need it from the offset 4 to 6. And let's see the value of byte 2. So this time this is 0c, which is this byte in /x format. Now it is necessary to convert this value into this format because we will be passing individual bytes in the zip file format structure. So I hope that this is clear. If not, do this exercise on your own and try to understand how it works. If you still have any questions, please ask them in the Q&A section. So our next step is to calculate the size of central directory record header, again in hex format. To do that, we'll go to the final script and copy these 3 lines from here. So in these 3 lines, I'm first creating a size cd variable which will hold the length of central directory record header, and I'm using format function and passing it 46 plus payload length. Remember from our discussion earlier that in this case the size of central directory record header will be 46 plus the length of file name, and I need it in this 0x format. Next, I'm extracting the 2 bytes as returned by this format function and converting them into /x format. So our next step is to calculate the offset of start of central directory record relative to start of archive. Again, we'll need it in hex format. So to do that, let's go to the final script and copy these 3 lines, and I'll paste them here. So here again, I'm creating a variable by the name of offset cd, and I'm assigning it the value returned by the format function. Now to format function, I'm passing a value of 30 plus payload length. And again, if you remember from our discussion earlier that the offset of start of central directory record is 30 plus the payload length or the file name length. So I'm passing that value here, and I'll need it in the 0hex format and with a total of 6 characters. And then in the next 2 lines, I'm extracting the individual bytes and converting them into the /x format. Our next step is to create the zip file structure. So again, let's go back to our final fuzzing script and copy these lines from here. And paste them here. So as you can see here that these are the same fields that we saw in the zip file format specification, and these are the same value that we had extracted from the zip file format structure used by a target application. You can even check it by using our Excel file. So let me show you that. So we'll start with the local file header, and starting from the first value, you can match each of the corresponding values here, and it will be the same value as we have seen here, except for the file name length and the file name fields, because these were the dynamic fields as we had marked earlier, and same I have mentioned here. So in our case, in the script, the file name length field will become a combination of payload length by 2 plus 1, and similarly in the second part, which is central directory file header, the payload length or the file name length field will become a combination of payload length by 2 plus payload length by 1. And in the final section, which is end of central directory file header, size of central directory will become a combination of size cd byte 2 plus size cd byte 1. Now I know that this field is of 4 bytes and we have only considered the 2 bytes here. A simple reason for that is that in our case, the size of central directory file header will not go to a value wherein we'll need to use these 2 bytes. The same is true for the offset of central directory field, which is again of 4 bytes, and we are using only these 2 bytes, and we have kept these 2 bytes as static. So now we have built the zip file structure. Our next step is to write the zip file structure to a file. To do that, let me maximize it first, and I'll go to a final script, and let's copy these 5 lines here and paste them here. So here first we are creating a file name, and let me change it for now to, let's say, test.zip. So first we are creating a file name which is test.zip. Then we are opening this file for writing, and then writing the local file header, then our file name, then the central directory file header, then again our file name, and then the end of central directory file header, and then finally we are closing this file. So this will give us a zip file containing this structure as we just saw here. Now if you're clear with the working of this script so far, let's move to our final script and see the final changes. Now since we need to generate sample files from this script, we'll need to run this code in a loop with a variety of file sizes. So for that, I have put it here in a for range loop, and I've created two variables here. First is count1 and second is count2. I'm using count1 for the loop variable, and I'm starting from 1 and going up to 5000 with a step of 500 each. Next, we are dynamically generating our payload based on the value of the loop count variable, which is cnt in this case. And we are using cnt2 as the name of our zip file. As you can see here, we are using the cnt2 variable as the name of our zip file, and we are incrementing this by 1 every time a zip file is created by the script. So it would give us zip files by the name of 1.zip, 2.zip, 3.zip, and so on. So that is how this script works. If there is some part of the script that is still not clear to you, I would suggest that you go through this video once again and try to go through the script line by line and understand what it is doing. And if you need any help with that, you can reach out to me in the Q&A section. The script is available as part of course files. So that brings us to the end of this video. In the next part, we'll run the script, create our sample test files, and using file fuzz, we'll finally fuzz our target application. I know that this has been a much longer journey in fuzzing than any of our previous modules, and that is because we are covering a lot of ground here and I don't want to rush through any of it. So please be patient and hold your seat tight for the next set of acrobatics. These are the few learning resources you can use to learn more about the tools, techniques, and software we are using in this module. Thank you for watching this video, and I'll see you in the next part. Hello and welcome to part 2 of the acrobatics module. I'm working with few assumptions here. I'm assuming that you have a prerequisite or basic knowledge of following tools and software. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we are on part 2, that is fuzzing. And as I said that we have divided this part into subparts, so this will be a last subpart of fuzzing. In previous parts, we have covered a lot of ground. We understood the zip file format specification, and then we reversed the zip file format structure used by the target application, and we correlated the two and created an Excel sheet out of it. In using that Excel sheet, we created a fuzzing script to generate our sample zip files. And now all that remains to do is to run that script and generate the zip files, and finally use file fuzz to fuzz the target application. and it will also need some manual intervention on our part. So without further ado, let's move to the lab and let's complete the fuzzing part of this module. This is the Python script that we created in the last part, and I hope that you're clear with how this works. If not, I suggest you go back to the previous video and understand how this script is working. Now, one thing that I would like to mention here, the number of zip files or number of test cases that will be generated by this script will depend on the step that we specify here. So since we are going from 1 to 5000 and we have specified a step of 500, it will generate around 10 sample zip files. If you want more, you can reduce the size of the step, or if you want less, you can increase the size of the step. So for our purposes, I'm going to make this as 100 for a better demonstration, and I'll save it. Then let me close Notepad++ for a minute, and let me copy this zip file to a place where I want to store my sample zip files, which is in my computer, C drive and fuzz. So let me remove this already existing files and I'll paste it here. Alright, so now let's open the command prompt and navigate to this directory, and finally we'll run our script to generate the sample files. So we'll use python zip.py. Oops, it's giving an error. So let's open this file and see where the error lies. So our command prompt says that it's on line 73, and apparently it says that file name is not defined. So let's see what is happening there. So the error is here, and it is obvious because we have defined the variable file name after we are printing it. So we need to correct it, and I'll paste it here. And let me just reformat it a bit. I'll save it. Then I'll go back to command prompt again and run the script. So as you can see that it has created 50.zip files, and if I come here to this folder, you can see that 50 zip files have been created, numbered 1.zip to 50.zip. Now as a test, and before we feed these files to FileFuzz to fuzz quickzip.exe, let's try and open one of these files in quickzip. So to do that, I'll just double click it because my system is already set to open files with quickzip.exe, and you can say that a central header signature is wrong. Now there is a reason for that. Let me first close it. The reason is that here we are specifying hex 0a, which gets translated into a new line character. So when this structure is being written to this zip file, this character, instead of staying as hex 0a, it is getting translated into a new line. And when the zip software finds that instead of 0a there is a new line, it is giving that error of corrupt central directory header signature. So to do that, instead of 0a, if I just put 0 here, and similarly let's change here also in the central directory file header, in the third field, that is version needed to extract minimum, let's change it to 0 also, and I'll save it, and let's run the script again. And this time let's open the file with quickzip, and as you can see that it has not given me any errors so far. And if I open this file is also opening, so everything is fine with our sample test cases. Now the next step is to feed these files to FileFuzz and let FileFuzz do its magic. So I'll open FileFuzz here, and here I'll need to specify certain settings. First is I'll need to move it to zip, and let's change this to fuzz. We don't have a zip directory in there. and we don't need to change any other setting in the create section. Let's go to execute, and here we need to specify the command that we needed to execute. So let's select quickzip.exe, which is in C program files, and quickzip4, and then we'll select quickzip.exe. Now I'm enclosing it in double quotes because there are spaces in between this path, and if I don't put the double quotes, or if I don't enclose this in double quotes, FileFuzz will not be able to interpret this path correctly. And from here, let's remove this string. We'll only need to pass one argument to it, and here I'll specify the start file as 1 and the last file or the finish file as 50, and in milliseconds I would like to specify 5 seconds so that I can do the manual intervention in between. Or rather, let's see what happens if we keep it at 2000 milliseconds and we don't intervene manually. Alright, so looks like we are all set. Let's clear this log and execute. So you can see that nothing is happening so far. It is just opening quickzip.exe and then closing it. So we have covered all 50 test cases, and now it is reporting that no exceptions have been found. So that means if we let this run on its own, no exceptions are found. So we need to intervene manually a bit. So to do that, I'll need sufficient time between the opening and closing of quickzip.exe. So let's change it to 6000 milliseconds and execute it again. And let's try to open this file. So it has opened and nothing has happened. So I will continue to do this, and as you can see that so far no exceptions have been found, and now one exception has been found. And similarly, as you can see here that in 5.zip there was again an exception, and if I open this file it will give another exception in 7.zip. Similarly, it's giving an exception in 9.zip as well, and in 11.zip also we have an exception. So that means we have found an exception. So let's stop this. I'll use the kill all button to stop this execution, but it is not stopping, so I will have to let it execute. So now all our test cases have been executed and we have identified multiple crashes. So let's look at the first crash itself, and the first crash occurred at 4.zip, and in this case the length of the file name was around 400 bytes or 400 characters, and subsequently we had crash on every file after this. So I have sampled few of the crashes here for you, can see here, and let's analyze this crash in this window. You can see that EX has been overwritten with 41 41 41 41, which is hex for capital A, and EBX has also been overwritten with same characters. ECX is all 0, and EDX also has been overwritten with 41 41 41 41. And if we check other registers such as ESI, EDI, ESP and EBP, so apart from EDI every other register seems fine. But anyways, this gives us something to work with. We need to investigate this crash further to see if we can exploit it or not. To do that, we need to convert a fuzzing script into a POC script and then replicate this crash in quickzip.exe. Now, just to make things easier for us a bit in the next part, what I have done is I've executed the sample test cases till 50.zip. So that means that even at length 5000 we are getting this same crash. However, the registers which are being overwritten with 41, 41, 41, 41 have changed. So you can see that in this case, ESI and EDI have been overwritten with these characters and EBX is 0. So I've done this so that we don't spend much time in finding out the appropriate buffer length that is available to us. So finally, our long journey of fuzzing has come to an end and all our efforts have paid off because we are seeing successful crashes here in this window. So that means our understanding of zip file format structure was correct, our correlation was correct, and finally the sample zip files that we created from our fuzzing script were also of right format. So everything seems to be working here. In the next part, we'll create a POC and replicate the crash. These are the few learning resources you can use to learn more about the tools, software, and techniques that we are using in this module. Thank you for watching this video and I'll see you in the next part. Hello and welcome to part 3 of acrobatics module. These are the few assumptions that I'm working with. I'm assuming that you have a prerequisite knowledge of following tools and software. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we are on part 3, that is POC creation. Our target software for this module is we will be using Microsoft Windows XP as a VM, and on that our target application is QuickZip 4.6, and this version of QuickZip is vulnerable to a zip file containing long file names. This vulnerability was discovered by Colan Coder in 2010. If you want to read a detailed write-up about this vulnerability, please check out the link mentioned below. So a proof of concept is nothing but a script or program that we will use to replicate the crash that we saw in the fuzzing part. It can be written in any language of your choice, either Python, Perl, C, C++. I will be using Python for this module. And then this POC is further enhanced and converted into a working exploit. So let's move to the lab and create a POC from the fuzzing script that we saw earlier. So I'm on my Windows XP machine and this is the fuzzing script that we had created earlier. Now we'll need to modify this script a bit to convert it into a working POC for our exploit. To do that, I'll first save this file as a zip POC and I'll save it on my desktop. Now I only need to generate one zip file, so I will remove this for loop and these count variables also. I don't need them now, and instead of this count I'll specify 5000. So this means that the length of my file name in this zip file or in the POC zip file will be 5000 a's.txt. Then rest will be all automatically calculated based on our payload, so I'm not going to touch that. Now the next change that I need to make is removing this count2 variable, and then I'll remove this count2 from here also, which is the file name variable, and instead of that I'll write zip poc.zip. Now the last change that I need to do is change the formatting of this entire code. I need to remove the tab from every line here because earlier it was aligned to be inside a for loop, and now since we don't have that for loop, we don't need this indentation. So make those changes, and I'll make those changes on my end also, and I'll see you after I make those changes. So now after removing all the indentation, our POC is now ready. So that means that we have successfully created a proof of concept script from our fuzzing script. Now we need to give it a test run. So I'll save it and I'll open my command prompt, and then I'll go to the desktop and run python zip poc.py. Looks like there is an error, and this is the same error that we saw, that I am using this file name variable before I am declaring it. And I'm sorry that this error has occurred again. I'm using the same script from a different place, so the changes that I had made in the earlier script are not reflecting in this. Alright, so now I'll save it and run it again. So this time our zip poc.zip file has been created. Now let's open Immunity Debugger and launch QuickZip in it. Now do note that for me it was available in the recent programs, for you it might not be. So if it is not, then go to open and navigate to program files, QuickZip folder, and then select quickzip.exe and I'll run it. And now in this I'll open our zip file that we had just created, which is this zip poc.zip. So as you can see that there is a single file here containing a long file name, and if I double click on this file, our application crashes and we have an access violation when reading 41414125. And as you can see here that ESP has been overwritten with a certain value, but EIP has not been overwritten. So let's check our ACH chain. Seems like a long chain and there is nothing that suggests here that this chain has been overwritten. So never mind, still let's pass this exception to the program and see what happens. So let's keep on passing the exception to the program and see what happens. Passing it again and again and again. Alright, so after these many tries you can see that EIP has been overwritten with 41 41 41 41, which is part of our buffer and it is hex for capital A. And now if you see the ACH chain, you can see that it has been overwritten by the file name, by the buffer that we had supplied. However, passing these many exceptions to the program and then finally waiting for EIP to be overwritten is a bit inconvenient. So let's see if we can optimize it a bit more. So I'll first restart quickzip.exe in Immunity Debugger and I'll go to my POC, and instead of 5000 here I'll specify a length of 4000 instead. Save it, generate a new zip file out of it, and then run quickzip.exe again. I'll open this file and then double click on it, and let's see if we have overwritten the ACH chain now. So this time it seems that ACH chain has been overwritten and we'll only need to pass the exception once to the program for the EIP to be overwritten. So let's go back to CPU window and press Shift F9 to pass the exception to this program. And as you can see that EIP has been overwritten with 41 41 41 41, which is X for capital A. So that means that we have replicated this crash successfully. And now since EIP has been overwritten with the value that we had supplied, we can now take advantage of this crash and create an exploit out of it. This is something that we will do in the next set of videos. So these are the few learning resources you can use to learn more about the tools, techniques and software that we are using in this module. Thank you for watching this video and I'll see you in the next part. Hello and welcome to part 4 of acrobatics module. These are the few assumptions I'm working with. I'm assuming that you have a prerequisite or basic knowledge of following tools and software. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we are on part 4, that is controlling the execution. In the last part, we investigated the crash and we found it to be exploitable because we saw that we were able to overwrite EIP with a part of our buffer. Now in this part, we'll further investigate that crash and we'll find out the location of the character which overrides SEH pointer and thus the EIP. We'll then verify that location. Now in a normal SEH, the next part is to redirect the execution to a memory location that is controlled by an attacker. In this case, this is us. And to do that, we'll need to find an accessible and reliable memory address that contains the instructions pop pop return. And then we overwrite the SEH pointer with a pointer to these instructions. And then normally we'll find a buffer and jump to it by overwriting NSEH with a backward or forward jump as required. However, this case is going to be a bit different because of the limited character set that is available to us. So let's move to the lab and work on an exploit to enhance it further. If you need a refresher on how SEH override works, do check out the second module of our hands-on exploit development course. It covers the SEH override technique, and in that the first video explains how SEH override technique works. So onwards to the lab now. So this is my Windows XP machine and this is the POC that we had created in the last part. So let me open it in Notepad++, and now let me open Immunity Debugger, and in it I'll launch quickzip.exe and then I'll run it. So quickzip has launched. Now first task for this video is to find out the location of the character at which SEH pointer is overwritten. So to do that, we need the MSF pattern. Now up till now we have been generating that MSF pattern using Kali Linux. However, there is a command in Mona library also that does the same thing. So we are going to use that. So I'll use Mona and pattern underscore create, and then I'll specify a length of 4000 because that is what we are using in a file name, and I'll press enter. So you can see that it has generated the pattern. However, it says that we don't need to copy this pattern from this window. It has written this pattern to pattern.txt and we can copy that pattern from that file. So to do that, let me go to the root directory of Immunity Debugger, which is in my computer, C drive, program files. Let me maximize it and I'll go to Immunity folder, which is here, and Immunity Debugger. And in here there'll be a file called pattern.txt, which is this. So I'll just copy this pattern. By the way, also note that it has written this pattern in hex form also, so we can use this also, but for now let's stick to the ASCII version. So now I'll go to my POC, and where I'm creating the file name, I'll replace this with the pattern, and let me save this file. Now I'll go to the command prompt and change directory to desktop because that is where this file resides on my system, and I'll run python zip poc.py. Alright, so our POC zip file with this pattern is now ready. All we need to do is open this file in quickzip.exe. So that is what I'm doing now, and I'll select this file. So you can see that this file is now open in quickzip.exe, and now I'll double click on the file in it. So this will trigger the crash, as you can see here. And now let's pass the exception to the program using Shift F9. And looks like our EIP has not been overwritten. So let's go to view SEH chain, and if we pass the exception again to this program, it should be overwritten with these characters. And I'll press Shift F9 again. So this time EIP has been overwritten with characters that looks like as if they belong to our MSF pattern. Now in order to find MSF pattern, I'll use the find MSP command of Mona library. So I'll use Mona find MSP. You can see that it is looking for cyclic pattern in the memory, and I'm extremely sorry for this. This happens because QuickZip freezes when it crashes, and it is impossible to move this window. So from next time we'll need to keep this window a bit lower so that it doesn't block our view. But for now, let's work with what we have. And it says that it has written these results to find msp.txt. So let's go there and search for this file, which is find msp.txt, and here it is. And let me move this window here so that it is not blocked by this window. And now let's scroll. So here is the result. So you can see that cyclic pattern found at this memory location, and length is 259 bytes, and again it has found at this location, length is 259 bytes. And then if you see here, it says examining SEH chain, SEH record, and SEH field at this has been overwritten with this pattern, and the offset is 294, which is followed by 1020 bytes of cyclic data after the handler. So this means that at offset 294, SEH record has been overwritten. So let's verify it. To do that, we'll first restart quickzip.exe in Immunity Debugger, and I'll press yes. And now let's update our POC. Let's remove this MSF pattern, and in place of that, I'll again go back to A. I'll write 290, and I also want to overwrite an SEH record, which will be overwritten by B's. So 290 plus 4 B's gives 294, and now I will write 4 C's, which should overwrite the SEH record, and thus the EIP. And for the remaining, I'll just send a set of D's to it. Now in order to keep it at 4000, we need to specify 3706. So let's save it and generate this zip file again, and let's close these text files. We don't need them anymore. Let's close Immunity Debugger folder also, and I'll go to Immunity Debugger and I'll press play to run the application. So quickzip.exe has launched. Now this time I'll move this window to the side so that it doesn't block this view, and I'll open the zip file. And I'm selecting this zip file, and now let's double click on it to open this, and it triggers the crash. Let's pass the exception to the program using Shift F9, and as you can see that it has overwritten it with 44, 44, 44, 44. So this has overwritten this with 4 Ds. So that means there was a bit of miscalculation in our payload here. So let's make it 294, and we'll reduce it by 4 here, and let's make it 3702. We'll save it, and let's restart this application again. Run this application, and I'll generate the new zip POC file. Now let me open the POC zip file again. Zip poc.zip, and I'll double click on this file to trigger the crash. And now let's pass the exception to the program using Shift F9 once again, and this time you can see that it has overwritten it with 43, 43, 43, 43, which is hex for capital C. So let's go back to our presentation and see what our next step is. So we have identified the location of character at which SEH pointer is overwritten. We have verified that location, and the next step is to redirect the execution to the memory location which is controlled by us. and for that we need to find this pointer to pop return instructions. So let's move back to the lab and do that. Now let me restart the application in Immunity Debugger. And I'll run this application. Now it is recommended that before finding that instruction, or let's say even jump ESP instruction, that you run this application, because after running certain modules are loaded, and if you try to find the location of jump ESP or SEH pointers as we need here, before running this application, certain modules might not be included in your search. So it is always recommended to do this search after your application is running in Immunity Debugger. So I'll go here, I'll issue the command Mona and SEH. So it is taking some time to search. Alright, it's back. So let's view the log window. And here it says that it has found a total of 7973 pointers, and only first 20 pointers are shown here. So let's see if any of these pointers could work for us. And from the first look of it, I think we can choose either this or this. I'm going to go with this. So I'm going to copy this to clipboard, and I'll just need the message part. Let's go back to our POC and put a comment here and paste this. And now we'll replace these C's with this memory address in little endian format. So to do that, I'll do hex 31 and hex 56 and then hex 42 and then hex 00, and I'll save it. Now do note that since here we are specifying a 0, which is a null byte, there is good possibility that it might truncate our buffer, and the remaining part, that is the D part of the buffer, might get written somewhere else in the memory. Let's worry about that a bit later. Let's first verify if this is working. So I'll copy this address, and I've already saved this file, so I need not do it again. And Immunity Debugger, let me go back to the CPU window, and I'll go to this expression, and I'll put a breakpoint here. Alright, now let me regenerate the zip file or the POC zip file, and now let's open this zip file in quickzip.exe. So let me first move this window here, and I'll open this file, and now I'll double click on it to open it. So our application has crashed, and let's pass the exception to the program or to the debugger, and so now our breakpoint has been hit, so that means that we are able to get to this memory address correctly. Now let's step into it one by one. Return, and then you can see that we are at the location where NSEH record should be, and since we have overwritten NSEH with 4 B's, and that is what it is showing here, 42 is hex for capital B. So we are on this part of the buffer, and let's see what do we have above this. So if I scroll up a bit, you can see that this is a portion of the buffer which we have specified in this part. So that means these are 294 A's or 294 bytes that is available to us. Now let's see if this part has made it successfully. So let's scroll down, and that part of D's should have been here. However, as I said, that because of the null byte, which is this part has been truncated, and now we need to check if this part has been written somewhere else in the memory. If we are able to find this part, then we will have to think of a technique so that we are able to reach this portion of our buffer. Now first let's find out if this portion of buffer is still in the memory or not. To do that, I'll restart Immunity Debugger, or rather quickzip.exe in Immunity Debugger. I'll run it. And again, I'm going to use Mona pattern create command to create a pattern of 3702 bytes. And this is written in pattern.txt. So let's go there and copy it. And let's go to program files and immunity.inc, which is this Immunity Debugger. And here I go to pattern.txt. From this file, let's copy this ASCII string of 3702 bytes, which is still here. And let's move back to our POC and replace this part of these with this pattern. Let's save it. Let's generate the POC zip file again. Alright, now let's go back to Immunity Debugger and CPU window. So our application is paused. Let's run it. Alright, so our application is running now. Let's open the zip file in it. And I'll go to zip POC and double click on it, and then I'll double click on this file. So you can see that a crash has occurred, and I'll pass this exception to the debugger, and we have hit our breakpoint. So let's step into it one by one, and we are at the first portion of a buffer. Now I'll use find MSP command to find this pattern, and let's see if we are able to find this pattern. If not, we'll have to think of some other technique, and if we are able to find it, then I think we can use a technique that is known to us. Can you guess which technique is that? Alright, so it has returned with the results, and this time you can see that the cyclic pattern is found at this memory address and the length is 3618 bytes. So we had sent it a pattern of 3702 bytes, but it has written only 3618 bytes. But right now that is not of concern to us, because even this length is sufficient to put our payload shellcode here. So that means that even though this part of a buffer got truncated, it is still there in the memory somewhere, and using a correct technique we can reach to it. Alright, so which technique are we going to use for this? Any guesses? So if your answer is egg hunters, you are spot on. Well done. So now this finding means that we need to write a egg hunter in this part of a buffer, and once that egg hunter runs, it will jump to our payload shellcode and execute it. But for that, we'll have to first jump back from this portion to this first portion of our buffer. So we have around 294 bytes here. To find out relevant jump statements, I'll go to my Kali machine and I'll use msf underscore nasm, msf nasm underscore shell. So now since we have 294 bytes, let's try to jump back around 200 bytes, and let's see what is the relevant instruction for that. So we'll do jump $-200. So dollar here means current location, and we are saying that we want to jump from current location to 200 bytes backwards, and press enter. So you can see that this is a pretty long opcode, and it's around 6 bytes if I'm not wrong. So 1 2 3 4 5, yeah, 5 bytes. But if you go back to our crash, we only have 4 bytes to overwrite it. So definitely we cannot use this jump. So let's try a shorter jump, and to do that, let's do jump $-126, and here it says EB80, so this is just to instruction, and it will fit well into our NaCH portion. Alright, so let's try this. I'll first go back to my Kali machine. Let me just copy these two lines. And on my Windows XP machine in my POC, I'll go here and paste these two lines. Now let me remove this MSF pattern. I don't need it anymore. And I'll replace it with 3072Ds or 3702Ds. Save it, and in the first 2 bytes of NaCH, I'll write the opcodes for this short jump, which is hex EB and hex 80, and then let's convert BB into their hex representation also, which is hex 42 and hex 42. Alright, let's save it, generate the zip POC again, and let's go back to Emulator Debugger and restart the application. Run it. So it has hit a breakpoint during its normal execution, so not to worry about it, just press play here, and seems like it has again hit the breakpoint. Just press play. Now let's open the zip file. Zip poc.zip. Let's double click on this file. So our application has crashed, and let's pass the exception to the debugger using Shift F9, and now we have hit our breakpoint on the pop return instructions. So just let's step into it, and here we are on the NaCH part. Oh, but what is this? We had sent it a short jump of 2 bytes followed by 2 bytes of Bs, but clearly something has changed here, and it has changed the entire meaning of a short jump. So what is that all about? Can you guess? So looks like this might have something to do with the character set that is available to us. So before we can move forward, we need to do a bad character analysis for this application, which is something we'll do in the next part. So in this part, we were able to reach till here where we have overwritten SCH with the pointer of these instructions, but we have not been able to jump back to our buffer, possibly because of the character set limitation. So these are the few learning resources you can use to learn more about the tools, techniques, and software that we are using in this module. Thank you for watching this video, and I'll see you in the next part. Hello, and welcome to part 5 of the acrobatics module. These are the few assumptions that I'm working with. I'm assuming that you have a prerequisite or basic knowledge of following tools and software. If you don't, please check out the resources mentioned at the end of this video. This is our module structure, and we are on part 5, that is bad character analysis. In the last part, we saw that the short jump opcodes that we had sent to the application got translated into some other characters. So therefore, it is essential for us at this stage to do a bad character analysis for this application. And in bad character analysis, we send all possible characters from hex 00 to hex FF as part of a buffer and see how the application treats them. And if any of those characters are translated differently by the application and thereby changing the meaning of our shellcode, we remove those characters from our final payload shellcode. And these characters are considered to be bad characters for our final payload. Now for this application, I'm considering these 3 characters as bad characters by default, and the rationale behind it is as follows. The first character shown here, which is hex 00, is a bad character by default because it represents a null byte, and as we have seen earlier, it truncates our buffer. The second character, which is hex 0a, is a line feed or a new line character, and it also truncates our buffer. And this is also we have seen earlier when we were building our zip file structure. The next character here is hex 0d, which represents a carriage return, and works in the similar way as a line feed or a new line. Hence, it also truncates our buffer and we will consider it as a bad character for our buffer. Now to find out the rest of the bad characters, let's move to the lab. So I am on my Windows 7 machine and this is the POC that we had created so far, and we'll use this POC to find out the bad characters. To do that, I'll first open Immunity Debugger and in it I'll launch quickzip.exe and let's run the application. And it says that it has hit our breakpoint, so let's run it, and once again we need to press play. Now our application is running, so I'm minimizing it for now. Now in order to send all characters from hex 00 to hex FF, we'll need a list of those characters. We can very easily use Mona library to generate a character set for us, which is called byte array, and from that exclude the characters that we are already assuming to be bad characters. So the command to generate byte array using Mona library is !Mona, and then I'll specify the command byte array and -b to specify bad characters, and here I'll specify hex 00, hex 0a and hex 0d. Now before I issue this command, I would also like to show you one more feature that Mona has, and that is to set the working directory of Mona library. Now you can very easily do this entire process using the default working directory of Mona library. However, I just want to show you how to set it in case you ever find yourself in a situation where you need a different working directory. And this is also a good way of introducing different features of Mona library. So to set a different working directory, we'll first have to create a directory. So let's go to C drive, and here I'll create a directory named Mona, and now I'll go back to Immunity Debugger, and here I'll say !Mona config -set working directory to C Mona. And if you check the log window, it is saying that it has written this configuration to the file, and it has replaced the old value with a new value, which is Mona folder in the C drive. Alright, so let's go back to CPU window, and now let's continue generating our byte array. So we'll do that using !Mona byte array, and to specify bad characters I'll use -v, and then in single quotes I specify the bad characters, which are hex 00, hex 0a and hex 0d. So as you can see that Mona has generated an array of around 253 characters, and you can see that it has generated a table excluding 3 bad characters. Now it has written this array to the file bytearray.txt in the working directory that we had just set. So let's open that file in Notepad++, and I go to open and go to C drive now, and here let's go to Mona folder and open bytearray.txt. So now let's just copy this, and do remember that the size of this array is 253 characters. And let's go back to our POC, and here we'll create a new variable called byte array. You can choose any name of your choice. I'm using byte array just for convenience, and let me copy it. All right, and let me remove the extra double quote from here, and now we'll place this byte character in the first part of our buffer, which is byte array, and let's place around 25 A's here. And now we need to fix the size of this A. So if we subtract 253 and 25 from 294, that gives us a buffer of around 16 bytes. So this value should be 294. Let's verify it. I'll open calculator and it's 16 plus 253 plus 25 is 294. Alright, great. So now I'll save this file and I'll open command prompt to generate a new POC zip file. First, I'll change directory to desktop and now I'll run the command python and the name of the python file, which is zip poc.py, and it is saying that it has some error. Alright, so we need to remove this extra double quote from here also. So generating it again, and now the file has been successfully generated. Now let's open this file in quickzip.exe and I'll open zip poc, and you can see that, alright, let me go to CPU window. You can see that application is running but nothing has happened so far, and if I go to quickzip.exe, it seems to be frozen. Alright, so that means that there are some other characters in our buffer that are not going well with quickzip.exe and hence it has frozen. Not a problem. So let's restart the application first. So now we'll need to identify what other characters we should include so that our buffer becomes valid. Now if you remember that we are sending our payload in the field called file name, and by default Windows has certain characters which are not allowed to be part of a file name. Now what these characters are, you can check that out in Microsoft documentation using this link. A short link for this is displayed below, and as you can see here that it has around 1 2 3 4 5 6 7 8 9 characters which are marked as reserved characters and they cannot be part of a file name. So these characters seem to be a good candidate to eliminate from our buffer and then see how our application responds to the resulting buffer. Now one thing I would like you to note here that even though these are reserved characters for file name, it is not necessary that all of these characters would be bad characters for our application. We are just going to exclude them to see how the application responds to the buffer, and then we'll eliminate these characters one by one and identify which out of these characters are actually bad characters for our application. So if it does not make any sense, follow along with me. Now I have already copied these characters in a text file here, and let me copy it, and I'll need hex representation of these ASCII characters. To do that, I'll go to a ASCII to hex converter and I'll paste these characters, which I've already done here, and you can see the hex representation of these characters. So I'll copy this hex representation of these characters from here, and let's go back to WinDbg and then generate a new set of byte array without these characters. So I'll paste them and let me just quickly convert them into /hex notation. Our list of bad characters is ready now, and let's press enter to generate this byte array, and this array has been generated and you can see that it has excluded 12 bad characters, so not to worry about that. And let's open this file in Notepad++ and I'll press yes to reload this file. So this is the new byte array that was generated, so I'll just copy it and paste it here. Now do remember that this length is of 244 bytes because total number of hex characters are 256 and 256 minus 12 is 244. So we need to fix our buffer here, and if we minus 244 from 294 we'll get 50. So that means we need to increase this by 9 bytes and make it 25, and we already have this A as 25, so this makes it a total of 294 bytes as it should be. So I'll save it now and let me now regenerate the POC zip file, and Let's run the application in immediate debugger. Let me go to CPU window, and it seems to have hit a breakpoint, so we need to press play twice, and our application has launched. Let me move it here and open the new POC zip file. So you can see that now it has not frozen and it is displaying a file as well. So I'll double click on this file and our application has crashed. You can see an access violation when reading this value. So I'll pass this exception to the program using Shift F9, and we have hit the breakpoint at pop return instructions. So let's just step into it. And now we have arrived at NACH. So let's scroll up to see our byte array. So this is the byte array that we had sent to the application. And from the first look, it seems that some of the characters have made it to the buffer as it is and some have changed. We'll compare that in a bit. So now to compare the byte array that is in application memory with the one that we had sent, we'll again use Mona library and we'll use the compare feature of Mona library. So to do that, the command is Mona compare, and I'll need to specify it a file which is in our C directory, Mona folder, and byte array dot win, and then I'll need to specify a memory address in memory from where our buffer starts, or from where the byte array starts, to be more specific. So in our case it is this memory address 0012FAEF. So I'll write that here, 0012FAEF. Now if you're wondering that from where this file came, just check the log window and navigate to the logs where we have generated this byte array. You can see that it has written this byte array to a file called bytearray.txt, as well as it has saved the binary output in bytearray.bin file, which is residing in our Mona working directory. So that is where this file came from. So let's move back to CPU window and I'll press enter to run this command now. So you can see that Mona library has returned. Let's see what it has returned for us. So it's saying that you need to specify a valid file name using parameter -f, and looks like I've forgotten to specify -f. So let me correct my mistake by putting f here, and now let's run this command. It says that at address this, first corruption appears after 12 bytes, and if you want to check more details of it, you can go to the log window. Let's maximize it, and here are two tables. So let's first check this table, and it says that for bytes 01 to 0e they are unmodified and 0f is corrupted, and in memory instead of 0f it has found a4. Then in the next line it says that the bytes 10, 11, 12, 13 are unmodified, and if you move to the next line it says that bytes 14 and 15 have been translated into b6 and a7 and hence they are considered as corrupted. Then in the next line it says that bytes from 16 to 7f are unmodified and every other byte from 80 to ff has been translated to some other character and hence it is corrupted. So a more elaborate version of this table is this comparison results. So here you can see two set of rows for each byte. One is the value of byte as it appears in the file. Second is the value of byte as it appears in the memory. Now if in memory row there is no byte as it is here, so that means that the value of byte in memory and the value of byte in file are same. However, if you note that in the memory row there is a different value below a byte, that means that the value of byte in file differs from the value of byte in memory. So in very simple terms, it means that though we have sent 0f, but it got translated to a4. Similarly, we had sent 14, that is 14, and it has got translated to b6, and 15 has got translated to A7. And similarly, if you see 80 to FF onwards, these bytes have also been translated into different bytes. So that means that we have a very limited set of buffer, which is from 01 to 7F, and even between that, some characters are bad characters for us. Now let's move to the next step of bad character analysis, which is finding the true bad characters from this list of characters which we have currently excluded from our byte array. So we'll do that one byte at a time, and what we'll do is that from a list of bad characters, we'll first remove this byte and then see how the application responds. And if the application does not consider it to be a bad character, we will then completely remove this character from our list of bad characters, and we'll repeat the same process for all of these characters until we identify a set of true bad characters from this list of characters. Now I know this is going to be a repetitive process, and I'll do this process for these 3 bytes. For the remaining character set, consider this as an exercise to do it on your own. Just repeat the process what we will be doing for these 3 characters for the remaining set of characters, and you'll identify true bad characters. And if you have any troubles, please shoot a question in Q&A section. Let's get started with the process. To do that, I'll go to WinDbg and restart the application and run the application. Run it twice and the application is running, so I'll move it aside for now, and let's generate a new set of byte array. And now I don't want 7C to be included in a set of bad characters, so I'm removing it, and now I'll press enter. So you can see that a new set of byte array has been generated, and this time 11 bad characters have been excluded. So let's go to Notepad++, and yes, to reload the file, let's copy this byte array, and this is of 245 bytes in size, so we need to fix our buffer accordingly. And I'll save it, and here, since we have an additional byte in this, let's remove a byte from here and we'll make it 24. Now I'll recommend that you remove the bytes from this portion of the buffer and do not touch this buffer, because if you do so, your memory address from where byte array starts will change. To show you what I mean, let's keep it at 25 and let's change this to 24, and now I'll save it. Let's generate a new POC zip file, and now let's open this in our application. And I'll double click on this file, so you can see that application has crashed. Let's pass the exception to the program and let's step into it. And now if I scroll up and let's see the memory address at which our byte array starts, you can see that this time it starts from 0012FAEE, and the last time when we did this process, it started from 0012FAEF. Now usually this is not much of significance, but in this case, since we are using a memory address to compare, it becomes really convenient if this memory address does not change with every change in a buffer. So I recommend that you don't change bytes from this part of the buffer. Rather, if you want to remove or add any bytes to your buffer, to do it from this part. And this recommendation is for this specific exploit only. With other exploits, conditions might vary and so might your preference. So anyways, let's continue with our process and let's compare this byte array with our byte array.bin, and we'll need to change this memory address to EE as it is shown here, and let's press enter, and let me put an F here. If I don't, it will again give me an error, and now let's press enter. So you can see that again it says that corruption, or rather the first corruption has occurred after 12 bytes, and let's go to log window to see it in more detail. So you can see that these lines will be more or less same as they were the last time. So this time we had included 7c in our byte array. So let's see if that character has made an intact, and there is no byte in memory row. So that means that value of 7c in file and value of 7c in memory is same. So that means that 7c is not a bad character. Now let's repeat this process for the next character. Let's restart the application. Run it. Press play twice. And now let's generate a new byte array. And this time we'll remove 7c and 3e. And let's open this file in Notepad++. Yes, we want to reload this. And let's copy this. This time the size of this byte array is 246 bytes. So let's paste it here. And as I said that we should not touch this part to keep the memory address static. So let's restore it to 25 and make changes in this portion of the buffer. So we need to remove 2 bytes from here and it will become 23. And now let's generate a new POC zip file and let's open it in quickzip.exe. Double click on it, double click on the file name, and it has triggered the crash. Let's pass this exception to the debugger using Shift F9, and we have hit the breakpoint at pop-up return instructions. Let's step into it one by one, and let's navigate up to our byte array. Or even without navigation, you can just issue this command, mona compare byte array.bin and this memory address, because this memory address is static, so you don't need to check this memory address every time. And it again says that corruption starts after 12 bytes, which we already know. And this time we had sent it the character 3e. So as you can see that 3e has also made it as is in the memory, because there is no other value in the memory row. So that means that 3e is also not a bad character for us. So let's continue this process and let's first restart this application and run it. And I'll press play to move from the breakpoints. And let's generate a new byte array now with these 3 characters removed, which is 7c, 3e and 3c. And I'll press enter. So a new byte array has been generated. And you can see that the size of this byte array is 247 bytes. So let's open this file in Notepad++, and it's already open, so we'll reload it. And let's copy it and paste this into our zip poc.python file. And let's remove one more byte from here to make it a total size of 294 bytes. And let's generate a new POC zip file. And now let's open this zip file in quickzip.exe. Now I'll double click on this file. So you can see that again application has crashed. I'm passing this exception to the debugger using Shift F9. And let's just step into our pop-up return instructions. And this time I won't navigate back to our byte array. I'll just issue the command mona compare. And let's see if it works or not. So again it is giving me the same error using valid file name, and looks like I have again forgot to specify the -f option. So silly of me, but never mind. Silly mistakes happen often in the tech world. So I'll press enter now. And let's go to our log window, and you can see that this table is same. And let's see if 3c has also made it intact. So 3c has also made it as is. because there is no other value in memory row. So that means that 3C is also not a bad character. Now I'm going to stop this process here. I'll continue it off camera. I recommend that you do this as an exercise and try to figure out which are the two bad characters. So if you need to pause the video and continue the process, please feel free to do that and move on to the next part only when you have found out the true bad characters. So I hope you have finished this exercise, and I also hope that you were able to identify the true bad characters in that range, which were 2F, 3A and 5C. And this is the entire list of bad characters for this application. Now let's see one by one why these characters are bad for this application. First three I've already told you. Let's move to 0F. And as we saw in the Mona compare results table, that 0F gets translated to A4 and 2F also gets translated to 5C. This you should have found out as part of your exercise. Similarly, 3A, which is colon, freezes quickzip.exe if it is part of a buffer. Again, this is something you'll notice if you do the exercise. Then moving on to 5C, this again is not allowed in file names and it changes the meaning of the path that we had sent to the application. And this is also something you will observe as part of the exercise. Next is 1.4 and 1.5. These are again, as we saw in the Mona compare result table, they get translated into B6 and A7 respectively. And then finally, all characters from hex 80 to hex FF get translated to other characters. Now here I would advise you to keep this comparison results table handy, because in the next part of this module we will take advantage of some of these character translations, as some of these bytes translate into valid instruction set that we will use as part of our payload shellcode. So for now, just keep this file handy. You may want to navigate to the Mona directory if you have created this, or wherever your Mona working directory is set to be, and copy this file compare.txt and place it on the desktop for future reference. So this will ensure that this file is not overwritten by any other experiments that you might do apart from this module, and also we can easily access it whenever we need to. So we'll do that in the next part of this module. That was it for this video. These are the few learning resources you can use to learn more about the tools, techniques and software that we are using in this module. Thank you for watching this video, and I'll see you in the next part. Hello and welcome to part 6 of acrobatics module. These are the few assumptions that I'm working with. I'm assuming that you have a prerequisite or basic knowledge of following tools and software. If you don't, please check out the resources mentioned at the end of this video. This is our module structure and we are on cracking the shell. Usually in our previous modules, when we land on this part of the module, we are very close to obtaining the shell from the target machine. However, in this particular exploit, we are still a few miles away from obtaining a shell. If you remember this slide from the first part of this module, so I promised you that we will be covering all of these things in this module. So far, we have covered till SCH overwrite, and we have also figured out that we need to use egg hunters, but we have not yet either generated the egg hunter or encoded the egg hunter. So all the remaining steps from egg hunter to automated alphanumeric encoding we will be covering in this part of the module. So it is going to be a bit longer part, and as you will come to know in a minute that I have divided this part into few subparts. So moving along, now what is it that remains to be done to get a full working exploit? So we have found out the bad characters, because without bad character analysis we were not able to take a short jump back. So the first step here is to take a short jump back, and we will be taking a short jump back of 55 bytes, and after taking the short jump we will take a long jump back of around 250 bytes. Now because of the character set limitations, we will not be able to take this long jump directly. Instead, we will have to carve out the opcodes of this long jump on a stack and then execute those opcodes to take the long jump. Now in order to carve out this long jump, we'll first need to pivot our stack to a memory location wherein we want to start carving out, and then we'll finally carve out the opcodes for long jump, and after that we'll start stack pivoting to carve out the egg hunter, and then we will take a long jump back of 250 bytes. And then once we have taken that long jump, we will complete our stack pivoting to carve out egg hunter, and then carve out the egg hunter on the stack itself, and then finally execute the egg hunter, jump to our payload shellcode and execute the payload shellcode. Now in this entire process, we will be doing two kinds of encoding. As we saw earlier, we will be manually encoding the egg hunter, and we will be using alpha 2 encoder to encode our final payload shellcode. Now I could also encode the egg hunter using alpha 2 encoder, but in this module I wanted to show you the techniques of manually encoding shellcode in case you ever need to do that. So how do we handle all this? I know this could be a lot of things to do in just one video, and that would make it a really complicated and long video, and that is something I want to avoid. So I want this process to be as simple as possible for you to follow and understand. So the simple answer to this is to divide and conquer. And what do I mean by this is that we'll break down this execution flow into smaller building blocks and then work on one block at a time. So I've divided this entire process into 4 blocks, and this essentially means that we will at least have 4 videos covering each of these blocks. Some of the blocks, for example egg hunter, might flow into 2 videos. So if you're feeling overwhelmed by what we have just covered, just take a deep breath, relax, and follow along with me. In this video, we will cover the first building block, which is the short jump. So for now, I want you to forget about all the remaining building blocks and focus on just the first building block, which is the short jump. So in part 4, when we tried to do a short jump, we failed miserably because the opcode for short jump which we have tried, which was EB80, got translated into some other bytes, and hence it changed the meaning of our shellcode. And if you want to check what these bytes got translated to, just open the compare.txt that we had created in the last part and saved it on our desktop, at least in my case. You can open this file from wherever you have saved it and just refer to this table. So we had sent EB80. So let's search for EB here, and this is EB, and it got translated to 64, and here is 80, which got translated to C7, and obviously these are not the opcodes for jump instruction. So what choice do we have now? Luckily for us, we can use a pair of conditional jumps to take this short jump. What I mean by that, I will get to it in a minute, but first let's understand how we came to this value of 55 bytes. So essentially you can use any other value instead of 55 bytes, provided you are able to find the right opcode in this table. But please note that if you choose any value other than 55 bytes, any subsequent calculations that we will do from here onwards will vary according to the value that we have selected. So if you want to follow along with me, I suggest that you stick to 55 bytes and you can try other values once you're through with this module and understand what we are doing and why we are doing that. The two criteria I had while choosing this value of 55 bytes is that it is convenient, and the second criteria was that it is sufficient space to carve out the long jump. So we'll need around 40 bytes to carve out the long jump, and 55 bytes is more than sufficient for that. Now why this value of 55 bytes is convenient to us? To find that out, let's go back and remember that we had sent EB80 as short jump opcodes to the application initially, and the 80 part got translated to C7, and the C7 value corresponds to 55 bytes. Now how I work that out? To explain that, I'll go to my Kali machine and let's launch a terminal, and in a terminal let's launch msf nasm underscore shell, and here let's find out the opcodes for our initial jump, which was jump $-126, and the opcodes for this jump are EB80. And now let's say if I reduce this value to 125, it becomes EB81, and similarly if I further reduce it to 124, it becomes EB82, and 123 becomes EB83. So that means that as I'm reducing the value of the bytes here, the value of the second opcode is increasing. That will correspond to the second opcode being C7. To find out what is the value of that byte, open a calculator and let's put it in hex mode, and here let's subtract 80 from C7. So I'll put C7 minus 80, and this comes out to be 47 in hex, and if I want to see this value in decimal, it comes out to be 71. So now if I subtract 71 from 126, it will give me 55 bytes. So now if I write jump $-55, it will give me C7. So as I said, that for me using this value of 55 was convenient, because then I can use the second part of opcode which gets translated into C7. So now I don't have to go back to this table and find out what other value I can specify. Of course, if you prefer to choose any other value, you can find that out from this table. But for me, this was a really convenient option, so I went with 55 bytes. Now moving on to what I meant by using conditional jumps. So let's go to my Kali machine, and here I have this page open. So x86 assembly provides a variety of conditional jumps, and these jumps are taken based on the value of the corresponding flag. Now what I mean by this is, let's say we want to take a jump based on the value of the 0 flag. Now the value of 0 flag will be 1 either when the condition that we are testing is equal or it is 0. So in this case, this jump will be taken. And similarly, let's say if I want to take a jump if the value of 0 flag is 0, and that will happen either when the value that we are comparing are not equal or they are not 0. So in this case, the instructions are JE or JZ for equal and 0 respectively, and JNE and JNZ for not equal or not 0 respectively. Another thing I would like you to observe here are the short jump opcodes for these jumps. Now as you can see that starting from here till here, all these opcodes lie in the allowed character set for quickzip.exe. So what that means is that we can use any of these jumps to take a short jump based on the value of the corresponding flag. Now in an exploit, when we are using conditional jumps, it is advised to use a pair of complementary conditional jumps. What I mean by that is, let's say we decide to use this jump JZ, which is jump if 0, and this jump will be taken if the value of 0 flag is 1. Then we should also use this complementary jump, which is JNZ, that is jump if not 0, which means that the value of 0 flag is 0. So by using complementary jumps in this manner, it will be ensured that the jump is taken irrespective of the current value of this flag. I hope that explanation was clear. If not, go through the explanation once again. And if you still have any questions, please reach out to me in Q&A section or the Discord channel for this course. So for this module, we will be using this set of complementary jumps for which the opcodes are 74 and 75. So let's go back to Nazm shell and write jz, that is jump if 0 $-55, and the opcode for it is 74C7, and jnz $-55, and the opcode for it is 75C7. So let me just copy these 4 lines, and now let's move back to our POC, and we can remove this short jump here because it did not work for us, and paste these 4 lines, and I'll convert them into comments. So this is just for a reference in case we ever need to figure out what a particular piece of shellcode is doing. And now we'll specify these values in place of these values which overwrite NSEH. And remember that instead of C7, we will be using 80 as the opcode here, because as we saw here that 80 gets translated into C7. So this segment of shellcode will look something like this. We'll write here 7480 and then 7580. Alright, let me save it, and now let's generate a new POC zip file. Go to my desktop and run python zip poc.py. So the new zip POC file has been generated. Now let's open WinDbg and in it launch quickzip.exe. Let's run it and press play twice to move from a breakpoint, and let me move this window to the side. Now I'll open the POC zip file, which is this, and now I'll double click on this file name. You can see that application has crashed and an access violation has been triggered. Let's pass this exception to the debugger using Shift F9. So we have hit a breakpoint at pop-up return instructions, and if we just step into it, you can see that now our opcodes at NSEH have got translated into conditional short jumps, which are jump if equal to 0 and jump if not 0. So now irrespective of the value of 0 flag here, this jump will be taken. What I mean by that is that if the value of 0 flag is 1, this jump will be taken, and if it is 0, then this jump will be taken. So in either case, we will jump 55 bytes backwards from this position. And you can see here that it also says that because the value of 0 flag is 1, this jump will be taken. So let's step into it. And now you can see that we have landed 55 bytes backwards into a buffer. Now these instructions are part of the byte array that we had sent here. So what I'll do here is I'll remove this byte array, and here let's remove all this and make it a value of 294 as it was earlier. We will change this value again in the subsequent videos, but for now do not worry about that. So now since our short jump is working and we have 55 bytes of buffer to carve out our long jump, let's get to the next building block, which is the long jump of 250 bytes, and this is something we'll see in the next video. These are the few learning resources you can use to learn more about the tools and techniques that we are using in this module. Thank you for watching this video, and I'll see you in the next video. Hello and welcome to part 6 of acrobatics module. In the last video, we covered the first building block for this part, that is the short jump, And now let's move on to the second building block, that is carving out the long jump and then finally taking that long jump. To help you understand better what we have done so far and what we are going to do, I have made a visual representation here. So you can see that this is the application stack and this is the portion of the buffer that is controlled by us or that is owned by us. Now so far we have landed on NaCH, and then from here we have taken a short jump of 55 bytes, and at present we are on this part of the buffer. Now our next step is to first align the stack pointer to this portion of the buffer so that we can carve out the long jump. And once we have successfully carved out the long jump, we will start aligning ESP to this portion of the buffer to carve out our egg hunter. But for now, don't worry about that. This is something we'll cover in the next video. And then finally, we'll take the long jump and jump to this portion of the buffer which is of 250 bytes. So that is all we are going to do in this video. For remaining blocks, do not worry about that at present. We'll cover them as and when the time comes. So why we have chosen 250 bytes for our long jump? Because it is sufficient space to carve out egg hunter, and we'll need around 173 bytes plus 32 bytes, that is a total of 205 bytes to store our encoded egg hunter, and then finally the decoded egg hunter which is of 32 bytes. Now you can use any other value besides 250 bytes, only make sure that it is sufficient to store the encoded as well as decoded egg hunter. And also note that if you choose any other value apart from 250 bytes, any subsequent calculations that we will do from here onwards will vary. So for now, I would recommend that you stick with 250 bytes and follow along with me. Now, as we saw previously, that there are three parts to our code. First is to align ESP to this portion of the buffer and then carve out the long jump. And then finally, the third part of the code is to start the alignment of ESP for carving out egg hunter. So that is how I divided this code here. Now I will not go into the explanation of this code on this slide. I will explain it as and when we execute it, because there are some calculations that you will understand only when we are executing this code. Also, if you need a refresher on stack pivoting, do check out the fifth part of the second module of this course, which covers and explains the concept of stack pivoting. So now let's move to the lab. So this is the POC that we had created so far. And before we go ahead and include the next part of shellcode in our payload, let's first see what are the opcodes for the long jump that we need to carve out. So to do that, I'll go to my Kali machine and launch terminal. And here let's launch msf nasm_shell. And now let's see what are the opcodes for that long jump of 250 bytes backwards. So to find that out, I'll specify jump $-250. So this means that we want to jump 250 bytes backwards from the current position. And as you can see that the opcode for this long jump are E901FFFFFF. So let's just copy this and go back to our Windows XP machine. And in our POC, let's put another comment here to include this long jump. This is again for reference in case we need to debug our code and we need to identify what a particular piece of code is doing. Now I'll go ahead and copy this shell code for carving out the long jump and include it in our payload. Now, so I'll put double quotes and include this shell code here. And now I'll give it a buffer of 10 A's. And now I'll need to reduce our total size of this part of the buffer from 294. So to find out the size of this shell code, you can select it and check here that it says that we have selected 136 character. Now each byte here is made up of 4 characters. So if you divide 136 by 4, it comes out to be 34. And if you add 10 to it, it becomes 44. So that means we need to minus 44 from it. So that gives us a value of 250. And now I'll save it. And before I go ahead and execute this code, we need to make another modification. I'm not sure if you have observed it in the slide so far. If you have, kudos to you. So let's go back to the slide, and here you'll notice that the opcode for pop ESP is 5C. And as we saw in part 5, that is bad character analysis, that 5C is a bad character for this application. So what do we do now? Luckily for us, the answer is there in the comparison table that we had saved from our bad character analysis. So I'll open that next. That table is in a text file on my desktop, which is this. So let's open it in Notepad++ itself. And here if you'll notice that the character to F gets translated to 5C. Now remember that we have also marked this character as bad character for our application, but that was precisely for the reason because it got translated to 5C. However, since now we need this 5C opcode, we can use this 2F character as part of our payload shellcode. So I'll go back to my POC, and here I'll replace 5C with 2F, which will essentially get translated to 5C when we execute this code. So now I'll save it, and now let's generate a new POC zip file. To do that, I'll go to my terminal and write python zip poc.py, and it has generated the new POC zip file. Let me minimize it, and now I'll open Unity debugger, and in it I'll launch quickzip.exe. We run this application. So our application is running. Let me move it down here, and let's open the POC zip file. And now I'll double click on this file to trigger the crash. So our application has crashed. Now I'll pass this exception to the program using Shift F9. So now we have hit our breakpoint at pop-up return instructions. Let's just step into it. Now we have landed on our short jump. Let's take this short jump of 55 bytes. And now we are on this portion of the buffer. So let me just step into it and come to our shellcode. So now let's take the first part of our code, which is this, wherein we are aligning ESP for the long jump. And let's go through it instruction by instruction. So here we are pushing the current value of ESP, which is this, onto the stack. So you can see that this value is now on stack, and then let's pop this value into EAX. So you can see that this value is now stored in EAX. Now we could have done this easily using move instruction, but in our case the opcodes for move instruction lie in the bad characters. Just let me quickly demonstrate that. And here if I'll write move EAX ESP, so you can see that opcodes for this instruction are 8B C4, which as we saw earlier are bad characters for this application. So hence we cannot use this instruction. So anyways, and now we need to move the stack pointer to a location in this region of the buffer. Now to do that, I need to add certain value to this value of AX to make it lie in this region of the buffer, and that is why I'm adding 063B to AX to make it equal to 1 to FB, which is this location. Now I'll finally push this value on stack and then pop it in ESP. So you can see that our ESP now points to 1 to FB, which is this location. And now we'll start carving out a long jump from here onwards. Now do remember that stack grows in the upward direction, that is from the higher memory address to the lower memory address. That is why we'll have to carve out this part of the long jump first and then this part. So let's do that. Now in order to carve out this portion, which is FF onto the stack, I'll again need to add certain value to this value of AX to make it equal to FF. So now if I open my calculator and let's put it in hex mode and let's put the value FF, and from that let's minus FB. So that gives us a value of 0404. So that means that if we add 0404 to the value of AX, it will become FF, and that is what we are doing in the next instruction, which is add AX 0404. So now you can see that the value of AX has become FF, and now we push it twice on the stack because we have 3 FF bytes here, 1, 2, 3, and pushing it twice will give us 4 FF bytes on the stack, which is more than sufficient for our purpose. So you can see that 4 FF bytes have been carved out on the stack. And next we need to carve out this portion of the long jump onto the stack, and in order to do that we'll have to first make the value of AX equal to 01E9. Now do note that we are not making AX equal to E901. Instead we are making it equal to 01E9. Now this is because of the little endian format used by Intel processors. Now in order to make the value of AX equal to 01E9, we'll now need to subtract certain value from FF, and now let's check what that value will be. To do that, I'll go to calculator and let me put value FF here, and now if I subtract 01E9 from this, I'll get FE16, but unfortunately we cannot use FE as it lies in the bad character range for our application. So if I divide it by 2, I'll get 7F0B. Now both of these characters or both of these bytes lie in the allowed character set for this application. So if we subtract 7F0B twice from this value of AX, we'll get 01E9 in AX. So let's do that by these two instructions. And as you can see that AX is now 01E9, and now we'll finally push AX onto the stack, and that completes the opcode for our long jump. And as you can see that these bytes have now combined to form a long jump of 250 bytes. Now to verify whether it's 250 bytes or not, let's again go to our calculator, and if we subtract this value from this value, it should give us 250. So let's do that. So I'll put 1 2 FB F5 minus 1 2 FA FB, which gives me FA, and if we see it in decimal, it gives us 250 bytes. Now the next two instructions start aligning the stack pointer to this portion of the buffer, and to do that we need to add certain values to AX. Do not worry about these values for now. This is something we'll cover in the next video, wherein we'll cover egg hunter. For now, let's just step into these two instructions and move on with our code. Now one thing I would like to mention here, and you might also be wondering that why have we put these two instructions here and not in the larger part of the buffer, and even if we have put them here, why we are doing it partially, why we are not doing the complete ESP alignment here. Now the answer to your first question is that because we had certain bytes available to us, I made use of this space to start the aligning process. And the answer to the second question, that is why can't we do full stack pointer alignment here, is that if we do any further stack operations, they will get written here in this portion of the buffer, and hence they will interfere with our long jump. So I hope that is clear. If not, please shoot out a question in the Q&A section or on the Discord channel for this course. I will be more than happy to address all your questions and queries. So moving on, let's step into these three instructions. And finally, we'll take our long jump and we'll land back to 50 byte, as you can see here. So that completes the second building block for this exploit. In the next video, we'll move on to the third building block, which is egg hunter, in which we'll cover manually encoding the egg hunter and finally carving it out onto the stack. So that's all for this video. These are the few learning resources you can use to learn more about the tools, techniques, and software we are using in this module. Thank you for watching this video, and I'll see you in the next video. Hello, and welcome to part 6 of Acrobatics module. In the last video, we worked on the second building block, that is long jump, and completed it as well. So now we have 2 building blocks completed and 2 are remaining for us to cover. In this video, we'll cover the third building block, which is egg hunter. Now, in order to complete this building block, we need to perform these following 4 steps, which are generate the egg hunter using mono library, and then manually encode it, then finally add the encoded egg hunter to the POC, and finally give it a test run. So let's start with the first step, which is generating the egg hunter using mono library. So let's go to the lab, and on my Windows XP machine, I'll launch WinDbg, and here I'll just issue the command mona egg, and I'll specify the egg or tag as YCSC. So you can see that Mona library has generated an egg hunter for me, which is of 32 bytes, as you can see here, and it's written in egghunter.txt. So let's go to our Mona working directory, which is C Mona, and let's open this file and copy the egg hunter. And you can also see here that it says that you need to put this tag in front of your shellcode. So that is YCSC YCSC. Now, if you need a refresher on egg hunters, do check out the first module of this course that explains the technique of egg hunters. So now I'll open my POC, which is this, and edit it with Notepad++. And then in the comments, for now I'll put the egg hunter here. Now our next step is to encode this egg hunter. Now why do we need to encode it? Because as you can see that there are certain bad characters which are part of this egg hunter, and we need to find a way so that we can tackle these bad characters without affecting the functionality of the egg hunter code. So that is our next step. Let's go back to our presentation. Now, in order to encode the egg hunter, we have a few challenges in front of us, and that is purely because of the limited character set. The first challenge is to choose the right CPU register, because opcodes for various operations on CPU registers might not lie in our allowed character set. So we need to choose that particular register whose operations opcode such as add, push, subtract, etc. lie in our allowed character set. The approach that we are going to take to tackle this challenge is to check opcodes for various register operations, and that is something we'll do in a lab in a bit. Our second challenge is to zero out registers. Now there are various techniques to zero out registers. The first is simply to move 0 bytes to a register, which obviously adds null bytes to your shellcode. So that is not a preferred technique. The second is to XOR the register with itself. Third is to subtract the register with itself. And another technique is to AND the register with two more or less complementary values. Now in our case, we'll need to choose that operation whose opcodes again lie in our allowed character set. Any other operation whose opcodes lie in the bad character set is invalid for us. So to tackle this challenge, we'll be using AND operation to zero out the registers, and we'll cover that in a minute as well. Our third challenge is to finally avoid bad characters from the egg hunter shell code, and we'll tackle this challenge by using add operation to avoid bad characters. Now I'll explain each of these approaches in detail in the following slides. So the first challenge that we need to tackle is to find the right CPU register for us, and to do that our approach is to check opcodes for various register operations, and as I said that is something we need to find out in the lab. So let's go to our Windows XP machine, and let me go to CPU window, and let's launch quickzip.exe. Now there is another way to do this. You can use MSF NASM shell in Kali Linux, but I don't want to keep juggling between these two machines right now. So I'm using Immunity Debugger, and essentially the process is same in both of the cases. So here select any instruction, and let's start out with EAX register, and let's see what opcodes are there for various operations on EAX register. So we'll start with add EAX, comma, let's put any random value which is 23, 23, 23. So as you can see here that the opcode for add EAX is 05, which lies in our allowed character set. Now let's check the opcode for subtract EAX. So we'll, instead of add, we'll write sub EAX and then the value, and let's assemble. Again, opcode for subtracting a value from EAX is 2D, which lies in our allowed character set. And let's check the opcode for subtract EAX from itself, and the opcode for it is 2B Now of course C0 lies in our bad character set, so we cannot use subtract EAX to zero out the register. Now let's check for XOR, and again you can see that the opcode for this is 33C0, and C0 lies in our bad character set, so we cannot use this instruction as well. So if we do AND EAX with some random value, let's see what the opcode for that is. So you can see that opcode for it is 25, which lies in our allowed character set, so we can use this operation. And finally let's check push EAX. So the opcode for it is 50, which again lies in our allowed character set. And by the way, we have been using push EAX as part of our stack pivoting, so we can anyways use this instruction of push EAX. Similarly, you can check opcodes for other registers as well by assembling the relevant instructions here. And if we do that for, let's say, EBX, so let's start with push EBX. You can see that this opcode lies in 53. So right now it seems that we can also use push EBX, but let's see what happens for other operations. Let's say we do add EBX and add a random value to it. So the opcode for it is 81C3, and both of these characters lie in the bad character set, so we cannot use EBX to add something to it. And since we cannot use EBX to add something, so that rules out the possibility of using EBX in our encoding shellcode. Similarly, if we check ECX, the opcodes for this is 81C1, and again these lie in our bad character set, so that rules out ECX as well. And if I check EDX, the opcodes for it are 81C2, which again lie in the bad character set, so we cannot use EDX as well. So looks like EX is the only choice for this particular exploit, and since we can do almost all of our required operations using EX, so we are going to select EX as our chosen register. So let's go back to the presentation, and here as we just saw that we have selected EX as our chosen register, and the opcodes for various operations on EX are for AND it's 25, which lies in our allowed character set. For add EX it's 05. or rather the opcode for adding a value to EAX is 05, and then opcode for push EAX is 50, and all of these characters lie in our allowed character set, so we can use them. So let's move on to our next challenge, which was to zero out the registers. And as we saw in the lab earlier, that apart from AND, we cannot use any other approach because the opcodes for those operations lie in our bad character set. So our only choice for this particular exploit is using AND operation to zero out the registers. A quick trick to zero out a register using AND operation is to AND the register twice with two almost complementary values. Now, how do you find those two values? So the trick for that is to select a series of 4 hex characters between 000000 and 7F, 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 7F. Now we have selected this range because this range lies in our allowed character set. So you choose a series of 4 hex bytes between this range. These could be any 4 hex bytes. Just ensure that the bytes that you have chosen do not contain any bad characters that lie in this range, which are 00, 0A, 0D, 0F, 3A and 5C, as you can see here. And 14 and 15 are also bad characters in this range. So we need to avoid these while choosing that series of 4 bytes. You can also select a single byte, let's say 2C, and then use it 4 times. So your series of 4 bytes in that case becomes 2C, 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 2C. And then the next step is to subtract the selected series from 7F, 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 and that will give you more or less complementary numbers. And when you perform AND operation on the selected CPU register, which is EAX, once with each of these two series of bytes, it will result in the register being zeroed out. Let's see a demonstration in the lab. So let's first move a value in EAX, and let me move a random value of I can move any 4 values, so let be 34, 67, E3 and 4E. Alright, and let me move the origin to this instruction. And now we'll perform the AND operation with the first series of 4 bytes. So we'll do AND EAX, and the first series of 4 bytes be 23, 43, 12 and 10. Alright, let me just copy it quickly and I'll press assemble. Now we'll find the complementary of this using calculator, and as I said that in order to find the next series of 4 bytes, we need to subtract this value from 7F, 7F, 7F and 7F. So I'll write 7, so let me put it in hex mode first. Now I'll write 7F, 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 7F minus this value, and this is equal to 5C, 3C, 6D, 6F. Now do note that we have 5C in this series. So if you are going to choose these two values, ensure that you replace 5C with 2F, which will get translated to 5C during the runtime of the application. Now I'll copy it, edit, copy, and here I'll paste the series of 4 bytes, which is 5C, 3C, 6D, 6F, and I'll press assemble, and let's press cancel to close this window. So now you can see that I have 3 instructions here. First is moving a random value to EAX, and then we are performing 2 AND operations on EAX using complementary numbers. So I'll step into it. So you can see that value of EAX is 34, 67, E3 and 4E, and now we'll AND it with the first series of 4 bytes, which gives us this value, and now AND this value with the second series of 4 bytes, which results in EAX being 0 out. Great. So as I said that you can choose any set of 4 bytes in the allowed character set. However, to make the process simple, just select a single byte and then repeat it 4 times. So let's say if we redo this operation, and let me first move the origin here, and let's redo this operation using 2c as the selected byte, and we'll repeat it 4 times, and I'll press assemble. And now to find out the other series of 4 bytes, we'll go to our calculator and subtract 2c from 7f, 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 and 7f, and from that 2c, 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 and let's press enter to find out the result, which is 5353 5353. And let me copy it and I'll paste this here. Let's reassemble the instruction. So you can see that these two instructions have now changed to reflect our selected series of 4 bytes. So let's step into these instructions again, and as you can see that this value has moved into EAX. So let's perform our first AND operation using 2c, 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 and it gives us this value. And now let's perform the next AND operation using 5353 5353, which results in EAX being 0 out. So why does this approach work? Can you take a guess and explain the logic behind this approach? If not, don't worry, just follow along with me. So to find that out, let's open our calculator. And in order to explain, I'm just going to use 2 bytes instead of 4 bytes each. So let's pick the first 2 bytes from our selected random number that we moved into EX, which are 3, 4, 6, 7, and let's convert it to binary. Let me copy it and let's paste it in Notepad. Let me clear this out. Let's move to hex, and now let's see binary representation for a series of 2c bytes. So 2c, 2c, and again I'm choosing 2 bytes here because I'm working with 2 bytes in this case, as I just explained. And let's move to binary to check its binary representation and copy it, and let's paste it here. And now let's do the same thing for 53, which is the complementary of 2c, 353, and let's see the binary representation of this. Copy it and paste it here, and just let me make a quick change here. It seems that calculator has not put a 0 here, so let's put a 0, and now these 2 bytes are equal in size. Now if you closely observe this number, and if I invert the individual bits of this number, I will get this number. In this case, this bit has not been inverted, but do not worry about that, because even though they are complementary, but they are not true complementary. Had it been true complementary, then the total sum of these two series of bytes would be FFFF. But in our case, this does not affect the functionality of our case, so that is why I said that they are almost complementary. And now let's perform an AND operation on this number using each of these series. So first I'll again need to pad it with 0 to make it equal size. And now let's perform the AND operation. So 0 and 0 gives me 0, 1 and 1 gives me 1, 1 and 0 gives me 0, 0 and 1 gives me 0, 1 and 1 gives me 1, then we have 3 zeros, then 1 and 0 which give me 0, then 1 and 1 which will give me 1, 0 0 will give me 0, 0 and 1 will give me 0, 1 and 1 will give me 1, and then 1 and 0 and 1 and 0 will give me 0 0. And now if I perform an AND operation on this result with the next series of 2 bytes, or with the next series of these bits, which essentially represent 5353, let's see what we get. So 0 and 1 is 0, 1 and 0 is 0, 0 and 1 is 0, 0 and 0 is 0, similarly 1 and 0 is 0, and then 0 and 1 is 0, 0 and 1 is 0, 0 and 0 is 0, then 0 and 1 is 0, 1 and 0 is 0, 0 and 1 is 0, 0 and 0 is 0, similarly 1 and 0 is 0, and then 0 and 1 is 0, and then 0 and 1 is 0. So as you can see that the second AND operation resulted in all bits being converted to 0. So that is why this approach worked, and that was the logic behind that. These two numbers, or the series of 4 bytes that we choose, or the two series of 4 bytes that we choose, are more or less complementary, and hence they result in a value of 0 when we perform AND operation on a value with each of these series. So if it is sounding a bit complicated, I recommend that you try doing this exercise on your own, and that way you will be able to understand it better. So let's move back to our presentation. So we have just seen that why does this approach work, and I hope you're comfortable with the explanation. And as I said that if you're not, do try this exercise on your own. That way things will get more clear to you once you do this by hand. And if you still have any questions, do reach out to me in the Q&A sections or on the Discord channel of this course. So for this module, I have selected a series of 4 2C bytes, and then as we saw that almost complementary for it are a series of 4 5-3 bytes. So our resulting instructions here become AND EAX with 2C 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 2C, and AND EAX with 53 53 53 53, and the resulting shellcode for this is 25 2C 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 and 25 53 53 53 53, which comes out to be a total of 10 bytes. So make a note of this shellcode. We will be needing it a lot in tackling our next challenge. Our next challenge was to avoid bad characters from our egg hunter shellcode, and the approach that we had selected to tackle that challenge was to use add operation to avoid bad characters. Now essentially what we are going to do is we are going to divide a 32-byte egg hunter into blocks of 4, so that will give us 8 blocks of 4 bytes each, and then we will push each of these blocks individually onto the stack to carve out our egg hunter shellcode. Now obviously, because each of these blocks will contain characters which lie in the bad character set, we will need to divide that block of 4 bytes into a 2 or 3 series of 4 bytes each, such that the sum of each corresponding series will result in the value of the block. If it sounds too complicated, just take a deep breath, relax, and follow along with me as usual. In order to encode our egg hunter, and using our approach, we'll need to take certain preparatory steps, which are first divide the egg hunter shellcode into blocks of 4 bytes each, and then we will reverse each block to comply with the little endian format, and then finally we'll start encoding from the last block to comply with the stack direction. So remember that the stack grows from the high memory address to low memory address. So we'll need to put the last block of egg hunter shellcode first, and then the second last, then the third last, and so on till the first block. Now let's see how we are going to divide each of these blocks into 2 or 3 series of 4 bytes each, such that the sum of each series will result in the value of the block. So I've made a quick algorithm for it. A first step is to check if all the bytes in that particular block lie in our allowed character set. If they are, we do not need to divide them into further series of 4 bytes. We can just add those bytes to the CPU register, which is EAX, and then push them to the stack. However, if those bytes do not lie in our allowed character set, we need to check if the block can be divided by 2 and if it is a fair division. Now by fair division, I here mean that the division should not leave a remainder, and the resulting series of 4 bytes should not contain any bad characters. So only when these two conditions are met, we will consider that division as a fair division. So if the division by 2 results in a fair division, we will then add that series twice to EAX and then push to stack. However, if division by 2 does not result in a fair division, we divide the block by 3 and then again check whether it's a fair division or not. And again here the requirements for fair division are that it should not contain bad characters and it should not leave behind a remainder. So if after dividing by 3 we do get a fair division, We add those series of bytes thrice to EAX and then push the value to the stack. However, even after dividing by 3, if we don't get a fair division, we divide each individual byte by 2 or 3 and then adjust the resulting bytes in such a way that we get 2 or 3 series of bytes which do not contain any bad characters, and their total results in the value of the block. And once we have that, we add those series to EAX and push them to stack. So here, if we are dividing each individual byte by 2, we'll get 2 series of 4 bytes each. So we need to do this add operation twice. And if we are dividing each byte with 3, then we'll get 3 series of 4 bytes each, and we need to perform this add operation thrice and then finally push the value of EAX to the stack. So this is a quick algorithm that I'm going to follow to encode each of these blocks. Now remember that we have 8 blocks, so I'm going to cover 4 blocks with you, and for the remaining 4 blocks you will have to do this exercise on your own and find out the resulting series of 4 bytes and then match your results with the value shown in this presentation. And this presentation is part of course files, so you can download it from there. So let's start with our preparatory steps. So you can see that this is our egg hunter and the egg is YCSC, and this total shell code is of 32 bytes. So our first task is to divide this into blocks of 4 bytes each. So this is what we get after dividing this 32 byte egg hunter shell code into 8 blocks of 4 bytes each. And then our next task was to reverse each of these blocks. So if you match to the value here is just the reverse of this particular block, and similarly the value here is the reverse of this block, and so on. And finally, in order to divide each of these blocks into corresponding series of 4 bytes each, we'll start with the last block, which is this. So I've numbered these blocks. So this is block 8, 7, 6, 5, 4, 3, 2 and 1. So we'll start with block 8. So as you can see here that the block 8 contains 4 bytes which are E7, FF, E7 and 75. So first test was to check if all bytes in this block are in allowed character set, which they are not because E7, FF and E7 are in the bad character range. So hence this test has failed. So let's move on to the next test, which was divide by 2. So if I divide this value by 2, I'll get 73 FF, F3 and BA, and if I add these two, I'll get E7 FF, E7 74. You can verify this calculation using a calculator in hex mode. I'm not going to do that here. If you want to verify these calculations, you can do them on your own, and in case you come across any discrepancy, do let me know. I will change the slides accordingly. So moving on, now the sum of these two series of 4 bytes is E7 FF, E7 and 74. Now if you compare this with our block, you can see that the last byte is 75 in our block, but in this case it's 74. So this division is with remainder, and it also contains bad characters which are FF, F3 and BA. So let's move on to the next test, which was divide by 3. So now if I divide this block by 3, I get this set as the resulting value, and since I have divided by 3, so I get 3 sets of same value, and the sum of this set is E7 FF E7 75, which matches the value of our block. And if you see the series of 4 bytes which are 4D, 55, 4D and 27, each of these lie in our allowed character set, so we can definitely use these series of 4 bytes each to encode this block. So all we need to do is then add this series 3 times to EAX, and it will result in this value. And the resulting shellcode for this is mentioned here. Now do note that I have prepended this shellcode, the 10 byte shellcode, to zero out EAX register. So this is AND 2C 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 2C, then AND 53 53 53 53, and then I'm adding this value to EAX thrice, and then finally pushing it to stack. So let's move on to the next block. So I'm skipping 7, 6, and I'm taking 5. 7 and 6 you need to do on your own, and then match your results with the values mentioned in the presentation. So in block 5 we have bytes 43, 59, B8 and EF. So our first test is to check if each of these bytes lie in our allowed character set, which they don't because B8 and EF lie in the bad character range, so this test fails. Our next test is to divide this value by 2, and the resulting series of 4 bytes are 21 AC DC 77, and if you add these two series, the resulting value will be this, and if we match this with the block, you'll see that the last byte here is EE and the last byte here is EF. That means that this division is with remainder and it also contains bad characters. So again, we are not going to choose this. Now let's divide this by 3. So we'll get a series of 4 bytes which are 16, 73, 3D, A5, and if we add these three series, we'll get the resulting value of 43, 59, B8, EF, which is equal to the block value. However, do note that this contains A5 which lies in the bad character range, so we cannot choose this value as well. Let's move to our next test, which was to divide each individual byte by 2 and then adjust them accordingly so that we get two series of 4 bytes each, such that their resulting sum is equal to the value of the block, which is this. So I've taken each of these bytes and divided them by 2. So if I divide 43 by 2 in calculator in hex mode, I'll get 21. So I've put 21 here, and now in order to make this value 43, I need to put 22 here. So that is what I meant when I said that adjusting each value in such a way that their sum will result in a total value which is equal to the value of the block. So if you see that we have adjusted these 2 bytes in such a way that their sum will result in 43. And similarly, if you come to the next byte, which is 59 here, again if you divide this by 2 in hex mode, you get 2C, and in order to make it equal to 59, you need to add 2D to it. So again we have adjusted this byte so that the resulting sum of these 2 bytes is 59. And similarly, if you divide B8 by 2, you'll get 5C, and in this case there was no adjustment required, so that is why you are seeing 5C 5C here. However, in the next byte, which is EF, if you divide it by 2 in hex mode, you'll get 77, and you need to add 78 to it to make it equal to EF. So that means that now we have two series of 4 bytes each adjusted in a manner such that their sum is equal to the value of the block, which is this. Now do note that in this case these series contain 5C, which is a bad character for us. However, as we saw earlier in the comparison table, here you can see that 2F gets translated to 5C. So if we need to send 5C to the application, we need to put 2F here instead of 5C. So that is what our shellcode reflects, and here instead of 5C I have put 2F, which will essentially get translated into 5C. So you can also take advantage of such character translations in case you come across such bytes while encoding a block. So now the resulting shellcode for it is this, which is of 21 bytes, and again it includes a 10 byte shellcode to zero out the EAX register, and then finally we add these two series to EAX and then finally push it to stack. So let's move on to the next block, which is block 4. So the first test here is to check if each of these bytes lie in our allowed character set. In this case, all of these bytes lie in our allowed character set, so we need not perform any other test on that, and we can just add this value to EAX and then push it to stack. That is what we have done here, and the resulting shellcode is 16 bytes. So we have first put 10 byte shellcode to zero out EAX register, and then finally adding this value to EAX and then pushing it to stack. So let's move on to another block. Block 3 is left as an exercise to you, and so is 2. So now finally let's tackle block 1, which is FFCA8166. So our first test, which is to test if each of these bytes lie in our allowed character set, fails because of FFCA, so we cannot use this as is. Let's divide it by 2 and we'll get the resulting values as 7F E540B3, which do give us this value, which is same as block. But do note that the series contains E5 and B3, and these are the characters which lie in the bad character set, so we cannot use this series. So let's move on to our next test, which is divide by 3, and this is the result that we get if we divide by 3, and if we add these three series, our final value is FFCA8165. And if you match this last byte with this, it's not matching. So that means that this division is with remainder, and since it also contains 80, so this division is also with bad characters. So let's move on to the next test, which is divide each individual byte by 2 and then adjust the series in such a way such that the resulting sum is equal to the value of the block, which is this. And as you can see here that we have divided each of the individual bytes by 2 and we have obtained this series, and if I add these two series I get a resulting value of FECA8166. So if you match this first byte with this, you'll see that this is different. We wanted FF but we are getting FE, so that means that this division is with remainder, hence we cannot use this division as well. So let's move to the last test, which is divide the bytes by 3 and then adjust each series in such a way such that their sum is equal to the value of the block. And in this case you can see that I have divided each of these bytes by 3, so I've got 55, 55, 55, 43, 43 and 44 after adjusting, and then 2b, 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 and then 22, 22, 22. And if I add these three series, we get a final value of FFCA8166, which is equal to the value of our block. And this results in a shellcode of 26 bytes, which contains 10 bytes of shellcode to zero out EX register, and then we are adding the corresponding series and then finally pushing this value of EX onto the stack. So that completes our encoding process, and it will result in a encoded egg hunter of 173 bytes. I hope the encoding process is clear to you. If not, do this exercise on your own. Start from the preparation steps and then follow this algorithm to divide the bytes into respective series, and then match your results with the ones shown in this presentation. And if you have any questions or you need any clarifications or you have any suggestions, do reach out to me in the Q&A section or on the Discord channel of this course. Now, one thing I would like to note here that the approach that I have shown here is not the most optimized way to do it. There are several other techniques you can use to do the same thing. So if you want to invent your own technique, go ahead and share that with me. I will be more than happy to know and understand that. A more optimized way of doing this would have been to use an automated encoder, this alpha 2 encoder, and that would have resulted in the encoded egg hunter of 118 bytes. I have not used that approach here because I wanted to explain this process of manual encoding. However, if you want to try that on your own, do feel free to do that and share your results with me. So now we have our final egg hunter shellcode of 173 bytes. All that remains are the final two steps, which were to add the encoded egg hunter to our POC and then give it a test run. So let's first add this egg hunter to our POC, and to do that let's move to the lab. So this is the encoded egg hunter that we have just created, so I'll copy it and now move back to our POC, and here I will create another variable called egg hunter and I'll put this code here. Now let's include it in our payload. So I'll put my egg hunter here Then let us provide some padding to this egg hunter. So I'll put a into 38 and plus, and let's close this double quotes here. And here we need to adjust this value also to make it a total of 294. So if I subtract 173 from 250, I'll get 77, and then if I subtract 38 from it, I'll get 39. So let's put 39 here and save it. Now let's give this egg hunter a test run, but first we'll need to include our tag here. So we'll add ycsc twice, and again save it. Now let's launch a terminal and change to desktop. That is where my POC is saved. Now I'll run python zip poc.py. Sorry, so now our new POC zip file with encoded egg hunter is ready. So let's launch WinDbg and restart quickzip.exe. Run it. Let's play twice to move away from our breakpoint. And let me move this window here. Now I'll open our POC zip file, which is this, and let's see our file, and let's double click on this file to trigger the crash. So a crash has been triggered. Let's pass this exception to the program using shift F9. So we have hit our breakpoint on pop-up return instructions. Let's step into it. Now we have landed on the short jump. So we have taken a short jump of 55 bytes, and now let's carve out the long jump of 250 bytes. But first, if you remember that here, before taking this long jump, we had started the process of aligning the stack pointer to the larger portion of our buffer in order to carve out our egg hunter. But we have not finished that process yet. So before giving our egg hunter a test run, let's first understand this alignment process, and then we'll continue with testing our egg hunter. So to do that, I'll restart my application. And press play. And then play twice to move away from a breakpoint. And then let me put this quick zip window in the bottom and open the zip POC file, which is this. And then let's double click on this file to trigger the crash. I'll pass this exception to the program using shift F9. And then let's quickly go to our code wherein we are doing stack alignment for egg hunter. So I put a breakpoint here and press play. So now at this stage, we need to align a stack pointer again to this memory region, which is the larger portion of our buffer, so that we can start carving out our egg hunter, and then once we have carved out, we can reach to it. Now at present, if you see, the current value of ESP is 12FB F5, which lies in here where we have just carved out our long jump. Now we can choose to use this value of ESP and let our encoded egg hunter overwrite all this code to carve out the decoded egg hunter. However, do note that the size of decoded egg hunter is 32 bytes and the size of the code here is 34 bytes plus these additional bytes. So if we remain at this address, any further stack operations will start overwriting from here onwards. So if we are carving out our egg hunter from here till 32 bytes, and in between we'll get some of this leftover code which might interfere with the working of our egg hunter. So for this reason, it's better to move a bit further along in the buffer space so that our encoded egg hunter has sufficient space to carve out the decoded egg hunter, and then we can easily reach to it. So that is why we have chosen to move our stack pointer from here to a memory region that lies between these two memory addresses. So if I now add these two values to EAX into this value, you can see that this value now becomes 0012 FPDA, which lies in this region. And from here, if I now overwrite 32 bytes, all I will get between my encoded egg hunter and my decoded egg hunter is this padding of 41, which we already know that it will not interfere with our egg hunter shell code. Now since we have started this process here, we need to complete it also, and in order to complete it we need to push this value onto stack and then pop it in ESP. So we need to modify our POC accordingly. So to do that, we need to add push and pop instructions before the egg hunter. So the opcodes for that are 50 and 5C, but we'll write to F because we know that it gets translated to 5C upon execution. And then we'll remove 2 bytes from here and make it 37, and then save it. Let's generate a new POC zip file, and let's go back to WinDbg, restart the application, run it, and press play twice to move away from our breakpoint. And then let me shift this window here. Let's open the zip file, and then let's quickly open the file and double click on it. So our application has crashed. Let's pass this exception to the program using Shift F9. So now we have hit our breakpoint, and now we have taken a short jump. Let's carve out the long jump, and as you can see that the process to align stack pointer for egg hunter is started. And now finally we completed by pushing this value onto stack and then popping it in ESP. So now ESP has become 0012 FPDA. And now let's test our encoded egg hunter. So we are carving out our first block, which is this E7FF E775. So let's first zero out EX and add these 3 series of 4 bytes each, and then check this value. It's E7FF E775, which matches E7FF E775. And then we finally push this block onto stack, and if I go a bit down, you can see that this block has now been pushed onto stack, and before that there is this code which will eventually get overwritten with further blocks of our egg hunter shell code. So let's continue this process and move to the next block. And here you can see the value is AF EA75AF, which is equal to the value of our 7th block, which is AF EA75AF. So now let's push this onto stack as well, and let's check out our stack now. And you can see that AF EA75AF has been pushed, and the other code that was here has been overwritten. Similarly, let's carve out the 6th block, and the value of that block is FA8B4353, and you can check out from here FA8B4353. Let's push this value onto stack, and then if we move down and check, so you can see that These 4 bytes have now been written on stack, and other code that was there now has been completely overwritten with our egg hunter shell code, with these 3 blocks of our egg hunter shell code. Now similarly, continuing this process, and let's move on with the next block. And this time the value that we need to carve out is 4359B8EF, and if we check our presentation, the value of fifth block is 4359B8EF. So this seems to be correct. Let's push this on stack and move to next block, which is block 4th, and the value we need to carve out here is now 745A053C. And if we check in our presentation, value of block 4 is 745A053C. So let's push this onto stack as well and move on to the next block, which is block 3. And now we need to carve out this value, which is 2ECD5802. Let's verify this from our presentation. It's 2ECD5802. So let's push this value onto stack and move on to the second block. And now the value that we are pushing is 6A52420F. Let's verify this from our presentation. 6A52420F, and that is the value that we saw in our EX register. So let's push this value onto stack as well. And then finally let's carve out our first block. And the value that we need to carve out is FFCA8166. And if we verify this with a presentation, the value of first block is FFCA8166, which is same as here. So let's push this onto stack. And now if we see our egg hunter shell code, you can see that this is the decoded egg hunter shell code, which is of 32 bytes. So let's put a breakpoint here and press play. So now we have landed on our egg hunter shell code. Let's give it a test run. So I'll remove the breakpoint from here and put a breakpoint on the final instruction, which is jump EDI. Press yes, and then let me first change the size of this window. Alright, now I'll press play. So you can see that our egg hunter code is running and our application is also running. So once it has found our egg, our breakpoint should get hit. Alright, so it says that breakpoint at this memory address has been hit. So that means that it has found our egg, and now it's ready to jump to our payload shell code, which is this region where we have put D's for now, and 44 is hex for capital D. So that means that our encoded egg hunter is working as expected, and we have landed on the buffer where we put our final payload shell code, which is something we'll cover in the next video. So I know that this particular building block was a bit complicated as it involved a lot of steps, and I really hope that you are clear and thorough with all these steps. If not, just go back to the step where you're confused, see that video again, see the explanation, and if you need, read it on a bit on internet. And if you have any further questions or any doubts regarding the entire process that we have done so far, do reach out to me in the Q&A section or the Discord channel. I want you to be thorough with this process so that next time when you tackle any such problem, you know what to do and how to do that instantly. So that was it for this video. These are the few learning resources you can use to learn more about the tools, techniques, and software we are using in this module. Thank you for watching this video, and I'll see you in the next video. Hello, and welcome to part 6 of acrobatics module. So now we are finally onto the last building block of this part and also the last video of this module, and this is when all things that we have done so far finally come together and they will give us something that we have been waiting for so long, a reverse shell from a target machine. Such a beautiful thing. Let's move on to this building block, and there is not much that we need to do in this part. So now all that we need to do is generate our payload shellcode using MSF Venom. I will be using Windows Metapreter Reverse TCP, and this is the IP address of my Kali machine, and we'll be listening on port 4444, and I'll need it in raw format, so that is why I've specified capital R, and we'll save the output in a file name quickzip.raw. Then finally we'll use alpha2 encoder to encode this payload shellcode, and we'll specify the register EDI because as you might have observed in the last video, the egg hunter finally jumps to the EDI register where our shellcode starts. So that is why we are specifying EDI, and we'll need it in all uppercase. And then finally we are feeding it the file or the payload shellcode that we had generated from MSF Venom. And then we'll set up a multi-handler on Metasploit to listen to the reverse connection that will be sent via the target machine on port 4444. So let's move to the lab and generate a payload shellcode first. So I'm on my Kali Linux machine, and here I'll write MSF Venom, and payload is Windows Metapreter reverse underscore TCP, and lhost is 192.168.126.163, and L port is 4444, and we'll need it in raw format. We need to save the output in quickzip.raw. Alright, now in this case we need not specify bad characters because we will be eventually encoding our shellcode with alpha encoder, and that too with uppercase characters, and all those characters lie in our allowed character range. So I'll press enter to generate the shellcode. So you can see that it has generated a payload shellcode of 341 bytes, and if I perform a quick ls, you can see that we have a file called quickzip.raw here. Let me clear it out and let's run alpha2 encoder using alpha2, and this register I need to specify is EDI. We need a shellcode to be encoded in uppercase character, and the file that we are feeding you is quickzip.raw. So this is our shellcode as encoded by alpha2 encoder. So I'll copy it, and before that let me just start MSF console because it takes some time to launch. And now let's go to our XP machine and add this shellcode to our POC, which will now get converted into an exploit, and I'll put a variable called scode here, and I'll put this code in here, and then I'll just put this variable here, and let's reduce around. So what is the size of this shellcode? This comes out to be around 700 bytes, 742 bytes. So let's make it 3000. So now I'll save it, and let's generate the new POC zip file. And before that, let's close all the windows that are not needed. Alright, so let's go to WinDbg and restart the application. Run it. Press play twice. So now the application has started. Let me open the POC zip file. Now our application is crashed, as you can see, and let's pass this exception to the debugger using Shift F9, and we have hit a breakpoint. Let's quickly take a short jump and then carve out the long jump, then take the long jump, and then finally carve out our egg hunter. So instead of stepping through, I'm just putting a breakpoint here and let this code run. And now let's come to our egg hunter and place a breakpoint here. So now I'm letting the egg hunter run, so it will find our egg and eventually jump to our shellcode. So you can see that it's running now. Now before I take this jump to our shellcode, let me set up multi-handler. So I go back to my Kali machine, and here I'll write use multi-handler, set payload Windows meter getter reverse TCP, set L host 192.168.126.163, and set L port 4444. So by default it's 4444, but anyways I'm setting it, and let's run. So our reverse handler is now running on port 4444 on this machine. And now let's take the jump to our shellcode. So this is our encoded shellcode of around 700 bytes. And now let's run it and see what happens. So it says that access violation has happened. And if we check our Kali machine, and so we have got nothing here. So it looks like something has gone wrong with our shellcode. So I know what is wrong here. Let's see if you can figure it out. So while working on this exploit, I did run into this issue, and if I say that I figured it out at once, I would be lying. It took me some trial and error to figure out what the problem was, and one of those steps that I took during trial and error was to send the message box shellcode, because that is a very simple shellcode and a bit lower in size. So that worked well. And remember that whenever you are stuck in these kind of situations, it's better to start with a simple shellcode and then move on to complicated shellcode such as meterpreter reverse shell or even bind TCP or reverse TCP shellcode. So coming on to the issue here, if you observe the value of ESP and EBP registers, they are same. So that means our stack is now non-existent because EBP and ESP point to the same memory location. Now in order to rectify this issue, we need to do stack adjustment again after we have carved out our decoded egg hunter, and you can either add to the value of ESP at that time or subtract to it. Just make sure that it does not interfere with your egg hunter and it's far away from the value of EBP in either direction. So I have already prepared this 8-byte shellcode here. So let's just copy this and put it in our POC, and we need to place it after our encoded egg hunter. And instead of 5C, let's put 2F here. And since this is 8 bytes, we need to minus 8 bytes from here. So let's make it 30. Save it, and let's generate our POC again. Now I'll explain to you the working of this shellcode when we are executing it. So don't worry about that. Let me restart this application. Run it. Breakpoint. So our application has started. Let me place it here, and I'll open the POC zip file. Let me just quickly come to the file. So So an application has crashed, and after passing the exception to the program, we have hit a breakpoint. Let's just step into it. Let's take a short jump, and now let's carve out the long jump. And let's take the long jump, complete a stack alignment for egg hunter, and then finally carve out an egg hunter. And now let me put a breakpoint here. So this is the 8-byte shellcode that we had written in order to align the stack pointer again. So we are pushing this value of ESP onto stack and then popping it in EAX, as you can see here, and then subtracting 0606 from this value, and then we are finally pushing EAX onto stack and then popping it into ESP. So as you can see here that the value of EX is now 1 to F5B4, which is much above this region, and also it's above the current value of EBP, which is 1 to F698. And as we know that the stack grows from higher to lower memory address, so any stack operations will lead to a lower memory address than this, and we'll never run into a problem of stack being completely wiped out. So let's pop this value into ESP. So now ESP is pointing at this location, and now let's go to our egg hunter. I'll put a breakpoint here and let the egg hunter do its magic. So we are ready to take a jump to our shell code, and now if I run it, you can see that application is running. And now if I go to my Kali machine, you can see that we have received a metapletter session from this target machine. And finally, all of our hard work has paid off in terms of this beautiful shell from our target machine. So let's verify it. So this is the Windows XP machine that we are working with. And if I go into the shell of this machine, and let's check the IP address by ipconfig. So the IP address of this machine is 192.168.126.160. And let's go back to Windows XP machine, and let me clear this window, and if I run ipconfig here, I'll get 192.168.126.160. So that means that we have successfully exploited our target via quickzip.exe. So let's exit this shell and let's see if we can get further access to the system using get system command. So it says that it got system via technique 1. So if I now get UID, you can see that we are NT authority system, which is the highest level of access on any Windows machine. So as usual, check out the help section of metapletter and play around with various commands. So in this case, let's say if we try hash dump. So we have successfully extracted hashes for various accounts on this machine as well. So go ahead and give these commands a try run and have fun with metapletter and your newly exploited target machine via quickzip.exe. So finally, this brings us to the end of this module. And as you already know that this was a much longer module than any of the previous modules that we have had in this course. But the reason for that is that we have covered a lot of ground in this particular module. We have indeed created a very complicated exploit by first understanding a file format structure and then reversing it to create a POC, and then finally tackling the limitations of character set using manual encoding and automated encoding. So now if we go back to the bird's eye view slide that we saw in the first part of this module, which is this. So you can see that we have covered fuzzing acrobatics. We did reverse the zip file format for fuzzing, and then we used manual and automated fuzzing to fuzz quickzip.exe. And then in terms of exploit, we used two techniques. One was SCH overwrite, and we combined that with egg hunters. And then in terms of shellcode, we used a short jump, wherein we used complementary conditional jumps to take this short jump. And then we carved out a long jump onto the stack and then took that jump. And while doing all this, we covered shellcode carving onto stack, and we also covered stack pivoting by aligning ESP or stack pointer again and again. And then finally, in terms of encoding, we covered manual alphanumeric encoding, wherein we encoded our egg hunter manually using the technique that I showed you earlier. And then finally, we used alpha to encoder to encode our final payload shellcode. So that was automated encoding. Now you can give yourself a pat on the back for having learned so many acrobatic techniques in terms of exploit development. And even if you see Golang coders write up of this exploit, he does say that it's a box of chocolates, and there are various complications that he talks about in his write up, which we have all covered in this module. So I really hope that this module was fun to learn, and it has been a good exercise in combining various techniques that we have learned in this course so far and then create a complicated exploit out of them. So that's it for this module, and once again, congratulations if you made it till here. You now know how to write complicated exploits for complicated file formats. So these are the few learning resources you can use to learn more about the tools, techniques, and software that we are using in this module. Thank you for watching this video, and I'll see you very soon in the next module of this course.